How do polar coordinates work? So the polar coordinates are an alternative coordinate system for the Cartesian plane. And that's not a very good x-axis. Let's try again. There we go. So normally we label our axes as x and y, and if we want to locate a point within space, within this plane, right, the way we do it is we measure the distance of this point from both of the axes, right? We measure the distance from the x-axis, the distance from the y-axis. So the coordinates x and y that we ordinarily would use to label a point, x, y, these are often referred to as rectangular coordinates because, well, you can sort of see the rectangle which is formed here. You have x, y, and the origin at opposite corners of this rectangle. You can see the two sides sort of dashed out there in green. And so this is one way of locating a point in space. This is, it's a grid coordinate system. It's a sort of, if you were navigating in, like, I don't know, Manhattan or somewhere like that, you're in a busy city where you've got streets that you can move on. You can only move north-south or east-west, but those are the only possible motions that you can make. This is the sort of coordinate system that you might want to use. This, of course, this coordinate system goes all the way back to René Descartes. Legend has it that he discovered this coordinate system while lying sick in bed and watching a fly crawl around on the ceiling, and realizing that he could specify the location of the fly by knowing how far away it was from each of the walls. The Cartesian coordinate system, the rectangular coordinate system, it works great for a lot of things, but it's not always the best tool for the job. The other way that you can locate a point in the plane, once you have an origin, right? Rather than moving on city streets, think about navigating on the ocean or wide open spaces. If I wanted to get from the origin to that point, I probably wouldn't do it by traveling first horizontally and then vertically. I would probably just go directly from point A to point B by pointing myself in the correct direction and then walking the appropriate distance. And that's exactly what the polar coordinate system is for. So the polar coordinates are calculated as follows. I can construct the line segment from the origin to the point that I'm interested in. I can label that segment by r, where r is the length of that line segment, so the distance from the origin. And we know how to measure distances. We know that r, this distance from the origin, is given simply by x squared plus y squared. And theta, as usual, is just the angle between the positive x-axis and the line segment that you've drawn. So there are a number of ways that you can define that theta, but one way to specify that theta, if you know x and y, if x and y are the quantities that you know, then if you think in terms of, triangle trig, you've got this triangle sitting here like so, and you can think in terms of, opposite over adjacent. You could say that tan theta is equal to y over x. And so your polar coordinates are these two numbers, r and theta, and this simply gives you another way of locating a point in space, right? If I know the value of theta, I know which direction I'm facing. If I know the value of r, I know how far I need to go, and this is going to let me get to the point that I'm interested in. The only thing to kind of beware of here when you're dealing with polar coordinates is note that there are some ambiguities. So, for example, the point. So we might label this point here as, instead of labeling it as x, y, we might label it as r theta. Note that the point r theta will be the same thing as the point r, and if I add some multiple of 2 pi, right, where k here is an integer. So theta is not uniquely defined because I can go all the way around as many times as I want. I can add as many revolutions as I want. I can instead of going here, I could go once around, but I could go around and around and around and around and around, and I would still end up facing in the same direction. Now probably if you're using this to navigate, you don't want to spin yourself around too many times before you start out, or you'll get dizzy. But as long as you kind of are, moving in a straight line in the right direction, then you're going to get to the point that you want to get to. And of course, you could measure, we by default we measure our angles counterclockwise, but you could measure a clockwise angle. That could work too. If you learn about polar coordinates in a calculus course, you may also learn that you can sometimes consider r to be negative. You can consider a negative value, which means instead of going forward while facing in a certain direction, you walk backwards. And so then, there are some different ways that you can express a point where you allow r to be less than 0. We're not going to concern ourselves with the case where r is less than 0 in this course, because for us, r is always going to be the modulus of a complex number, and we'll see that that's always defined to be positive. In fact, the modulus of a complex number is just given by this quantity here. And the other thing that you should note is that so the origin 0, 0, x is equal to 0, y is equal to 0. It's simply defined by setting r equal to 0. So r is 0 and theta is undefined. There is no value for the angle if you're at the origin, right? If it doesn't matter what direction you're facing. If you're already at the origin, you're at the origin. There's nowhere to go. So the equations that we've written down here, these guys, they tell us how to kind of calculate r and theta if we know x and y. But of course you can convert the other way. A little bit of triangle trig, so cosine theta we know is adjacent over hypotenuse, sine theta opposite over hypotenuse. We can play around, and we can also convert back, and we can say, all right, x, x over r would be equal to cos theta. So that tells me that x is equal to r cos theta. Y over r should be sine theta, so y is equal to r sine theta. Now, to some extent, maybe this seems like an artifact of drawing my picture in the first quadrant, but you can play around and you can check that if you have a point in another quadrant, you have an angle that lands you in another quadrant. These conversion formulas for converting from polar back into Cartesian, they remain valid no matter what quadrant you happen to be in. Okay, so that's the polar coordinate system. Before we finish with it, let's do a couple of examples just to make sure that we have the hang of it. So let's say we want to convert a few points. So let's convert the points. Let's do 2, minus 2, and let's say 3, 4, 2 to polar. All right, so let's say we want to convert these 2 points. Let's deal with 2 minus 2 first. Okay, so here we're dealing with, and maybe it helps to draw a little picture. Let's just kind of stick it down here in the corner. So x is equal to 2, y is equal to minus 2, so we're down here in the fourth quadrant, like so. And notice that aside from the sign, the absolute value of x and y, both of them are equal, and so we already know what this angle should be. We can guess the angle, right? This angle is going to be minus pi over 4. That happens to be one of these special angles that we're familiar with, so we can write that one down, and where everyone is happy. We got to figure out what r is. So what is r? Well, we know that r is the square root of x squared plus y squared, so in this case that's the square root of 2 squared plus minus 2 squared, so that's the square root of 4 plus 4, which is the square root of 8. By the way, you can leave it as square root of 8. If you really feel like you have to, you could write this as 2 times the square root of 2, but square root of 8 is perfectly valid. And so the point 2 minus 2, if we were to write this in polar coordinates, we could write this as root 8 for the r value and minus pi over 4 as the theta value. And again, you're not forced to write that as minus pi over 4. If you want to, you could also do, instead of doing the clockwise revolution, you could go counterclockwise. You could go with, say, 7 pi over 4. That would also be perfectly fine. The r value is set in stone. The theta value, you've got some freedom to choose. All right. What about for the point 34? So here is one where, okay, calculating r comes out, this works out nicely. This, our sort of 3, 4, 5 rule, right? 3 squared plus 4 squared. So we get 9 plus 16, which is the square root of 25. So we get 5 for r. Okay, so that's good. Now, when you want to calculate theta, this happens to be a case where there's no nice way to write down the value of theta, right? This point, it doesn't correspond to one of these special angles. If y is equal to 3, x is equal to 4, the best thing we can really say here is that tan theta is equal to 4 over 3. That's about the best that we can do. Or you might say that theta is equal to arctan, if you like, 4 over 3. If you want to work with the inverse, if you're familiar with inverse trig functions, some people write this as tan to the minus 1. You can do it that way if you like. Okay, let me just clean that up. The handwriting wasn't so good there. Now, there will be a few problems where it comes up like this, where I give you a point that doesn't correspond to one of these sort of angles where you can write down the exact value for theta, a pi over 4, pi over 3, something like that. Occasionally this will come up, but we'll try to avoid it for the most part and keep the computations simple, especially in a test scenario or something like that. The one place where you may run into this might be on, say, an online homework problem or something like that, where the online homework, often they're generating these values randomly, and you might end up with some funny numbers. The only one thing I'll caution you about is, let's say we did this problem over again, but let's say I gave you the point in the third quadrant. So we were down here. We're at the point minus 3, minus 4. So then you kind of have to play around a little bit, because if you were to calculate tan theta, you would actually get, you would get minus 4 over minus 3, but that comes out to be 4 over 3. And then you run into a little bit of a problem, because it's no longer true that theta is equal to arctan of 4 over 3, because theta is equal to arctan of 4 over 3. That's this angle here, okay? That's this angle that we found originally. This arctan function is defined so that it always gives you an angle in either quadrant 1 or in quadrant 4. It never gives you an angle in quadrant 3. So how do you fix that? Well, one of the ways that you can fix it is you could say, all right, I guess what I'm looking at here is, well, if that angle is theta, then this angle here, that would be the same angle there. So what you would have to do if you wanted to get a point like that, I guess let me draw that a bit better. I'm here, right? Is say that, well, this angle is the same as this angle. And so what I'm really looking for, if I want to write down theta, is I'm looking for this angle. And so what I need to do is I need to take this value and I need to add on this half of a revolution. So down here, if I was working in the third quadrant, I would have to say theta is equal to pi plus arctan of 4 over 3. So sometimes, this is where maybe sometimes the trig can get slightly complicated. That's about as bad as it can get, though, for us. Okay. Converting from polar to rectangular. Polar to rectangular is a little bit better. So let's say we do, r is equal to 4, theta is equal to pi over 6. Well, converting this is straightforward because I say, all right, x is equal to r cos theta, y is equal to r sine theta. So now it's a matter of plugging things in. 4 times cos of pi over 6, 4 times sine of pi over 6. So this is 4 times root 3 over 2. This is 4 times 1 over 2. And so my point xy in this case is just going to be the point 2 root 3 and 2. So that's pretty straightforward. The only kind of thing we could make that would be tricky here would be maybe I tell you that r is equal to 3, and again maybe I tell you something like theta is equal to arctan of, I don't know, let's say 2/3, something like that. Okay, so here things are a little bit trickier. If you want to give exact values for x and y, one of the ways that you kind of do this, one of the ways you can figure this out is you draw yourself a little triangle. You put theta in one corner and you say, okay, so arctan 2/3. This is telling me that tan theta is 2 over 3, right? And remember that tan theta should be like opposite over adjacent. So that should be a 2, that should be a 3. It's a right-angled triangle, so Pythagoras tells me that this should be square root of 2 squared plus 3 squared. So square root of 13. And then I can figure out what cos theta and sine theta should be, because I know I can do adjacent over hypotenuse, I can do opposite over hypotenuse. So x is going to be 3 cos theta, so 3 times 3 over root 13, so 9 over root 13. Y is 3 sine theta, so 3 times 2 over root 13, so that's 6 over root 13. And now you've converted back to rectangular coordinates. As a reminder, you start with the real number system, and we've already gone over the fact that there's some difficulty in giving a careful definition of the real numbers, and we're not going to bother getting into the technicalities of that here. But you picture the real numbers as this continuous number line. There's no gaps in there. You can, as you move along, as you move from point to point to point, every single point on that line corresponds to some number. And there's no limit. You can keep going forever. If you go off to the right, you sort of head off towards, positive infinity. If you head off the other direction, you're off to negative infinity. Of course, plus and minus infinity, these are not real numbers. They're just, this is a way of indicating that there is no end to the real number system. You can increase them forever and ever. You can get bigger and bigger and bigger. There's no limit to how big you can make your numbers. All right, and so of course all the integers are in there, all the rational numbers are in there, but roots are in there, numbers like pi, e, all these numbers are there in the real number system. Anything that you can write down with a decimal expansion is going to give you a real number. Okay, and then of course, so the Cartesian plane, the one that we're familiar with, both from high school and from working with our complex numbers, the set of all ordered pairs. So as a set, we haven't assigned any geometry to it yet. We just simply make this definition right here. Right, so we say it's a set of all ordered pairs. And by ordered, what we mean by ordered is we mean that, the pair xy is not the same thing as the pair yx. Well, unless x is equal to y, right? So changing the order changes the element of this set, changes the point. And the way we like to visualize these things is we kind of think of each of these two real numbers as giving you a point along some number line. And so we have two axes, right? You have an x-axis, you have a y-axis, and the convention here is that the x-axis increases from left to right, so this is the positive direction, this is the negative direction. The y-axis increases from bottom to top, so this is negative, this is positive, and they meet at the common 0. So where they cross is the 0 value for both x and y. And so if somebody hands you an ordered pair, they give you something like, say, the point 2, 3. This is telling you that x is equal to 2, so you kind of go, okay, 1, 2, there, x is equal to 2, y is equal to 3, 1, 2, 3, right? But the way you actually identify that point is, you kind of draw you've got sort of 3 of the 4 corners of a rectangle, so you complete this rectangle, and you kind of draw things out like that, and that remaining corner of the rectangle, you mark that spot and you label that as the point 2, 3. So you think of these two numbers 2 and 3 as giving you the measure of how far away that point is from each of the two axes. And of course, you can see this idea that this ordering matters, because if we switch to, say, the point 3, 2, if we want to do the point 3, 2, well, then we'd have to go, x is equal to 3, so we go 3 units out in the x direction. We only go 2 units in the y direction, and our rectangle then would look like this, and we would have this guy here, the point 3, 2, and we can see that indeed that is not the same point as the point 2, 3, right? So this ordering matters. So what we do now is you take this idea and you extend it. You don't have to stop with 2 variables. You could extend to 3 variables. You say R3, x, y, z. You add a z coordinate, and so on. But you don't actually have to stop at 3. You can consider any number of variables. So we can define in general the set Rn to be, so what these elements, they kind of have a funny name. These guys are sometimes called ordered n tuples. So this n tuple is some attempt at generalizing language of double, triple, quadruple to n tuples, where n could be any positive integer. At some point, you run out of words for this, and so the ordering again means that if you swap any 2 of these n numbers, then you get a different element, right? So you've got a first coordinate x1, second coordinate x2, third coordinate x3, and so on, and so the order matters, right? If you change any 2 of the positions, you change the point that you're talking about. And now, of course, if you're dealing with 4 or more variables, there isn't really a picture you can draw. You can't picture things anymore. You can't visualize it. But that kind of limitation, of the human brain to visualize things beyond 3 dimensions is not a limitation that's shared by the mathematics. The mathematics works just the same, no matter how many variables you have. And you do want to consider more than 3 variables. There are lots of practical problems where you might be dealing with hundreds or thousands or even millions of variables. Think of problems coming from economics, from finance, even from physics or chemistry. You might be dealing with large numbers of variables, and you want some mathematics to be able to describe these things, and so you have to move to these sorts of sets. Now, in 3 dimensions is the only one we haven't drawn, which we can draw. So in R3, the picture for R3, we get something that looks like this. So the way you kind of try to visualize R3 is you imagine you're looking at like the corner of a room. So you get something like this. And so these 3 lines, these 3 edges that kind of converge at one point, this is how you represent the 3-dimensional coordinate system. And so you think of these as your coordinate axes, label them x, y, and z. This is not the only labeling you could choose, but it's usually the one that we'll work with. It's the most convenient one that you can work with. And we draw this so that what we've drawn here are the positive x, y, and z axes. And of course, these do extend in either direction. So the x-axis goes off that way, and the y-axis goes off that way, and the z-axis goes off that way. We often just draw them like so. And so of course we, just as with R2, we require that everything meets at the common 0. So this point, is the point 0, 0, 0, and then every other point can be plotted with reference to these axes. The only problem is that when you try to plot a point, you're trying to draw a three-dimensional picture on a two-dimensional surface, and this generally ends badly. So if we have a point, right? So here's a point. We can describe that point by these coordinates x, y, and z. But how do you actually kind of picture this location in space? If you've got some nice 3D graphics software, you might be able to set up something where you can input values for x, y, z, and then rotate your point of view and look at it from different directions and get some idea of what you're looking at. If you're trying to draw this by hand on paper or on a screen, what you can do, one way you can kind of get around this is you can imagine, so you can imagine that down here is maybe the shadow of that point on the xy plane where z is equal to 0. So you can think of, there's this copy of the xy plane sitting here, right? And so that's where that drops onto. And then of course, once you've got that point in the xy plane, you can situate it with respect to the x and y axes. So you can drop this over, and so here would be your point. So this would be, x 0, 0, and you could go along this way parallel to the x-axis until you hit this point on the y-axis corresponding. So this would be the point 0, y 0. The z-coordinate is a little trickier. Where does this thing, where's the shadow on the z-axis? Well, what you can do, just like in R2, we kind of visualize things using rectangles. Well, in 3 dimensions, the 3-dimensional version of a rectangle is a box. So you've got part of a box sitting there already. So we complete this box. So we kind of draw the remaining sides. And we get something like so. And then you can see, okay, there's this corner of the box that actually hits the z-axis. And so the point 0, 0, z is sitting right there. And now you've got this kind of 3-dimensional box there, which lets you kind of get some idea of how you would visualize a point in 3-dimensional space in this sort of 2-dimensional drawing. Okay, now from here we want to talk about distance. And we've talked a little bit about distance in the context of complex numbers, because we've talked about, the modulus of complex numbers, is the distance from a complex number to the origin. And you can even talk about distance in one dimension. So the absolute value function, and just to remind you, if you haven't seen the absolute value function before, the absolute value of a number is, well, if you give it a positive number, nothing happens. So if a is bigger than or equal to 0, it just gives you back a. If you plug in a negative number, it says, I don't want a negative number, I only want a positive number. So it switches the sign. So if a is less than 0, it gives you minus a, right? And now remember that if a is negative, the negative of a negative is going to be positive. So minus a would be bigger than 0 in this sense, right? So the absolute value is basically telling you how far away any real number is from 0, right? And then if you want to figure out the distance between two other real numbers, well, you take their difference, right? The difference tells you how far apart those two numbers are, but the difference could be negative, and you'd like distance to be positive. The absolute value guarantees that outcome will be positive. One way, by the way, to write the absolute value is as the square root of a square. Because notice that if you take, say, the square root of, let's say I take minus 2, I square it, and then I take the square root. Well, squaring minus 2 gives me plus 4, and the square root here always denotes positive square root. So, you plug in minus 2, you get out plus 2, which is minus 2, right? So 2 is equal to minus 2. It's consistent with this definition of the absolute value. And so in 2 dimensions, we know that the Pythagorean theorem holds for us, and the idea is if I've got 2 points in the plane, if I've got an x1, y1 over here, and I've got an x2, y2 over here, I want to measure the distance between them, and so what I do is I kind of, I can draw in a little right-angled triangle like so, and this is the distance we're looking for, the length of the hypotenuse. But we know that the length of the base here is just going to be x2 minus x1, right? The difference between the x coordinates. The height is going to be y2 minus y1, right? As I've drawn it, x2 is bigger than x1 and y2 is bigger than y1, so I've done x2 minus x1, y2 minus y1. But of course, if I'd done it the other way around, I would get the negative of what I have here, but when I square things, that negative goes away, and so we get this distance formula right here. And it's coming exactly from the Pythagorean theorem. All right. Now, what if you want to extend this distance formula to higher dimensions? Well, in 3 dimensions, you can actually show that that the same definition works. So, if you have one number, you square it, and then you take the square root. If you have 2 numbers, you take the sum of the squares, and then you take the square root. If you have 3 coordinates, well, now you have 1, 2, 3 squares. You add them up, and then you take the square root. And then in Rn, you just kind of, you go with it, and you say, okay, the distance between, well, now things get a little bit harder to kind of, specify, but maybe I have something like, the distance from A1, A2, down to AN, and, B1, B2, down to BN, and you take the difference between the A1 and B1s and the A2 and the B2s, and so on down to the last coordinate, and then you take the square root of that whole thing, and that should give you the distance, right? You just kind of assume that this pattern continues. How do you see that the pattern should continue into 3 dimensions? It's a little bit tricky, but let me sketch things out. Well, let me sketch things out in the case that we're just dealing with distance from the origin. So from 0, 0, 0 to a point x, y, z, because that's a little bit easier to draw. So the idea is we do the same kind of trick we did previously to kind of locate our point. So we drop that point down onto the xy plane. Here's our distance x, y, 0. And then we say, okay, well, we've got 2 sides here. The length of this side is just z, right? Because this is just, from the xy plane up to the point x, y, z. The difference between the 2 is just the change in the z coordinate. Now, this distance here, we can think of that distance as being measured in the xy plane, right? X, y, z, those are our coordinates. And so we can use the distance formula from the previous slide for distance in R2. We can think of this xy plane as a copy of R2. And so this distance should simply be, square root of x squared plus y squared. Using, if you like, it maybe doesn't quite look like a right-angled triangle, but, this is a right-angled triangle here, where this side has length y, this side has length x, and so Pythagoras tells us that this side should have length x squared plus y squared. But there's one more right-angled triangle, which is this guy. And again, because we're doing perspective drawings, it doesn't quite look like a right-angled triangle. But it has to be, because that vertical line, right, that's landing straight on the xy plane. So that's a vertical line meeting a horizontal plane. Those definitely meet at right angles. So that's a right-angled triangle. This is the distance that we're interested in. And, well, we can see that one of our sides is this square root here. The other side is this guy. And so the distance squared is going to be square root of x squared plus y squared plus z squared, which is just x squared plus y squared plus z squared. And so taking the square root, and of course distance should be positive, you take the positive square root, that gets you to this distance formula here. Okay, so that's it for the Cartesian coordinate system. We'll be moving on to vectors in the next screencast. Okay, welcome back. This will be the first of our screencast videos on vectors, continuing on with the material in Chapter 3. So we're on, I guess this is, if you're following along in the textbook, we're at section 3.2 here in the textbook. So in the previous video, we introduced Cartesian coordinate system using coordinates to identify points in 2 and 3 and higher dimensional space. And today we're going to talk about vectors. And so we think of vectors as kind of giving us a method for navigating between points, as giving us sort of directions as how to get from one point to another. Now there are really, throughout mathematics, this word vector pops up all over the place, and it has a lot of different meanings depending on the context. And there are a lot of areas that use vectors and have a lot of applications. So anyone who's done high school physics has encountered vectors, and you're used to thinking of vectors as some sort of directed quantity, something that has both a direction and a magnitude. Magnitude you think of somehow as being like length, but often you think in terms of velocity, force, acceleration, maybe like the electric field, magnetic field, things like this. The strength of the field corresponding to the magnitude, and then the direction in which it's pointing. In mathematics, vectors are sort of viewed as algebraic objects. We're going to see that as we move through this course, that vectors are things that you can add together. You can multiply them by numbers, and there are certain rules that these operations have to follow. And so mathematically, that's where we kind of look at vectors, so algebraic objects, things that follow certain rules of algebra. You might think of vectors in terms of data analytics. You've got some information, you want to put it in some sort of order so you can keep track of it, but you might need to also manipulate that data. You might need to, take averages, do things like this, or maybe you're dealing with graphics processing, things like this. There are all sorts of places where vectors show up. And one of the things that we'll see is that these kind of algebraic and geometric points of view, which dominate a lot of the discussion of vectors, they're really just two ways of looking at the same thing, and both have their advantages, right? The downside to the algebraic point of view is you don't have a picture that you can work with. The downside of the geometric point of view is that it's not precise. You're drawing pictures, and there's always a little bit of room for error when you draw a picture, right? You can't draw a line that is infinitely thin. You can't draw a point which is really a point. There's always some size to a point, and so you can't do things accurately by simply drawing a picture. Okay, so like I said, a geometric vector, this is something that's viewed as an arrow. So if you are in, if you're in, 2 dimensions, 3 dimensions, you might have sort of something like this. Let's draw a 2-dimensional picture. So let's say I'll put it down here in the corner. You've got a pair of coordinate axes, and you've got a couple of points. You've got a point here, a point P. You've got some other point Q over here, and a vector is just going to be the arrow between them. So you draw a vector from a point P to a point Q, and the notation we would use if these 2 points are specified, you would call this, you'd put a little arrow over the letters PQ to indicate that we're talking about a vector here. So this is the idea of a geometric vector. You think of this arrow, and the way you can kind of get all the information about this arrow is contained in the coordinates for the 2 points. So this point is sometimes called the tail of the vector. The point Q is sometimes called either the head or the tip of the vector. And now this, I've drawn the 2-dimensional picture, but this is a picture that you can draw in any number of dimensions. Well, okay, you can draw it in 2 or 3 dimensions. You can kind of imagine that you could do the same thing in higher dimensions, but you can't really draw the picture anymore. So the thing to realize here is that what's important about this vector, about the 2 points, is really the differences between the coordinates. So the difference between the first coordinates, the second coordinates, the third coordinates, and so on, right? I can kind of take this vector and I could break it down. I could draw, this triangle in, right? And I could break it up into sort of horizontal and vertical pieces, and the length of the horizontal piece, is going to be the difference between the x coordinates. The length of the vertical piece is going to be the difference between the y coordinates. And kind of the way you might want to think about it is if if this point P, right, so if P is equal to, maybe this is the point x1, y1, and Q is equal to the point x2, y2, um, so then the vector PQ would be this vector x2 minus x1, y2 minus y1, and so we record these numbers, right? And now that we've described a vector using numbers, we have something which is precise, right? We're not just relying on this picture of an arrow. We have these numbers that we use to encode the vector, and numbers are precise. The arrow is not so precise, but the numbers are. And what these numbers are telling us, these numbers are really telling us how to get from the point P to the point Q. They're saying, okay, you start at this point x1, y1, and, well, what does the first component, this x2 minus x1, what is it telling me? Well, one way to think about it is it says, okay, you start at a point that has a coordinate x1. Now you add on the corresponding part of the vector, x2 minus x1, and you add that on, and then you see what's the number you get to. Well, notice that if you simplify here, the x's, those cancel out, and leaves you with simply x2. And of course you can do that for the y coordinate as well. And so what that vector is telling you, this vector gives you in this case a pair of numbers, and it's telling you, okay, take these numbers, add them to the coordinates of the point P, and you will end up at the point Q. So it's telling you how to get from one point to another. Okay, so just to give you a quick example, let's take this two-dimensional picture, and let's say that maybe P is equal to the point 1 minus 4, maybe Q is equal to the point minus 5, 2, and so the vector PQ would be, and again, remember, you got to be careful here that one of the common mistakes is to subtract in the wrong order. You always want to do tip minus tail, right? So this vector from P to Q, we want the differences between the head and the tail. So we want to do tip minus tail. So we do the coordinates for the tip, minus 5 and 2, and we subtract off the coordinates for the tail. And again, be careful about signs. You're subtracting minus 4 when you subtract the y coordinates there. And so you get minus 5 minus 1 gives you minus 6. And 2 minus minus 4 becomes 2 plus 4. So you get the vector minus 6, 6. Okay. And again, just as a reminder, you're doing this kind of head minus tail or tip minus tail rule to construct this vector. And again, as I said, notice that if you take those numbers, minus 6 and 6, if you add them to the P coordinates, you will end up with the Q coordinates. Okay, so one of the things that you want to kind of keep in mind when you're working with vectors, and one of the conventions that we take, is that, if we think of a vector as a geometric object, as something that's characterized by magnitude and direction, then we would say, well, any two vectors that have the same magnitude and same direction should be viewed as the same vector, regardless of how we draw them, in our coordinate system. So if I had, if I had two vectors, say here, and I'll try to draw them carefully, and here, that are pointing in the same direction, and they have the same length, I would say, well, those are basically the same vector, right? I've just drawn it with the tail at two different places. And so you can see that this works if you, if this is sort of, P, and this is Q, and down here is R, and this is S, then one of the ways that you kind of get the same vector, you can see that, well, however I move the tail, right, whatever direction and distance I move the tail, and in fact you can kind of think of that as a vector too, right? You kind of have this guy here. So that vector and that vector, those must be the same. These must also be the same. Maybe call that guy W, right? However I change the tail, I must change the tip by the same amount, or else I'm going to affect either the magnitude or the direction, right? If I lower the tail, but I don't lower the tip, I'm going to end up rotating that vector. So the way you kind of represent this numerically is you'd say, well, if P, P was the point x1 down to xn, Q was the point y1 down to yn, as on the previous slide. So if I add, whatever numbers I add to the coordinates of P, say a1, a2 up to an, if I add the same numbers to the coordinates of Q, then I get two new points, and kind of the distance and direction from R to S is going to be the same as from P to Q. And you can see this in terms of vectors because, if you calculate this, the vector from R to S, we do, again, head minus tail. So you do y1 plus a1, and you subtract off x1 plus a1, and then you do that for the second coordinate and the third coordinate, and so way down, all the way down to the last one, yn plus an minus xn plus an. And then, of course, if you push that minus sign through, this is going to give you minus x1 minus a1. So these guys, those are going to cancel. They're going to cancel. They cancel all the way along, and you end up with simply y1 minus x1 all the way down to yn minus xn, and that's the vector pq, right? So if you translate the vector, if you make the same change to the tail that you make to the tip, you're not actually affecting the vector. You're not affecting these numbers that give us the information about the vector. So we don't care about location. We only care about the length of the vector and the direction of the vector. Okay. All right. Now, because you can draw a vector anywhere you want, one of the most convenient places to draw that vector is you put the tail at the origin, and you get this notion of a position vector. So if you think of kind of a three-dimensional picture, the origin being here, 0, 0, 0. If I have any other point in space, I have a point, say, x, y, z, sitting there in space, then I can draw the vector from the origin to that point. And so this would be, so if this is the point P, and the origin, we often just refer to the origin as O. So this vector V here, right? So V is going to be this vector from the origin to P. And so, of course, I'm going to get x minus 0, y minus 0, z minus 0. We don't bother to write the minus zeros. We simply get x, y, z. Okay. So, the vector V, it contains exactly the same information as the point P. It contains these three numbers, these three coordinates, x, y, z, telling us where we are in space, right? There's a bit of a kind of a change in perspective here. Rather than thinking about a point, we're thinking about an arrow that's kind of directing us to that point. And we'll see that there's also a major practical difference. When we get to the next video, we'll see that the practical difference here is going to be that although it doesn't really seem to make any sense to add points, if you kind of imagine you have 2 points in space, what does it mean to add them together? That doesn't seem to make any sense. It does make sense to add vectors, and this is one of the big advantages of vectors, is that we can in fact add them. And that's one of the advantages of changing your perspective from simply working with points to working with vectors. And that's going to be something we discuss in the next video. Alright, so this is our last video for this week, and we're going to introduce algebra with vectors. We're just going to get started. We will continue with algebra of vectors next week, and we'll move on to the dot product and then the cross product, and then we'll be talking about lines and planes. But we'll begin with algebra of vectors. So this, again, if you're following along in the textbook, we're still in section 3.2 here in the text, and we will be for the next couple of videos. Alright, so I mentioned at the close of the last videos, we introduced the idea of a vector, and I mentioned that one of the advantages with vectors as compared to points is that you can add vectors, right? We also mentioned that when you're thinking of vectors geometrically, there are two quantities that you care about. The magnitude of a vector, which is basically the length of a vector, and then also the direction in which that vector is pointing. So we'll start by defining the magnitude, and introducing some notation, and then we're going to move on and we're going to talk about some algebra. We'll come back to magnitude later on. So first, some notation, and we've kind of been using this a little bit already, this angle bracket notation right here, right? So when we take a vector and we write it out in terms of these numbers, right? And we said, okay, if you're dealing with a vector, if your vector v is equal to, say, some vector pq, then each, if p has coordinates maybe x1 through xn and q has coordinates y1 through yn, then these numbers that you put into the vector are the differences between these coordinates, right? So you get these sorts of expressions here. Xi minus yi, or maybe yi minus xi, depending on how you're drawing things. So these numbers are called the components of a vector. For whatever reason, we choose to call them components rather than coordinates. And we've kind of already gotten this idea that these numbers tell us everything that we need to know about the vector, right? Remember that if you take the coordinates of the tail and you add the components of your vector, you get the coordinates for the tip. This is why you use this tip minus tail rule to construct the components of your vector. Now, if you kind of think about that, and if you think about the distance formula, right? If you draw a vector in space between 2 points, so I've got a point P and I've got a point Q sitting there somewhere in space, and I draw this vector between them. Well, then one thing you notice is that the length of v, if v is this vector, that's just the distance from P to Q, right? And we know how to calculate distance. The distance formula, this is given by, you take the difference in the first coordinates, so maybe we're doing x1 minus y1 squared and so on down to xn minus yn squared, right? The distance formula says you do the sum of squares and then you take the square roots. That's how you get the distance, right? So if this is my v1, v2, and so on down to vn, right? This kind of gives us an idea of how to calculate the length of a vector. So the way you calculate the length of a vector is you simply square each of the components, you add those up, and you take the square root. Okay. Actually, maybe before we jump onto addition, let's just do one quick example. Squeeze it in here. So if v is equal to, let's say, 1, 2, 3 in 3 dimensions, then the magnitude of v is going to be the square root of 1 squared plus 2 squared plus 3 squared. That comes out to give you the square root of 14 in this case. All right. Now, how do you add vectors? Well, you add vectors by adding their components. It's very similar to adding complex numbers. Remember that with complex numbers, you add the real parts and the imaginary parts. So you add the corresponding real and imaginary parts. And the thing is that, there's a lot of overlap here, right? If I draw my coordinate axes, right, and if I draw a point in my plane, there are a number of ways that we can describe a point in the plane, right? We can think of this as a ordered pair, xy, as a point in the plane. And again, we don't really know how to add points, but we could also think of this as a complex number, x plus iy. We do know how to add complex numbers. We could also think of it as a vector. We could think of it as the vector xy. And so if you think of a vector xy, if you think of that as kind of, corresponding to a complex number, x plus iy, then you add vectors in exactly the same way you add complex numbers. You just add the corresponding parts, right? So you add the x components, you add the y components, you put those together, and then that gives you the new vector. So if I took, say, v equal to 1, 2, I take w equal to, I don't know, minus 3 and 6, then v plus w should be 1 minus 3, right? Maybe we want to write this as 1 plus minus 3, but that's, 1 plus minus 3 is just a long way of writing 1 minus 3, and usually we skip right to the point. And then we add the y components, so 2 plus 6, right? So 1 minus 3 gives me negative 2. 2 plus 6 gives me 8. And we've calculated the sum of those two vectors. Now, one of the things that you might want to keep in mind here is that there's kind of a way to visualize things as well. We'll talk about that on the next slide. Before we jump, let's do let's do a three-dimensional example. Let's say A is equal to 1, 0, minus 3. Maybe B is equal to 2, minus 4, 6. A plus B, 1 plus 2, 0 plus minus 4, 0 minus 4, minus 3 plus 6, so we get 3 minus 4, 3 for our sum. All right, so there is a way that you can kind of visualize this thing if we draw out a pair of coordinate axes and we think about two vectors in the plane. So let's draw things out. So let's draw a couple of vectors. Let's say 1, 2, 3, 2. So let's draw this guy here. So V is going to be the vector 3, 2, and let's draw this guy here. W is going to be the vector, don't have quite enough room for it there. W will be the vector 1, 2, okay? So our rule for adding these guys says that V plus W should be 3 plus 1, 2 plus 2, should give me the vector 4, 4. So we mark off, okay, 4 units that way, 4 units that way, 1, 2, 3, 4, and we kind of, go out, and then we can draw the sum. So we draw the sum like so. V plus W. And so one of the things you can kind of do here is you can realize that you can sort of, take this picture and there's a parallelogram you can draw in. You can draw this guy here. Now notice that this is just another copy of V, right? It's got this, this is a parallelogram. So the direction, the magnitude are the same. And remember that location doesn't matter. So both of those are copies of V. And then of course we could also do the same thing with W. We could draw a copy of W there. We could put W in either spot. So this rule for adding vectors is sometimes called the parallelogram rule or the tip-to-tail rule. The idea is tip-to-tail meaning that you would take, say, the tail of W right here and you attach it to the tip of V, and then you kind of follow along V and then along W, and where you end up with, that should be the sum. One of the things that you might notice from doing this, and of course we'll see that this is a general rule, is that V plus W, it's the same thing as doing W plus V. And you can kind of see that geometrically here in this sense that you could follow either the bottom of the parallelogram or you could take the top of the parallelogram. Along the bottom you're doing V plus W, along the top you're doing W plus V. And if you think of it in terms of giving directions, right, a vector is telling you how to get from one point to another. Is basically saying, so first you follow the vector V, you get to the end of V, and then you do W. So V plus W is what you do if you kind of follow one set of directions and then the other. And it turns out that you can do that in either order, and you'll get the same results. Okay, so frequently this picture is quite useful for adding vectors. The other operation that you can perform on vectors is scalar multiplication. So if you have a real number, so real numbers are sometimes in the context of vector algebra, they're referred to as scalars. So C here is a real number. You can multiply a vector by a real number. And the rule for multiplying a vector by a real number is you just multiply each entry in the vector by that number. So for example, if V is equal to, let's say, 3, 1, minus 2, and let's say C is equal to, I don't know, minus 4, then C times V would be minus 4 times the vector 3, 1, minus 2, and we simply multiply each thing by minus 4. So minus 4 times 3, minus 4 times 1, minus 4 times minus 2. So we get minus 12, minus 4, plus 8 for our scalar multiple. So scalar multiplication, pretty straightforward. You're just multiplying each thing by the same number. Where does this name scalar multiplication come from? The scalar. The idea is that multiplying by a scalar is somehow rescaling. So what happens when you multiply by a scalar, if you're thinking in terms of geometric vectors, in terms of direction vectors, is you're changing the magnitude of the vector without changing the direction. Well, you could change the direction. If you multiply by a negative scalar, like we've done here, we'll see that you actually end up reversing the direction. So to give you an idea of how this works, here's a two-dimensional example. So let's say that C is a scalar, V is my vector AB, right? So the picture we're working with here is sort of, this one. Here's my vector AB. Well, so let's calculate the magnitude of C times V. So that's the magnitude of C times AB. Okay, so that's the magnitude of the vector CA, CB. So remember how you calculate the magnitude of a vector. You square each of the components, you add those up, and then you take the square root. So this is the square root of CA squared plus CB squared. And okay, let's multiply things out. Laws of exponents says the square of C times A, that's C squared, A squared. This is C squared, B squared. All right. Common factor of C. Pull that guy out. C squared, A squared plus B squared. Okay. Now, all of these are positive quantities, and so we can take the square root of each one separately. So this is square root of C squared times the square root of A squared plus B squared. And now if you recall back to the first screencast, the one on Cartesian coordinates, the square root of the square of a number is simply the absolute value of that number. And of course the square root of A squared plus B squared, that's just the magnitude of V. And so you can see that by multiplying by a scalar, you multiply the length by that same scalar. And as is noted down here, if it's a positive scalar, then the absolute value of C is just C, and so multiplying, V by the scalar C is the same, telling you that the length gets multiplied by that same thing. So C times AB would look something like, maybe C is equal to 2. You get something, same direction, but different length. Something like that. And the way if you're not convinced that the direction should be the same, you can kind of play around. You can make an argument using similar triangles. You can convince yourself that yes, really the direction is the same, at least if C is positive. If C is negative, you actually reverse the direction, and you would get something pointing in that direction if C is negative. Okay. The only last thing to mention before we close here, there is one vector that doesn't have a direction, and that's the 0 vector. This guy right here, right? The 0 vector is just the vector, well, in 2 dimensions, 0, 0. Whatever dimension you're in, it's just the vector where all the coordinates are 0. There is no direction assigned to the 0 vector. It has no magnitude. If you have something with no length, it's not very useful for pointing you in a certain direction. Okay, so that's it for this week. We'll look at algebra more formally next week when we get into things. Okay, so welcome to the next in our series of screencast videos. In this video, we'll pick up where we left off in the previous one, where we've introduced vectors. So in the last video, we introduced the notion of a vector in 2 or 3 dimensions. Well, we talked a little bit about how to generalize that to n dimensions. We gave the definitions for addition and scalar multiplication. We saw if you write down a vector in terms of its components, so if I write a vector, say v equals, say, A, B, C. So those numbers A, B, C are the components of a vector and what they sort of represent. So remember that vectors are meant to encode both a magnitude and a direction. And what those numbers are telling us is basically how to get from the tail of the vector to the tip. So they say, well, if you add A to the x coordinate, you add B to the y coordinate, you add C to the z coordinate, you will travel from the tail of the vector to the tip of the vector. And so you get this geometric interpretation of the vector. So we saw last time that the way you add vectors is you add the corresponding components. You would add the x components, add the y components, add the z components. Much like when you add complex numbers, you add the corresponding real and imaginary parts. We saw how to define scalar multiplication, where you multiply each entry in the vector by some common scalar, and we saw that there's a geometric interpretation of that as well, which is, it's called a scalar because it scales the vector. If I multiply a vector by say 2, like 2 times v would be the vector 2a, 2b, 2c, and that would give me a vector which is twice as long but points in the same direction. So we're gonna look a little bit more at some of the properties that those two operations, addition and scalar multiplication, the properties that those have. But before we get to that, we're going to pause briefly to talk about unit vectors, parallel vectors and unit vectors. So first, the definition of parallel. So thinking of scalar multiplication, we have this idea that if you multiply a vector by a scalar, you're changing the magnitude but not the direction. So if one vector is a scalar multiple of another, we can say that those two vectors are parallel, that they lie along the same line. So if we have one vector A and we have another vector B, if we can find this scalar k so that I can write A as k times B, so A is a scalar multiple of B, this is a way of communicating the fact that our vectors are parallel. So for example, let's just do two-dimensional examples because that'll fit nicely on the screen. Let's say that U looks like, maybe use the vector 1, 2. So if V, let's say the vector V is maybe 2, 4. So using the rules for scalar multiplication, I can pull out a 2. I can write that as 2 times 1, 2. So that's 2 times U. Or maybe I have W. W is equal to maybe minus 3 minus 6, let's say, which is minus 3 times 1, 2. So minus 3 times U. So I can consider, so all of those vectors would be considered to be parallel. So V and W are both parallel to U because they're written as scalar multiples of U. And of course I could turn things around. I could say that the vector U, U in turn I could write as, well, 1/2 of V, or I could write it as minus 1/3 of W. So parallelism is a two-way street. If A is parallel to B, then B should be parallel to A. The only maybe exception to that rule is if you extend the definition of parallel to allow for the zero vector, right? If I took A to be the zero vector, and then I took K equal to 0, right? Then 0 is equal to 0 times any other vector. So there are weird things like that that can go on, but of course if you're thinking about parallel, you're thinking about direction, and the zero vector doesn't have a direction, so normally parallel is a term that you would consider in the context of non-zero vectors. Just to kind of give you an illustration of where things are here, let's draw the, so U being 1 unit to the right and 2 units up, the vector U, if I draw it as a position vector with its tail at the origin, there's my vector U. The vector V is, I'm multiplying by 2, so I get something in the same direction but twice as long. So there's 2u, so that would be my v, twice as long as u. W, I'm multiplying here by a negative scalar, so I'm missing an equal sign there. When you multiply by a negative scalar, you reverse the direction. So w would be a vector which is 3 times as long and pointing in the opposite direction. So I would get something pointing down here. Okay. Now, often when you're talking about parallel vectors, you're concerned with the direction. One of the constructions you often use is that of a unit vector. So a unit vector, is basically we standardize the situation to insist that we're just going to talk about vectors that have length 1, right? So if all of our vectors have magnitude 1, then magnitude is really no longer something that we think about. We only have to think about the direction, right? So a unit vector has length 1, and what's relevant about a unit vector is the direction in which it's pointing. And so if somebody hands you a vector and you care about the direction that vector is in, you may want to construct the unit vector which is in the same direction as the vector you started with. Just to give you a quick example of a unit vector, and then we'll show you how you would actually construct such a thing. If I gave you, let's say, u to be 3 over 5, 4 over 5. You can check that that is a unit vector. I'll leave that as an exercise for you to verify that that is a unit vector. Remember, just if you look up the definition of magnitude, which was done in the previous video, make sure I spell exercise right. So in the previous video, remember the definition of magnitude is along the same lines as the definition of modulus for a complex number. We should square these two components. We square 3 over 5, we square 4 over 5. If you add those two together, you'll find that you get 25 over 25. When you take the square root, you get a magnitude of 1. All right. Now, let's suppose that somebody gives you some other vector v, and you want to come up with a unit vector u. You would like u to be a unit vector which is parallel to v, so you want u to be equal to k times v, so u is parallel to v. And you would like the magnitude of u to be equal to 1. And while we're at it, we might as well say that it's not enough to just be parallel. Let's say we want them in the same direction. So we want u to be the magnitude of u to be equal to 1, and we would like k to be positive. We want k to be a positive scalar so that u and v point in the same direction. The only thing that's different is the magnitudes. So what value should we choose for k if we want the magnitude of u to be equal to 1? Well, remember that when you compute the magnitude of a scalar multiple, if I have a scalar inside the magnitude, one of the properties of magnitude with respect to scalar multiplication is that you can take this scalar and you can bring it out front. And if it's a positive scalar, you can bring it out directly. With negative scalars, you have to worry about sign changes, but with positive scalars, that k comes straight out. So we would get k times the magnitude of v, and we want that to be equal to 1, right? We want the magnitude of u to be equal to 1, and that suggests that this scalar k should be equal to 1 over the magnitude of v. And so this is how we construct our unit vector. So our unit vector u is 1 over the magnitude of v, which is a scalar, right? Remember, the magnitude is just a number, so 1 over a number is still a number. So we take this scalar and we multiply by the vector v, and that gives us our unit vector. Okay. Now, among all the unit vectors that you could consider, there are certain basic ones which come up all the time. They're important enough that they're given sort of their own special names. We'll look at what these guys look like in both 2 and 3 dimensions. So in 2 dimensions, let's draw a 2-dimensional coordinate system. So there are sort of 2 fundamental directions in the Cartesian coordinate plane, right? The x direction and the y direction. These are sort of the most important directions, and in particular the positive x and positive y directions are the ones that we're interested in. So there's sort of two standard vectors that you could draw. You could draw this vector parallel to the x-axis. You could draw this vector parallel to the y-axis. And so these guys have names. We call these usually I and j. And of course, if we want these to be unit vectors, we want them to have length 1. Well, then we should go out 1 unit in the x direction, would take me to the point 1, 0. If I go up 1 unit in the y direction, that would take me to the point 0, 1. And I've drawn both of these vectors with their tails at the origin, and so that tells me that I should be writing I as the vector 1, 0. I should be writing j as the vector 0, 1. Now, what's really useful about these vectors, aside from kind of keeping track of these kind of x and y directions, these fundamental directions that we deal with all the time, what's really useful is if you kind of play around with the properties of vector addition and scalar multiplication. Let's say you take any other vector in R2. So I take a vector AB. Well, one of the things I could do is I can take this vector and I could split it into two pieces. One piece which is entirely in the x direction, and one piece which is entirely in the y direction. So if I had, let's kind of draw things in. If this was my vector AB, right, then this is the usual story that I kind of drop a perpendicular down and I would get this vector here. That would be my vector A0, and then this guy coming up, that would be the vector 0b. So I can split those guys up, but then the other thing I can do is I can take out these scalars. I could bring the a out front, a times 1, 0, and b times 0, 1. Right, because a times 1 would give me a times 0 gives me 0, so if I work back in the other direction, it's clear that these guys are equal. And so then what I get is that any vector in this of the form a comma b can also be written as ai plus bj. So you can write any vector in terms of these I and j unit vectors. You'll find frequently in engineering and physics that in many cases this is the preferred notation, this ij notation, rather than writing things down in terms of these angle bracket notation. Now, in 3 dimensions, you can play the same game. Of course, this time we have 3 vectors. So you have a vector I pointing along the x-axis. You have a vector j pointing along the y-axis. And, well, next letter in the alphabet is k, so we draw a vector k pointing up along the z-axis. And you can guess that just as in 2 dimensions, if you want these guys to be unit vectors, you want them to have length 1, then you don't have much choice. If you want something that's length 1 and it points along the x-axis, it's got to be of the form 1, 0, 0. J is going to have to be of the form 0, 1, 0. K is going to have to be of the form 0, 0, 1. Right? So it's clear that these vectors all have length 1 and that they point in the directions you want. And just as in 2 dimensions, and I'm not going to go through all the steps, but you can check that it's likewise true in R3, that if I had a general 3-dimensional vector ABC, I can write that as a I plus b j plus c k. Okay. So expressions like this guy on the left, by the way, these sorts of expressions, these are sometimes known as linear combinations. That's something we'll be talking about again later in the course. So the linear combination is sort of the fundamental object in linear algebra. It's sort of, something that you can build out of other vectors using the 2 operations of addition and scalar multiplication. And one of the things that you're often concerned about in linear algebra is whether or not a given vector can be written as a linear combination of some other vectors. And if you're in a situation where you have a set of vectors such that you can always do this uniquely. You're always guaranteed that you can find, these numbers A, B, and C, so that you can write the left-hand side in terms of the right-hand side. A collection of vectors like this is called a basis, and this is a very sort of important idea in linear algebra, and it's one that we will touch on briefly in this course. All right, before we jump ahead, the only other thing to mention, you do take a bit of care about context, because you'll notice that we use I and j in both 2 and 3 dimensions. The vector I in R2 is not the same thing as the vector I in R3. You can see they're different objects, right? One of them has 2 components, the other one has 3 components. But usually in the context, you'll be able to tell between the two, because you'll know what dimension you're working in, and so there's usually not too much risk of confusion. Okay. Here are 8 properties that you can verify for yourself. We're not going to do them here. I don't want to make this video drag on. It would be far too long if we tried to go through some of these properties. But if you take the addition and the scalar multiplication that we've defined for vectors in Rn, right? This could be R2, this could be R3, it could be R4. It doesn't matter. These 8 properties are satisfied by vectors in Rn for any n. Okay, so the order, so 1 tells me that the order of addition doesn't matter. 2 tells me that if I need to add 3 or more vectors, I can group them however I want. Placement of brackets doesn't matter. There is a 0 element, right? The 0 vector with all components equal to 0. If I add that to any other vector, nothing happens. There is an additive inverse, right? If I change the sign of each one of the components, adding that to the original vector, those two are going to combine to give me 0. Right? So those 4 properties, of course, those are properties that we already saw were true for addition with real numbers, for addition with complex numbers, and the reason that they're true here is that addition of vectors is defined in terms of addition of real numbers, right? Because you just add the corresponding components. And so the reason why x plus y is equal to y plus x here is because that's true for real numbers. The final 4 properties, 5, 6, 7, 8, have to do with scalar multiplication. 5 is just the observation that multiplying by the scalar 1 does nothing. 6 says that the multiplication, the scalar multiplication, is compatible with the usual real number multiplication. If you did a sequence of scalar multiplications, that's the same thing as, so if I did multiply by d and then I multiplied by c, that's the same thing as if I first multiplied the scalars together and then did one scalar multiplication. 7 and 8, these two together, these guys are both distributive properties. And you'll notice that there are 2 of them. And the reason there are 2 of them is because you've got 2 different types of addition. The first distributive property has to do with addition. On the left-hand side, that addition is in Rn. It's an addition of vectors. And then in property 8, that addition on the left, that's addition in the real numbers, or you're adding 2 numbers together and then doing the scalar multiplication. So there's 2 different distributive properties because there's 2 different types of addition that might come up. And as usual, these properties are going to drive a lot of equation solving. If you're trying to do vector equations, these sorts of things might come up. So you'll encounter these properties as we kind of go through some examples where we try to solve equations involving vectors. And of course, just even in simplifying expressions, things like, so property 8 would tell you, for example, that, if I was doing 2x plus 3x, that, well, 2 plus 3 is 5, so, I kind of have the left-hand side here. C is equal to 2, D is equal to 3. I can add those together and get 5x, and I know that this sort of operation is justified. All right, so that's all we'll do in this video for vector algebra. We'll be doing some examples in class with numbers. We'll show you how all of these operations work and how they all fit together. We'll do plenty of computational examples in the classroom. All right, so next up we're going to move on to section 3.3 and the dot product. So the dot product is a construction that can be made in Rn for any n. We're going to, of course, look at it mostly in 2 and 3 dimensions, but this is something that can be done in any dimension. And One thing that we'll kind of maybe emphasize before we do anything, one thing to kind of note is that the dot product is a number. Okay, so I'm going to tell you how this number is defined in a second, but I just want to emphasize this because one of the very common errors that people will make is they will assign some sort of vector quantity to a dot product. So a dot product is always a number. So the dot product is going to be something that you take two vectors as inputs and you get a number as an output. So let's see how that number is defined. So the dot product, it's also sometimes called the scalar product to emphasize the fact that the output is a number. The algebraic definition is this one here. So if I have two vectors, u, right, written in terms of its components, u1 up to un, v, written in terms of its components, v1 up to vn, the dot product of those two vectors is obtained by multiplying together the corresponding components. So I do u1 times v1 here, then I do u2 times v2 here, and so on until I run out of components. So I do this for each pair of components, right? And one of the mistakes that people will make is they'll take those products, u1, v1, u2, v2, and they'll write those as the components of some new vector. That's not something we're interested in. It's true that you can always form a new vector by just multiplying together the corresponding components. And that gives you some sort of vector product. The problem is it turns out that that is not very interesting or useful. So that sort of product, it just doesn't, it doesn't have a lot of useful properties. It doesn't have any applications. The dot product, on the other hand, we'll see that it's quite useful. So the important part here is that once you've calculated those products, you add them up, right? So you do u1 times v1 plus u2 times v2 plus u3 times v3 and so on. You add them all up. And so once you've added those numbers up, then what you're left with is just a single number. If you're comfortable with summation notation, then there's a short form here on the right-hand side. If you haven't really worked with summation notation, don't worry about it. You're not going to be expected to use it in this course. There is another way that you can define the dot product. If you think of two vectors geometrically, so you think of them as arrows, so things with magnitude and direction, u and v. So I can rotate my point of view until I'm sort of sitting in a plane which contains those two vectors, and I can kind of think of those guys as vectors in a plane. And if I think of them as vectors in a plane, then I can measure this angle between them. I can measure this angle theta right here. And we generally take theta to be sort of something, which is between 0 and pi, just to kind of resolve some ambiguity, because we don't want to kind of go the other way around. You can go the other way around. The cosine function sort of takes care of this anyway, but we'll generally measure the angle like that. And so you can measure the cosine of that angle between u and v, and we don't worry too much about, I should add, we don't worry too much about the direction of the angle here. The distinction is going to be between acute and obtuse angles. For something like this where you have an acute angle, we would want cos theta to be bigger than 0. If you were dealing with a situation where they were making some sort of obtuse angle, like so, then you would measure the angle this way, and cos theta would be less than 0. So there is the possibility that this dot product could be either positive or negative, depending on whether the angle is acute or obtuse. Okay, so the geometric formula says that you should calculate the length of v, then you should calculate the length of u, calculate the length of the two vectors, calculate the angle between them, measure the angle between them somehow, and then you can multiply these three together to give you the dot product. Of course, measuring an angle is not exactly something that's practical. You're not going to, probably be pulling out your protractor or anything like that. So what the way that this second definition is usually more useful is that, well, the first definition, this algebraic definition, is simple to calculate if you know the components. And so one thing this lets us do is, at least if our vectors are both non-zero, it means that it gives us a way of measuring the angle between vectors. because I can calculate the dot product. That's something that's easy to compute. I can calculate those two magnitudes. Those are easy to compute. And suddenly I have a way of calculating the angle between two vectors. And so this is one of the things that's sort of fundamental with the dot product, is the dot product actually, in one point of view, the dot product actually defines angles between vectors. So the dot product is encoding some of this geometry. Some of the directions are kind of built into this dot product, right? It's telling us how to measure angles, and to some extent it's also telling us how to measure length, because one of the things you might notice is that if you set u equal to v in this definition, you'd have u1 squared plus u2 squared plus up to un squared. So if you take the dot product of a vector with itself, what you get is the square of the magnitude, right? Cos theta, theta would be equal to 0 in that case. Cos theta would be equal to 1. And so there's information about the magnitude contained in the dot product. There's information about directions, about angles contained in the dot product. So the dot product encodes a lot of our geometry. Okay, so just to do a couple of quick examples here, we'll do one two-dimensional example, we'll do a three-dimensional example. Let's do a two-dimensional example first. So in R2, maybe we take u equal to 3 minus 8. I'll take v to be the vector 2 minus 1. And so the dot product u dot v is simply, so we just multiply the corresponding components. So the 3 multiplies by the 2, and then we add, so minus 8 times minus 1, right? So we multiply the corresponding components and then we add. So 3 times 2 gives me 6, minus 8 times minus 1 is 8, and now I add them together and I get 14. Okay? And if I wanted to, I could also calculate the angle between these guys. I could compute that the magnitude of u is equal to the square root, so 3 squared plus 8 squared, so that's 64 plus 9. Well, okay, this is not going to be one that's easy to look up on the unit circle, but I suppose we could punch it into our calculator. 2 squared plus 1 squared, root 5. So if I wanted the angle between these two vectors, I guess we could say that the angle is 14 over root 73 times root 5. Something in principle, you could use that to compute the value of theta. We're not going to bother to do it, obviously. In 3 dimensions, we can similarly do this sort of calculation. Let's say u is 3 minus 1, 5. V is maybe minus 2, 3, and 1. And if I calculate u dot v, I would get 3 times minus 2 plus minus 1 times 3 plus 5 times 1, right? So 3 times minus, here's my 3, here's my minus 2, those are the x components. Minus 1 times 3, those are the y components. 5 times 1, those are the z components. So I get minus 6 minus 3 plus 5. That comes out to be negative 4 in this case. Okay. So one of the things that you'd want to make sure, since we have 2 definitions of the dot product, you want to make sure that these things actually come out to give you the same number. Right? I gave you 2 definitions. How do you know that I'm telling you the truth, that these are both equally valid definitions of the dot product? Well, you actually just go ahead and you check and you make sure that it works. So the way you do this, because you're dealing with just 2 vectors, you can assume that you're working in a plane, in a 2-dimensional plane. And so what you do is you draw things out like this. Here's my vector u. Okay. Here's my vector v. And of course, I mean, a proof is, a picture is not a proof, but we'll see that you can use this picture to set up some algebra that works no matter how I actually choose to draw the picture. So what I'm going to do is I'm going to draw one more vector in here. I'm going to draw in, this vector here from the tip of V to the tip of U. And what this vector is actually the difference. So if you've been practicing with your vector addition and subtraction by now and some of the geometric pictures, you've probably come across this, right? And so why is that red vector equal to U minus V? Well, notice that if I kind of add tip to tail, if I do this vector V and I add that to U minus V, well, V plus U minus V. Remember that vector addition is commutative and associative. I can change the order, I can move brackets. I can write that as U plus V minus V. V minus V, of course, is 0, so this is U plus 0. I get U, right? And so that makes sense. If I do V plus U minus V, that's the same thing as doing U. So that works out. So that's the vector U minus V. And I've got this angle theta sitting over here. So what I do is I say, okay, if I let A equal to the magnitude of U, and I let B equal to the magnitude of V, and I let C equal to the magnitude of U minus V, then the law of cosines says, well, the magnitude of U minus V, so U minus V, that's the side which is opposite this angle theta, that's your C, right? So the law of cosines says that C squared equals A squared plus B squared minus AB cos theta, and what you do is you plug things in, and the part you kind of have to notice, and we'll mention this on one of the next slides, you've got to play around with some of the properties. So C squared, that's the magnitude of U minus V squared, and the key to making this whole thing work is to realize that, well, as we mentioned on the previous slide, or maybe 2 slides ago, right, the dot product of a vector with itself, that's just the magnitude squared. So if I have the magnitude squared for U minus V, this is like U minus V dotted with U minus V. And we'll see that if you work through the algebraic definition of the cross product and you work through the properties that cross product satisfies, you can expand this thing out, and it turns out that what you get here is you get U dot U plus V dot V minus 2U dot V, right? And so then this guy here is going to be A squared. This guy here is going to be B squared, right? And then you kind of you plug all this into the law of cosines. The A squareds cancel, the B squareds cancel, and you're left with that 2U dot V. And actually, I've got to make a correction here. I'm missing 2 in my law of cosines. A squared plus B squared minus 2AB cos theta. This is the correct law of cosines. And you plug things in, and once you cancel, you're just left with 2U dot V is equal to, or minus 2U dot V equals minus 2AB cos theta. You cancel the minus 2's, and you're left with the result. Okay. So, in that kind of argument in favor of the 2 definitions being equal, I mentioned that there are certain properties that the dot product satisfies, and here are some of them. Maybe let's put some brackets in here, just kind of clarify things. So the order doesn't matter for the dot product. U dot V is the same thing as V dot, U. There we go. And the dot product is linear in the sense that you can distribute it over sums, right? So this, there's actually 2 kind of things here. One is that U dotted with V plus W is U dot V plus U dot W, so there's a distributive property, but also that if you have a constant inside, so if I have, like, say, A times V, you can pull that constant out. You can write that as A times U dot V. So you can pull scalars out. All right. The 4th property we've already mentioned, and this follows directly from the from the definition. And also because, u dot u, it's the magnitude squared. We know it's given by a sum of squares, and we know a sum of squares can never be negative. And we know also that the only way you can get that sum of squares to come out to give you 0 is if each one of the terms is equal to 0. So the only way that the dot product of a vector with itself can be 0 is if the vector itself is equal to 0. The last property, we won't worry too much about that, but one of the ways to kind of think about this is simply the fact that the absolute value of the cosine function is always less than or equal to 1. This is what you use to establish that fact. Okay, so these are all useful properties of the dot product. The other one that I should probably keep in mind is the following. Using the fact that u dot v is equal to the length of u times the length of v times cos theta, this tells you that if u dot v is equal to 0. So suppose you got the dot product of two vectors equal to 0, and let's assume that the vectors themselves are non-zero. So this is not 0, and this is not 0. I mean that's one way that you could get a 0 dot product, right? If either one of the two vectors is 0, the dot product is automatically 0. But if those guys are non-zero and the dot product comes out to be 0, then what this would tell us is that the angle must be, well, cos theta must be 0, and that means that the angle must be a right angle. Theta must be equal to pi over 2. So we'll see in the next couple of videos that this is kind of the crucial property of the dot product. This tells us that the dot product lets us know when vectors meet at right angles. So if I have a vector u and a vector v, and they meet at a right angle, that's going to tell me that the dot product is equal to 0. And conversely, if the dot product is 0, well, either one of the vectors is 0 or they have to meet at a right angle. And so it's often important to know when two vectors are perpendicular in this sense. And so that's going to come up in a later video. Okay, so in the last screencast video on the dot product, we mentioned at the very end that the dot product, it gives us a way of measuring angles between vectors, and in particular, it gives us an easy way of telling whether two vectors meet at right angles, because if two vectors meet at a right angle, then cosine of that angle is equal to 0, and so if the dot product comes out to be 0, well, either one of the two vectors themselves is equal to 0, or the angle between them has to be a right angle, has to be equal to pi by 2, has to be equal to 90 degrees. So we're going to explore some of those geometric implications in this video, and we're going to move on. We've got a couple of videos here to come, and then we'll see kind of how this thing works out. Oops, that arrow is pointing the wrong way. Let's fix that. Okay, so let's say I've got two vectors, v and w. So remember, there's an algebraic definition of the dot product. You just simply multiply the corresponding components, v1 times w1, v2 times w2, all the way down to vn times wn, whatever, you might just have those first two terms if you're in R2. Maybe you've got one more if you're in R3. It's possible you might be in higher dimensions, and then of course if you want to, you can extend this definition. So we also showed that the dot product could be written in terms of magnitude and direction, right? So somehow these geometric quantities that we associate with vectors, they're encoded within the dot product, because if you kind of view your vectors as arrows, if I have v and I have w, oops, let's put our little hats on those guys, then I can I can determine the plane containing those two vectors, and then within that plane I can measure this angle theta. And so one of the ways I could compute the dot product is by measuring the lengths of the two vectors and then measuring the angle between them and computing using this formula here. Except of course it's usually not actually practical to go out, with a ruler and a protractor or something like this and measure your vectors. What you're usually given is you're given the components, right? You're given the v1, v2, v3, and so on. And so the algebraic definition is generally the more practical definition. It's the one that we're going to work with most of the time. And again, just to remind you, the dot product is always a real number. The dot product is not a vector, it's a number. Make sure that you keep that in mind as we go forward. Okay, so one of the properties that you can show holds for the dot product. While using the dot product, you can show that this result called the triangle inequality holds for magnitudes. Right? So the Cauchy-Schwarz inequality says that for any vectors u and v, the absolute value of the dot product. Remember, the dot product is a number. It might be either positive or negative. We take the absolute value to guarantee that this thing comes out to be positive. It's never larger than the product of the two magnitudes, right? This is what Cauchy-Schwarz says. This is Cauchy-Schwarz right here, right? And this, we can see it from this geometric definition, because remember that cos theta is always between -1 and +1, and so the absolute value of cos theta is always between 0 and +1, and that's essentially the Cauchy-Schwarz inequality. So using the Cauchy-Schwarz inequality, you can prove the triangle inequality, which is really only a relationship among magnitudes. Note in particular the less than or equal to sign. Okay, so be careful. Magnitude is not distributive. The magnitude of a sum is not equal to the sum of the magnitudes. And the way you can see this is, if you think about adding your vectors tip to tail, and in fact this is where the name triangle inequality comes from. Okay, if I draw my vector u, and I draw a vector v, then of course the vector u plus v, their sum, if we add them tip to tail, is sitting there. And so the triangle inequality is simply a manifestation of the fact that the sum of the lengths of any two sides of a triangle always has to be bigger than the length of the remaining side, right? So the length of the side corresponding to u plus the length of the side corresponding to v, that has to be bigger than the length of the remaining side. If it wasn't, then you wouldn't be able to join up your triangle. You wouldn't have a triangle. You'd have 3 line segments that kind of have a hole in them somewhere. So this is not something that we really need in this course, but it's worth mentioning if you are taking calculus courses. If you're going on through calculus, the triangle inequality becomes important there. A lot of results in calculus, if you're trying to actually carefully prove them, a lot of results in calculus rest on this triangle inequality. It's something that comes up all the time. But this is probably the last time we'll have to mention it in this course. Okay. So as we mentioned in the last video, using the dot product you can measure angles, because you can take this equation here and you can simply solve for cos theta, and this gives you a formula for the angle between two vectors. Of course, for this definition to make sense, u and v have to both be non-zero vectors, otherwise the magnitude would be 0 and you would be dividing by 0, and then of course that's always a terrible thing to do. So we don't want to divide by 0. And one of the things to notice here is that for non-zero vectors, and so this is if cos theta equals 0, of course the other way that the dot product could be 0 is if u is 0, or if v is 0. But if we insist that we're dealing with two non-zero vectors, then the only way that the dot product can be equal to 0 is if you have two vectors which meet at a right angle. So the name for vectors that satisfy this property that the dot product vanishes is orthogonal. So this word orthogonal here does kind of include the possibility that one of the two vectors could be equal to 0, but the situation, of course, that we really care about is the case where both of them are non-zero and they happen to meet at right angles. So, for example, let's say u is equal to 2, 3, v is equal to 3, and negative 2. Okay, if I calculate the dot product u dot v, I get 2 times 3 plus 3 times minus 2. Well, that's 6 minus 6. That comes out to be 0. So these are indeed vectors that are orthogonal according to this definition. If we were to plot these guys, u would be here. That's a pretty bad arrow. V would be down here, and the angle between them is indeed a right angle. Okay. So just as one more example, let's say we wanted to compute the angle between these two vectors, just to give us some more practice with computing dot products, computing magnitudes. We calculate the dot product. Let's do the dot product first. U dot v. So we multiply the x components, 2 times minus 1. We multiply the y components, minus 3 times 4. We multiply the z components, 1 times minus 2. So that's minus 2 minus 12 minus 2. We get negative 16 for the dot product. The magnitude of u, we get the square root of 2 squared plus 3 squared plus 1 squared. That's the square root of 14. The magnitude of v, we get the square root of 1 squared plus 4 squared plus 2 squared. Notice I'm not bothering to write down the minus signs because, of course, when we square these numbers, if there was a minus sign in front of them, when you square it, that minus sign goes away. So I'm being a little bit, I don't know, call it lazy, efficient, however you want to put it. I'm skipping the minus signs. Okay, so 1 squared plus 4 squared plus 2 squared, that adds up to give us 21, so we've got the square root of 21. So then, if we wanted to know what is the cosine of the angle between them, we'd say, well, cos theta is equal to minus 16 over root 14 times root 21. And you could leave it like that. You know, if you want to be really keen, you might notice that 14 and 21 are both multiples of 7. So there's a root 7 here, there's a root 7 there. So there's a 7 you could pull out if you really want to, but we can just leave it like that. One thing to notice is that in this case, the cos theta comes out to be less than 0. Anytime the dot product is less than 0, one of the things that tells you is that the angle between the two vectors is an acute angle. So they, if we were drawing them, we would have something that looks like this. Okay, so we'll stop here for this video, and in the next one we're going to start mining this definition of orthogonality, and we're going to see that there are a lot of things you can actually do with orthogonality. So that's where we're going next. Okay, so next up we're going to finish off section 3.3 on the dot product with probably one of the more important examples, one of the more important applications of the dot product, which is to construct orthogonal decomposition. So what we want to do with the dot product, we want to use the fact that the dot product allows us to measure whether or not two vectors are orthogonal. But one of the things you can do with this is you can actually use the dot product to take a vector and break it up into pieces that are parallel and perpendicular with respect to some direction that you're interested in. So the first ingredient here is this notion of a component. And so one of the things you're measuring with a dot product is you're measuring sort of, you know, how much of a certain vector lies in the direction of another vector. So what do we mean by this? What we mean is you have some direction that you're interested in. So there's some, you know, direction here, and we're like, okay, here's a direction, and to fix that direction we choose a vector u. Okay. Frequently we might choose u to be a unit vector, so we don't have to worry about the magnitude of u in this definition here. You know, if u is a unit vector, then we have a 1 in the denominator, and then we're simply computing the dot product. So if u is a unit vector, it's quite a convenient thing. But if we have some other vector, let's say v is here, right? what we often want to do is we want to kind of think about, well, what is the sort of shadow of V on that line? If I kind of imagine that, I've got a light up here and it's shining down, I drop this kind of shadow from the tip of V onto the line. Okay, so that is going to meet at a right angle. And I want to know, how long is this piece here? So this piece from here to here, the length of this piece, this distance is the component. Okay, so the component of V in the direction of U, it's exactly this measure. The measure of kind of how much of V is pointing in the same direction as U. And if you studied any sort of basic physics, you've probably encountered these sorts of problems. You're dealing with things like one of these classic problems, like you've got like a box sliding down an inclined plane, this kind of thing, right? There's an angle here that you have, and you know that the force of gravity is pointing down like this. Here's the force of gravity. It's a vector, and it's pointing straight down towards the center of the Earth. And you want to know, okay, how much of this force is actually pointing, down the inclined plane, and how much of it is pointing, this way. So you want to split things up into these components so you can get an idea of how fast your box is going to slide down the plane, ignoring friction, of course. So that's where these sorts of constructions are going to come up. Now, the component, notice that the component, this component is sometimes called the scalar projection because it's a number. All right. We won't actually work that much with the component. Some of you might find it's convenient to work with the component, but you can get by actually pretty far without working with components. What we'll be more interested in is the projection, and the projection is going to be sort of the vector version of the component. So, we've kind of drawn this line segment in black here, this guy here, and of course you can measure the length of that line segment. That's essentially what the component is. But you may also be interested in not just the line segment, but in fact this vector, right? So you might want that vector. And so that vector corresponding to the component is what's called the projection. Okay. So there's a pretty scary looking formula here. I mean, okay, it's not that scary. You'll get used to it, all right? So you'll see people write this in a few different ways. One way you might see this written as, U dot V over U dot U times U. You might see it written like that, okay? Remember that the magnitude of U squared is equal to the dot product of U with itself. So, as I mentioned, the magnitude of the projection should just be the component, right? So the component measures the size of this piece of the vector, which is parallel to the direction you're interested in. And then if we, if we kind of go back here, if we take a vector whose length is given by this black piece, and we want it to point in the direction of this vector U, well, we can always just take this particular scalar, multiply by the unit vector in the direction of U, and that would give me a vector of the appropriate length in the appropriate direction. And so that's what you see here. Okay, and so basically what you do is you take the component. So remember, the component is given by U dot V over the magnitude of U. There's the component, and then you're multiplying by the unit vector, which is 1 over the magnitude of U times U, and that's why you see the magnitude squared here in the denominator, because there's 1 here and there's 1 there. All right. So it is a curious looking formula. It seems like maybe it's more complicated than it should be. It's one of these ones that with a bit of practice you get used to. Notice that U shows up, in this definition here. You've got 4 U's and 1 V, and you always got to kind of always try to remember, okay, which one is U, which one is V, which one am I projecting which one am I being projected onto. The setup here is that u is the vector which is defining your direction. V is the vector that you want to project. So V is this guy here. Right? And you're dropping a perpendicular from the tip of U down. So you're dropping this line as perpendicular to the direction through U, and you're figuring out where these two dotted lines meet. You're figuring out this point here, and the projection is the vector that has the tail in common with the two you've already drawn, but the tip lands at this meeting point between the two lines, right? So, so the component, remember the component is a scalar, so you're taking this vector u and you're rescaling it to get the correct length, right? So this guy here, remember, that's a scalar. It's a number. It's a one dot product divided by another dot product, number divided by a number. So this vector in green, that's the projection of v onto u, right? The reason you see so many u's in that definition is you want the vector u, you only want the vector u to contribute a direction. You don't want the magnitude of u to have any influence on this vector. The length of the vector is determined entirely by the vector v and by the angle between those vectors. Okay. So the reason those u's are in the denominators is to cancel out the magnitude contributions in the numerators and make sure that the length of u doesn't actually have any impact on this guy. Okay. By the way, one thing to be careful about, there's nothing you can cancel here. I know you see u's on the top, u's on the bottom. You're like, yeah, let's start canceling some u. You can't cancel any of these u's. They don't cancel out, okay? Because these ones are stuck inside of a dot product, right? U dot u is a number. U dot v is a number, right? You've already computed that number. Those vectors are committed to the dot products. You've just got this one vector on the outside contributing your direction for you. Okay. So the important thing about the projection is actually two things. One of the things you'll notice is that the length of this projection is chosen very carefully. The length is chosen so that this remaining piece here is always going to be perpendicular. It's always going to be orthogonal to the vector u, right? This is always going to be a right angle. This is how the projection is being chosen. You're trying to take the vector v, you're trying to split it into two pieces. One piece that's parallel to u and one piece that is perpendicular to u. And this is exactly what the projection accomplishes. So here's the theorem telling you that this works, okay? So u is any non-zero vector, and we want to take another vector v, we want to project onto it. And so the claim is that you can always construct these parallel and perpendicular vectors, okay? And so how do you get the parallel vector? Well, the parallel vector is just the projection. Okay, so v parallel is the projection of v onto u. And because remember that this is given, there's a formula here, u dot v over u dot u times u, right? And this whole thing here is a scalar, right? So the projection is a scalar multiple of u, so it is parallel to u. Okay, so we've got that much down, right? So let's redraw this picture. We're going to draw this picture over and over and over again because it's this fundamental picture. Here's our vector u providing us with our direction, our non-zero vector u. Here's our vector v that we want to project. And so we drop this perpendicular down, right? And that gives us the projection. So the projection is here. So this guy in green, that's my v parallel. Now, what about the perpendicular part? Well, the perpendicular part should be this guy here, okay? And how do you define that guy? Well, the trick to defining that guy is I'm going to skip 2 for a second. I'm going to skip the second property and jump right to 3. So 3 says that these two vectors should add up to give me my original vector v. Well, we can see that in the diagram, but one of the things that this tells me is that this guy should just be v minus v parallel. Okay. Now, there's one thing left to check. I got to make sure that this definition of V perpendicular, is it actually orthogonal to U? So how do we check that two vectors are orthogonal? Orthogonality corresponds to the dot product being equal to 0. So we've got to take the dot product of this guy with U. We've got to calculate U dot V perpendicular. And we better make sure that this thing comes out to give me 0. So let's see. Does it give me 0? It's U dot with, okay, so it's V minus V parallel. What's V parallel? V parallel is the projection. U dot, V over U dot U times U. Okay. But now, remember our properties of the dot product from our previous video. The dot product is distributive, so I can push this dot product through the brackets, and I can write this as U dot V. And remember that this guy here, we've pointed it up above, but this guy is a scalar. I can bring scalars out of the dot product, so I can write this as U dot V over U dot U, because that's just a number, times, and now that dot product, it makes its way over to this guy. So I've got U dot U. All right. Well, now we're in business because U dot U, remember U dot U is a number. It's the magnitude of U. And we see that we've got one upstairs, we've got one downstairs. This guy, they cancel. What does that leave me with? That leaves me with U dot V minus U dot V. That leaves me with 0. Okay. So this construction, it really does the job that I want it to do. Okay, it lets me split this thing up. And we're going to see, as we move on in the chapter, when we talk about lines and planes, there are going to be a number of shortest distance problems we want to do, where this is the essential construction. This orthogonal decomposition is going to let us measure distances between various objects in three-dimensional space. All right, just one example to finish off. Let's actually compute some of these guys to make sure that we know how these things work, okay? So the component of U in the direction of V, let's do this one up here. Component of V in the direction of U. So remember, this is simply U dot V over the magnitude of U, okay? So what's the dot product? Let's just quickly do that up here. U dot V is 1 times 3 minus 2 times 4 plus 2 times minus 1. So that's 3 minus 8 minus 2. Okay, that's minus 7. So I get minus 7 over the magnitude of U. What's the magnitude of U? The magnitude of U is going to be, so this guy here is what? 1 squared plus 2 squared plus 2 squared, okay? 1 plus 4 plus 4, that's 9 under the square root. Square root of 9 gives me 3. So the component is minus 7 over 3. The projection of V onto U, remember, is U dot V over U dot U times U. Okay, so U dot V we calculated, that's minus 7. It's a number. U dot U, well, that's the magnitude squared, so 3 squared is 9. And we've got our 1 minus 2, 2. You can leave it like that if you want, or if you prefer, push the scalar through. Minus 7 over 9, 14 over 9 minus 14 over 9 gives me the projection. Okay, and remember that the projection is V parallel. So we've got our parallel part. What about the perpendicular part? Well, the perpendicular part is V minus the parallel part, so it's V minus the projection. So it's going to be 3, 4, minus 1. Subtract minus 7 over 9, 14 over 9, minus 14 over 9 comes out to be, so 3 is 27 over 9, minus gives me plus, I'm adding 7 more, 27 plus 7, 34 over 9, 4 is 36 over 9, 36 minus 14, 22, minus 1, that's minus 9 over 9, minus 9 plus 14 leaves me with 5 over 9. Okay, that should be the perpendicular part. Let me write this, let me simplify this. This is equal to 1 over 9 times 34, 22, 5. And let's see if we did our job correctly. Let's check. U dotted with V perp. What does this dot product come out to be? So let me pull the, so this is going to be 1 minus 2, 2, dotted with 1 over 9 times 34, 22, 5. Let's bring the 1 over 9 out front. What are we left with? 1 times 34 minus 2 times 22, 34 minus 44. 2 times 5 is 10, and that does indeed come out to be 0. So everything works the way we expected it to. Okay, so in this next screencast video for Math 1410, we're going to introduce the cross product. So this is from section 3.4 in the textbook. This will be the first of 2 videos going over material on the cross product. So we'll see next week that the cross product is going to be necessary for coming up with equations of planes in a lot of situations. Okay. So, what is the cross product? So the cross product is a way of combining 2 vectors to get a vector, right? So remember that the dot product, so we already defined the dot product, so the dot product gives me a number, right? So just as a reminder, let's put this down here at the bottom. The dot product, U dot V, the outcome there is a number. It's simply U1 times V1 plus U2 times V2 plus U3 times V3, right? This is a number. Okay. The cross product, on the other hand, the cross product is a vector. So it's important to keep track of the fact that one of these guys is a number, one of them is a vector, and again, notice that there is no product where we take the kind of, so in the dot product we're multiplying the corresponding components, but we don't take those as components of a new vector. We add them up to get a number, and there is no situation where we actually want to take those as components of a new vector. It could give us a new vector, but that vector is not interesting. So the way to get out a new vector from 2 vectors in 3 dimensions that is useful is using the cross product. And this formula here, it's fairly intimidating the first time you see it. And so what we're going to do is we're going to go over basically some methods for computing this thing, for remembering this formula, because it's a complicated looking formula. But it's a complicated looking formula because it does sort of a complicated job. It has sort of a sophisticated setup, right? And so the reason that you do the cross product, the job of the cross product is right here. This point here is key. Okay. This is what you need to know as far as how do you determine the direction of the cross product. The vectors u and v that you put in, right? They're going to be say here's u, okay, and here is v. All right. Now, any 2 vectors like that, as long as they're not parallel. So for parallel vectors, you just say the cross product is 0, and we can work out that the cross product of parallel vectors is 0 using this algebraic definition. It's not too hard to see that. But for non-parallel vectors, any two non-parallel vectors, they span a plane, right? So there's a plane here containing those two vectors. And you want the direction of the cross product to be perpendicular to that plane. So you want the cross product orthogonal to both of the vectors you put in. So the cross product, looks something like this. U cross v. And we'll see, I mean, you could take this if you want as a geometric definition, but we'll be able to prove that this is true, that if you construct the parallelogram spanned by those two vectors and you want to calculate the area of that parallelogram, the area of that parallelogram is equal to the magnitude of the cross product, right? So the direction is more or less determined by this requirement that it be perpendicular to the plane containing the two vectors that you put in. The way you just assign the magnitude is by this kind of area rule. And the fact that the cross product computes an area makes it useful for a lot of applications. But this orthogonality is also very important because when we get to the discussion of finding equations for planes, we're going to see that one of the things that we need what's called a normal vector. We need something which is perpendicular to the plane. And this gives me a method of constructing that normal vector. Now, remember, what does orthogonality mean in this context? The fact that it's orthogonal to both u and v. Remember that orthogonality is encoded using the dot product. So what we're saying here is that the dot product of u with the cross product is equal to 0. And the same thing is true if we take the dot product with v. Okay. So how do you actually remember this formula? It's a scary looking formula. How does this work? Well, let's see how things would work in an example. Let's say I take u is equal to -1, 4, 3. I'll take v equal to 2 minus 3. Let's go with 7. Okay. So the cross product, u cross v. So here's our formula, right? We have this formula for u2 v3 minus u3 v2 in the first entry. Then u3 v1 minus u1 v3 in the second spot. Then u1 v2 minus u2 v1 in the third spot. And so, I mean, you can kind of notice there is a pattern, that you have 2, 3, so the index on the u kind of goes up by 1, so it's 2 followed by 3, then 3 followed by 1. I mean, if you kind of think of them as being in a circle, you have 1 is followed by 2, 2 is followed by 3, and then 3 comes back to 1. And so if you sort of cycle the indices around, 2, 3, 2, 3, so we kind of do this, right? So the first one is 2, 3, and then the next one we kind of go one step along, we go 3, 1, and then the next one along we go 1, 2. So you kind of keep doing steps along the circle. So you can try to remember it that way if you want. We'll see some other methods right away, but that's one way. Some people are actually quite happy just kind of remembering this pattern and going with it. But the only problem with remembering the pattern is then you've got to do some pattern matching, right? So you've got to now kind of identify things. So u2, now we kind of go up here. So here's u1, here's u2, here's u3, right? And you start plugging things in. So u2 is 4, v3 7, u3 is 3, v2 is minus 3. Right, then u3, 3 times v1, which is 2, minus u1, minus 1, v3 is 7, and then u1 minus 1 times v2, which is minus 3, we're running short on space here, subtract u2, 4 times v1, which is 2. Okay, so let's work this out. So 4 times 7, 28, plus 9 gives me 37. 6 plus 7 gives me 13. And then this is 3 minus 8. -5 gives me the cross product. One thing you might notice is if I were to do, let's say, u dot, u dotted with u cross v. Here's one way that we can check to see, did we do things correctly? If I do -1, 4, 3 dot product with 37, 13, -5. The previous slide said this should come out to be 0. Let's see. -37, -1 times 37 gives me -37, plus 4 times 13 minus 3 times 5. So 4 times 13 is, that's going to come out to be 52, 26 plus 26. This, of course, is 15. So -37 minus 15 comes out to -52 added to 52. This does indeed give us 0 as we expected. You could check for the vector v if you want, but we'll just do the 1. Okay, so what are some other ways you can try to remember this cross product? So one way to remember, and this kind of gets us set up for things we'll do later anyway, is to remember the cross product in terms of what are called determinants. So a 2x2 determinant is basically a way to take a array of numbers, a 2x2 array, and by 2, so 2 rows and 2 columns. That's what we mean by 2x2, right? It's 2 across, it's 2 down, 2 rows, 2 columns, and you do this diagonal here. So you do A times D, and that one comes with a plus sign, and then you do B times C, and that one comes with a minus sign. So you do one diagonal minus the other diagonal. So A times D minus B times C, and that gives you the determinant. And so you can remember it this way. So the cross product is given, and remember our ijk, these are our unit vectors, so we could also think of this as, if we want to write it in angle form, u2, u3, v2, v3, u3, u1, v3, v1, u1, v1, u2, v2. You can remember it that way. There's still the matter of trying to remember which indices go where, 2, 3, 3, 1, 1, 2. So there's still some work to kind of keep track of things there. But some people find it kind of easier to remember these guys, and as far as putting things in the right places. So if we went back to our previous example, so what was our previous example? -1, 4, 3. V was 2 minus 3, 7, and you can work out that the cross product is going to be, so we do 4, 3 minus 3, 7 times I, and then we do 3, 7 minus 1, 2 times J, and then we do -1, 4, 2 minus 3 times K. Okay. And then you work out those 2x2 determinants, and you find that they come out to be the same as before. 28 plus 9, so 37I, 6 plus 7, right? Because notice you're doing minus. Remember, you've got this minus sign up here, right? So 3 times 2 is 6. 7 times -1 is -7, so 6 minus -7 gives you your 13J, and then -1 times -3 is +3. 3 subtract 4 times 2, so 3 minus 8 gives you -5K, the same as before. So you can remember it that way. And one way you can sort of think of this is, when you're doing the I component, right, you cover up the I component, so you cover up the I component here, and then you write down the 4 numbers that are left over. Okay, 4, 3 minus 3, 7. And then for the, and that works for the k component as well. If I cover up the last two entries, I'm left with the minus 1, 4, 2, minus 3, and I put those ones down. The only one that's kind of a little bit of an oddball is the one in the middle, because when you cover up j, well, then you've got the numbers on the outside, the minus 1, the 3, the 2, and the 7. And notice that the 3 and the 7 come before the minus 1 and the 2. So you kind of always, I guess the way to think about it is you cover up an entry, so you cover up one of the components, and then you work your way to the right, and then you cycle around once you reach the end. Okay. So the other way you can remember this is using a certain 3x3 array, and we'll see later on that this expansion rule for this 3x3 array, it does correspond to the expansion rule for a 3x3 determinant when we define determinants later on. But for now, we'll just kind of use this as a way of remembering the cross product. Notice, and this is again quite important, there are minus signs showing up in these 2x2 determinants, but there's also a minus sign here. Okay, so beware of that minus sign. And let me just kind of underline things here so we don't cover stuff up. That minus sign is important. If you don't like the minus sign, one of the things that you might notice is that if you take your determinant and you swap the two rows, or the two columns rather, then this would become, we again do this sort of, we do this product minus that product, so this one plus this one minus, then we have c times b, so we would have, I guess we wrote it the other way around, but let's do it this way. So this would be BC minus AD, and if I pull a negative out, that's minus AD minus BC, and that in turn is the negative of what we would get if we did A, B, C, D, right? So if you swap the columns, that amounts to a minus sign. So the other way you could write this here is you could write this as plus U3 V3 U1 V1 times J, and then that's exactly the same as the formula that we had on the previous slide. Okay, I think we left room for an example, so let's put that on the next slide. So let's say I want to do U cross, let's actually write down what these guys are. So let's say U equals 2 minus 1, 0. V is equal to 1, 3 minus 1. Then I can calculate the cross product by building this 3x3 array, I, J, K. So I write down U first, then I write down V, like so. And the way you do this expansion, so the way you think about this expansion rule here is when you want the I component, you go over here, here's the I component, you strike out the row and the column that contain that entry, and you write down the four numbers that are left over, and that's what you see here, right? And then when you get to the J, you do the same thing. You strike out the row and column containing the J, and you write down what's left over. So going back to here, we say, okay, oops, if I kind of delete the row and the column containing the I, then what I'm left with is minus 1, 0, 3, minus 1 times I. And if I delete, let's do another color here. If I delete the row and the column containing J, and I write down what's left over, and if I'm careful to remember that there's this minus sign in the middle, 2, 0, 1, minus 1 times J. And then if I do the K, so I do this row and the last column, and I write down the numbers that are left over, I've got 2 minus 1, 1, 3 times K. And so be careful, make sure you remember this, the main mistake people are going to make again is this minus sign. So the one in the middle comes with the minus sign. Otherwise, we just have to do these 2 by 2 determinants. So this one we do 1 times 1, that's 1 minus 0. So we just get 1 times I minus, let's put that minus sign down now before we forget. 2 times minus 1 gives me minus 2. And then 1 times 0 is 0, right? So it's minus 2 subtract nothing, leaves me with minus 2. J. And then 2 times 3 is 6, right? So going across, so this gives me plus 6. And going this way, I get minus 1. So that's plus 1. So 6 plus 1 gives me 7k, leaving me with the vector 1, 2, 7 for the cross product. Okay, and every other cross product is going to be the exact same story. The only thing we can really change on you are the numbers. Otherwise, the procedure is exactly the same. One of the things, let's just confirm one thing before we go on. I told you at the beginning that if one of your vectors is a multiple of the other, then the cross product should be 0, right? The cross product should give 0 for parallel vectors. And also, if you change the order, you get a minus sign. We'll go over some of those in the next video. But as far as the parallel vector rule, let's say I take W to be let's take any a times u, where a is a sum number, right? So 2a minus a 0. And if you think about what happens when you do u cross w, so I, j, k, and I'd have 2 minus 1, 0, 2a minus a 0, and you expand. So, well, the first one, we get that, minus j times 2a 0, 0, k times 2 minus 1, 2a minus a. Now, the fact that I've got zeros makes things easy. It's pretty, it's obvious that that's going to be 0. That's going to be 0 because you're multiplying, both of the entries on the left get multiplied by 0 when you calculate those 2 by 2 determinants. But even this one, notice that 2 times minus a, so you get 2 times minus a, and then subtract minus 1 times 2a, right? You can take that a and you can factor it out, and then what are you left with? You're left with 2 times minus 1, subtract minus 1 times 2. Well, that's always going to give you 0, right? This is a times 0, so you get 0. So that one is 0 as well, and so you get the 0 vector, and this is something that happens in general. Okay, so we'll look more at properties when we get to the next video. Okay, so this is our second of 2 videos on the cross product for Math 1410 Linear Algebra. In the previous video, we went over the definition and a number of ways for remembering the definition, which admittedly is a little bit complicated looking at first. And so we saw that there's this sort of, determinant trick for remembering the cross product. There's a few ways of trying to remember it, and it really doesn't matter which one you work with as long as you find one method that works for making sure that you get the right outcome. So this time we want to look at some of the properties that are satisfied by the cross product and understand why we actually care about this cross product, why it's useful. So this first property, we mentioned this last time, and it is the most important property to a large extent. So the fact that the cross product is always orthogonal to both vectors u and v. Now, there are a number of situations, as listed here and here, there are situations where the cross product could come out to be 0, right? If either u or v is the 0 vector, or if u and v are parallel, then the cross product comes out to be 0. And these are sort of degenerate cases. The interesting case is when u and v are non-zero, non-parallel vectors. And even in that setting, when you compute the cross product, you can verify that the cross product is orthogonal to both u and v. And so what does that mean? That means that if I take... Alright, so welcome to the next of our series of screencast videos for Math 1410 Linear Algebra. We're moving on now to look at lines in 3 dimensions. So we're on the home stretch for Chapter 3, the vector geometry. We've got a couple of videos on lines and then a few on planes, and then we will be finished with the Chapter 3 material. So let's jump right in. Now, just as a review how things work in 2 dimensions, I know everyone is pretty familiar with how lines work in 2 dimensions, right? So we have some sort of a picture like this, right? And we might think of a line as a graph, of a function like this, a function of one variable, and we might draw something like so b is the intercept value. So this thing, when x is equal to 0, y is equal to b. So you have a point 0, b on the line, and once you have one point on a line, if you know the slope, your rise over run, you can construct the line, right? And what makes lines sort of unique compared to other sorts of graphs that you might consider is that if you choose any 2 points on the line, this ratio, this rise over run ratio, right, change in x over change in y, this is always constant, right? It doesn't matter which 2 points you choose on the line, this ratio of the change in the y values over the change in the x values, this is always the same, right? So here, by delta y, I just mean y2 minus y1, and then x2 minus x1. Okay, so you have this constant ratio. So point in a slope tells you how to construct the line, and you probably remember doing some of these problems where somebody gives you a point. Maybe they don't give you the intercept, so they give you some other point on the line, some point x naught, y naught, and then you work out the slope, and then you have this this formula. This is often called the point slope formula for a line. Now, one thing you don't get with these types of equations, you don't actually get vertical lines if you write things this way. A vertical line doesn't really have a well-defined slope. I guess you could say it has infinite slope. The most general equation you can write down for a line in R2, sort of a general line, would look something like ax plus by is equal to c. And in the case where b is equal to 0, that covers your vertical lines. Otherwise, if b is not equal to 0, you can solve for y and get one of the other forms that we've written down. So in 2 dimensions, the main feature of a line is that you've got 2 variables, and they're related by this constant ratio. That when you change one, you know how much the other one changes, and this relationship between the 2 variables tells you pretty much everything you need to know about the line once you've got one point on the line. Now, once you move to 3 dimensions, things kind of come apart as far as this sort of approach, because you no longer have 2 variables. Now you have 3 variables, right? So you're dealing with 3 dimensions. So you've got a 3-dimensional coordinate system like this. So x, y, z. And of course one approach you could take is you could try to kind of introduce multiple slopes. You could try to sort of say how z changes with respect to x, and then say how it changes with respect to y, or something like this. Try to give some not one slope but 2, right? Because we can't really talk about slope anymore. Slope is something that takes place in a plane. And so you could try to give a pair of ratios, and there's some things you could do with that. You might be tempted to sort of add one variable to this sort of equation like we had here. This guy, you might just think about, maybe I'll just add a variable to that. But if you do that, well, you won't get the equation of a line, as we'll see later on. What you get is the equation of a plane if you try to do things that way. So just adding one variable to that type of equation doesn't work. You get a linear object, but you get something that's one dimensional. So how do you specify a line in 3 dimensions? Well, okay, so let's say I have 2 points, right? So I draw 2 points in space, and P, let's say Q is over here. So I'm not going to try to indicate accurately where those are in space, but we've got a couple of points. Well, if I've got a couple of points, as soon as I have any 2 points, I can draw the line that passes through them. And of course, this is true in 2 dimensions as well, right? If I have any 2 points, if I have a point x1, y1, and if I have a point x2, y2, if I have these points, I can use those 2 points to reconstruct the slope. And once I have the slope, I can use either one of those 2 points to get the equation of the line. Right. So this idea that 2 points determines a line, this is something that remains valid if you go up a dimension. But how am I going to write down the equation of that line? Well, what you do now is you say, in 3 dimensions, how do you specify which way a line is going in 3 dimensions? Well, you want to now give a direction. You want to know which way that line is pointing. And we know how to give directions. If you want to give a direction, you give a vector. And we also know that if you have any 2 points determine a vector, right? I can construct the vector PQ between those 2 points. And then if I wanted to get to some other point on the line, right, if I wanted to, let's see, mark some other point, maybe I'll mark it in black. Okay. So if I wanted to mark, say, this point R on the line a little bit further down, right, then I could try to draw this vector. Let me just kind of offset things a bit. So I could draw this vector here, right? I could draw the vector PR. I drew it sitting a little bit off the line just so I don't mess up the picture, but we want to draw that vector kind of on the line as well. So what can I say about PR? Well, I note that this guy here it's parallel to the vector PQ, right? And what do we know about parallel vectors? We know that parallel vectors are scalar multiples of each other. And so what I can do is I can say that, well, this vector PR it's got to be some multiple of PQ. So there's got to be some real number T so that PR is equal to T times PQ, right? So T here is a real number. And so then what you can also kind of think, if you think about this T now as a variable, so you kind of think of this as some sort of like scalar variable here. You can vary the value for T. If you make T bigger and bigger, you're going to keep going further and further out along the line, right? At T equals 1, you're kind of you're here at T equals 1, and then you go out here, you're at T equals 2, and so on. And of course, you can take values between 1 and 2. I could take, say, T equals 1/2 and start shrinking things. Or I could also, of course, go into the negative numbers. I could get to, say, T equals -1, and I could end up, going down the other direction on the line. So this allows me to describe every point on the line. But we have to make one more modification because, of course, when we want to specify points in space, if we want to describe points in terms of vectors, we want to give position vectors. We want things that are anchored at the origin, and right now these vectors are floating out there in space. They're all anchored at this point P. So how do we fix that? Well, we know how to fix that. We just use the tip to tail rule for vector addition, and so what I can do is I can draw 2 more vectors. So I'm going to draw this guy here. Actually, let's make everything in blue. So I'll draw this vector like so. This will be let me just call it P with a arrow hat, the position vector for the point P. And I could draw this guy going to the point R, right? And so then what can I say in terms of the tip to tail rule here? Well, I can see that this vector R, what can I say about R? Well, R is equal to P plus T times PQ, right? Because T times PQ is this vector that we drew in black. Adding P to this vector PR gets me to the vector R, right? So this is kind of all we're really saying here is that the vector from the origin to R is, well, that's like going from the origin to P and then going from P to R, right? That's all that we're doing here, but we have a particular way of describing this vector PR. So if we write, if we let V equal to PQ, direction vector, and often one of the notations you'll see is you'll see this R naught, R sub 0, to be P, right? So sort of the position at time 0. So you think of this here as like T equals 0. And often you could think of this scalar T as time if you think about kind of a particle moving along a line. Sometimes you think of this T as time. You don't have to think of it as time. So then you get something that looks like this. So you can think of R now, and if you want to, you can even think of it as a function of T is equal to R naught plus T times V. All right. So this gets you the vector equation for a line in 3 dimensions. All right. Now let's actually take that vector equation. Let's break it down. What do these things look like? So this, so we started with this guy here. So R of T is equal to R naught plus T times V. Okay, for our line going in space like this, right? Where R naught refers to some initial point on the line. So let's give that point coordinates: x naught, y naught, z naught. Okay, there's our vector R naught. We've got our vector V, which is parallel to the line, and let's say V has components A, B, C. And so if I have some other point on the line, so here's a point X, Y, Z, and we let R denote the position vector for any other point X, Y, Z on the line, then what we have is we have that X, Y, Z is equal to X naught, Y naught, Z naught plus T times A, B, C. And so then if I kind of equate components here, if I look at the X components and kind of break things down term by term, I get that X must be equal to X naught plus A times T. Y is equal to Y naught plus B times T. Z is equal to Z naught plus C times T. And so sort of an interesting thing happens because each one of these 3 equations, these are all linear equations. We can kind of, think of these are sort of in this format, y equals mx plus b, right? So this is kind of, I guess, this is like your b. This is like the a, b, or the c plays the role of the m, and t plays the role of x, right? So it's the same sort of form that you're used to for writing in the equation of a line in the plane. What's interesting is you go up by one dimension, so you add a 3rd variable, and it turns out that the right way to do things is to actually add even one more variable. Suddenly this t comes out, and x, y, z, treat all 3 of them kind of equally. So we don't really solve for one of the variables in terms of the other here the way we would in the plane. We treat x, y, z all as independent variables that happen to each of them depend on this one dependent variable t. This t, by the way, just in terms of some terminology, t. So t is sort of our dependent variable. Variable. T is frequently referred to as a parameter, and then you would refer to these guys here as the parametric equations for your line. Okay, so we can do the vector equation or we can do the parametric equation. Either one conveys the same information, and you can use them interchangeably. It really doesn't matter which one you choose to use. There's another set of equations that you'll often see in textbooks, which are the symmetric equations. We're not going to worry about the symmetric equations in this course. It's not something that will be useful for us. All right. So that's kind of the introduction of the basic terminology and the setup here. Let's do one example before we go. So here we've got a couple of points in 3 dimensions. We want to come up with the line that passes through those points. So the first thing we need is we need a direction vector. Okay. So what is our direction vector? Our direction vector is this vector from P to Q. And remember, when we calculate the vector from P to Q, we do tip minus tail. So we do 2 minus 0, minus 1, minus 1, 4 minus 3. That gives me the vector 2, minus 2, and 1. If you want to, you can think of, one thing you might want to kind of keep in mind when you're doing some of these. Note that so the vector from P to Q is the vector from the origin to Q plus minus the vector from the origin to P. This is the head minus tail rule. If you rearrange this a little bit, this is saying that the vector from the origin to Q plus the vector from P to Q is the same thing as the vector from the origin to, if I do the vector from the origin to P plus the vector from P to Q, that's equal to the vector from the origin to Q, right? And so the way you kind of think of this is telling you, well, if you start at the origin and you travel from the origin to the point P, and then you travel from the point P to the point Q, right, you end up at the point Q. So it's the same as if you just travel directly from the origin to Q. So you can keep track of things these ways, and sometimes it comes in handy to be able to break things down like that. All right, so we've got our direction vector. We need any point on the line. We might as well choose, we can choose either one of the two that we're given. Let's choose our point to be given by the point P. So we'll take 0, 1, 3, and that gives me the vector equation. So x, y, z will be given by 0, 1, 3 plus t times the direction vector, 2, minus 2, and 1. And the other way you could do this is say, well, x is equal to 0 plus 2t, y is equal to 1 minus 2t, z is equal to 3 plus t. Okay, so we'll do some more examples with lines in the next video. All right, so in our previous video, we introduced the idea of a line in 3 dimensions and the fact that in 3 dimensions you can no longer describe a line using slope, so you need to introduce the idea of using a point and a direction to specify a line, leading to either vector or parametric equations for a line. So in this follow-up screencast, we just want to do a couple of examples showing how to work with these ideas. Okay. To start with, just adding some terminology, parallel lines. We've talked about parallel vectors as well, right? We know that 2 vectors are parallel if they're scalar multiples of each other. And if you're dealing with lines in 3 dimensions, right, if you've got a couple of lines, so what should it mean for lines to be parallel? If I have 2 lines, in space, and they're parallel, well, they should both kind of be traveling in the same direction. And how do I know that they're traveling in the same direction? Well, if one of them has, say, a direction vector v, and the other one has a direction vector w, right, then those vectors should be parallel. So lines are parallel if the direction vectors are parallel, so I expect that w should be some scalar multiple of v. And this makes it fairly easy to tell if lines are parallel, right? So if somebody hands you, one line and they say, okay, so x, y, z is maybe 1, 2, 3 plus t times 0, 1, 2, and then so that's sort of your line 1, and then your line 2 maybe is x, y, z equals, let's say minus 1, 1, 4 plus, t times maybe 0, 2, 4, right? We look at these two and we say, well, the direction vector for the second line is just double the direction vector. For the first line, they have parallel direction vectors, so they're parallel lines, right? They pass through different points, so they're not the same line, but they are parallel. One thing that you do have to watch out for in 3 dimensions that doesn't happen in R2, in 2 dimensions, parallel lines are the only case where lines fail to intersect. In 2 dimensions, every pair of non-parallel lines is guaranteed to intersect. But in 3 dimensions, you can have non-parallel lines that don't intersect. What you want to think of here, think of them as describing in like flight paths or something. So you could have one line kind of heading off, in one particular direction with a direction vector going that way, right? And you could have another line that is, say, passing right underneath, let's say. So you might have another line that kind of goes along and passes underneath and heads off in some other direction with some other direction vector. Let's say W, right? And so the lines aren't parallel because they have direction vectors which are not parallel, but they also don't intersect. Somewhere along there, you might be able to, if you look hard enough, you might be able to determine kind of points on the 2 lines that happen to be closest together. Maybe this point here and this point here, and there's some kind of separation between the 2, right? So there's room for one line to pass, say, underneath or over top of another line because you're in 3 dimensions. So you can have these pairs of lines which are called skew lines, lines that don't intersect. And we'll look at some examples dealing with that as well. Now, so suppose somebody hands you a pair of lines. Like we said, it's pretty easy to tell if lines are parallel. You just look at the direction vectors. Or if somebody hands you a pair of lines, you look at the direction vectors, you can see that the direction vectors are not parallel, so the lines are not parallel. How do you tell if those lines are intersect or if they are skew? How do you figure that out? Well, you figure that out with a bit of algebra. So we'll play around with that in a second. First, let's just kind of work with this definition with parallel lines. So we've got the vector equation of a line. We want to find okay. Let's see what we got here. What do we have? Let's draw a picture. Okay. So we want a line L. What do we know about the line? Okay. So we've got a line passing through some point P, and we've got 2 other points. I don't know where exactly we want to draw them. Maybe one of them is here. Here's Q. R is, again, it's impossible to draw these things accurately. Let's say it's like this. Q, R here. Okay, so we have one line that's passing through those guys. We want to construct another line which passes through the point P and is parallel to the other line. So how do we do it? Well, the way you do it is you just use P as your R0, as your sort of reference point on the line, and you use the direction vector for the other lines. So we can figure out what this direction vector is. So we take V to be this vector from R to Q. Okay. So I've decided to set it up going from R to Q. You could do it going from Q to R if you want. So with Q as the head, we do head minus tail. So 1 minus 1 minus 3, 3 subtract minus 2, 2 subtract 5. So minus 4, 5, minus 3. If you'd done it the other way around, you would have 4 minus 5 plus 3. That works as the direction vector as well. You can always replace V by any vector which is parallel. You would still describe the same line. And so the vector equation for the line in this case is going to be, so x, y, z. Okay, so here's our R is equal to, what's our R0? So we need to make sure it passes through the point P. So here's our point P. So we take 2 minus 1, 4. that's our R0, our reference point, plus t times, now we put in our direction vector, -4, 5, -3. Okay, and we have a parallel line. All right. Now, what about this kind of determining whether or not lines intersect? Here are a couple of pairs. How do we get this to work out? Notice that one of the things I've done when I've written down these two lines is I've used different parameters for each line. The first one L1 of S, the second one L2 of T, S and T. Okay. Why do I need to do this? Well, because if you're dealing with lines given in terms of parameters, in terms of this S and T, if you think of these parameters as kind of like a time parameter, again, think of maybe a plane flying in a straight line, and the time tells you where you are at any, if you know the velocity and you know where they were at a given time, then you can figure out where they are later on as you vary the time, right? The plane moves along. And so one of the things you want to think about here is, if you have a couple of lines passing in space, and let's kind of continue this kind of plane analogy for a second, this airplane analogy, right? Let's suppose that I have one line going like this, and I have another line going like that, and imagine that they do in fact intersect at some point, right? And so think of these as like flight paths. All right, is it necessarily a bad thing if those two flight paths intersect? Well, not necessarily, unless they happen to coincide at a given time. So you can distinguish it. You might want to distinguish here between, say, an intersection and a collision. If it happens that you can get the same point for the same parameter value for both of the lines, that's the case where your two planes crash in midair and everyone dies a fiery death. But if you get the same point for different parameter values, that's okay. That means one plane passed through that point in space at 2 o'clock in the afternoon, and the other one passed through later on at 5. Then there's no problem. They go through the same point, but they go through at different times, different parameter values. So then you don't worry so much. So how do you figure out if lines intersect? Well, this point, right, whatever this point is, it's got some coordinates. It's got coordinates, let's say, x, y, z, right? And that's supposed to be a point on both lines, so it has to satisfy the equations of both lines. So let's look at this this first one here. Let's look at A, right, and see what we can say. Well, if there's some point which is common to both, then let's say x, y, z satisfies the first equation. Then I would be able to say that -1 minus 2s, that's the x coordinate on the first line. That would have to be equal to x, right? And 3 plus 3s, that would have to be equal to y. 4 plus s, that would have to be equal to z, right? But then I also want this to be a point on the second line, so I can equally say that x should be equal to 2 plus t, looking at the 2 plus 1 times t, right? Y should be equal to, 0, okay, right? 0 plus 0 times t. Y is supposed to be 0 on the second line, right? If you get a 0 in that direction vector, that means that coordinate is remaining constant. Z should be 1 minus t. So what you can do here is you now look to see whether or not you can find values for both s and t that work for all three of these equations at once. So this is an example of a system of equations, if you like. You could rewrite things if you want. You could rewrite this as, the first one as, let's move the 2s and the 1 over to the, let's move the 2s over, we'll put the constants on the other side. We could write this as 2s plus t equals -3, right, as one equation. The next one says 3s equals -3. There is no t. And then the last one I could rearrange to say that s plus t is equal to, all the right-hand sides are -3. That's strictly a coincidence. And so now I look to see whether I can find values for s and t that work everywhere here. Well, this equation nails down the s value for us, right? So that middle equation tells me that we must have s equal to -1, or else the second equation is not satisfied. We need to be able to satisfy all three equations at once. So if s is equal to -1 in one of the equations, it has to be equal to -1 in the other two. So we now look at the first equation. So equation 1 says 2 times -1 plus t is equal to -3. And that tells me that t would also have to be equal to -1. Now what about equation 2? So if we go to equation 2, -1 plus t is equal to -3. Well, that tells me that t would have to be equal to -2. And then we say, well, -2, but -2, that's not the same thing as -1, right? So the first equation, the only way the first equation works is if t is equal to -1. The only way the second equation works is if t is equal to -2. So I can't satisfy both of those at once. And so this means there's no solution. So that means there's no intersection. Okay. All right. That got a little bit crowded there. Let me rewrite that for you. No intersection. Because -2 is not equal to -1. All right. So let's do one more just to make sure we've got the hang of this. So if we're doing the second pair of lines here, again, we look at the first equation. So the first equation we have 0, so the x coordinates have 0 plus 1 times s. So s equals x. Then I look at the middle, -2 minus 1 times s. So -2 minus s, that should be equal to y. And then I look at the third components, 1 plus 0 times x, so simply 1 is equal to z. Right? That's what I get looking at line 1. Right? So line 1 tells me this. And on the other hand, x from line 2, x would have to be equal to 4 plus 2t. Y would have to equal -5 minus t. And z is going to have to be equal to 2 plus t. Okay, and those equations are going to have to hold if the point is going to be on line 2. So once again, you work with these and you say, well, you know what, I can solve right away for t if I look at this this equation here. Okay, so let's call these 1, 2, 3. And so from equation 3, I get that t plus 2 is equal to 1. Tells me that t is equal to -1. Okay, so now let's go up to, say, equation 1. Equation 1 says that s is equal to 4 plus 2t. So that would be 4 plus 2 times -1 equals 2. Okay, so this one says s is equal to 2. So now we go to the second equation and we say, okay, is this going to work? If I put, on the one hand, if I do -2, on the left, -2 minus 2, okay, gives me 4. So this should be my y value if I'm on line 1. And if I'm on line 2, I'm supposed to get -5 subtract -1. And that works. -5 minus -1, that's -5 plus 1. Oh, no, it doesn't work, does it? Oh, no, it does. I missed the minus sign. -4. I knew this one was supposed to work out. Minus signs always get you. Okay. So that works, right? -4, it works for both of them. So this one means in this case there is a point of intersection. Y is equal to -4. What about x and z? Well, we know what the z value is, right? Z has to equal 1.
x was equal to s is 2. So my intersection here for part B, let's put it up here at the top. The intersection is going to be, so I either plug the s value into the first equation, or I can plug the t value into the second equation, whichever way I want to do it. I find that the point of intersection is 2 and minus 4 and 1. That's the point of intersection. Okay. The other type of question that we can ask in the context of lines is we can ask a distance problem. So somebody hands you a line given to you either as the vector equation or as parametric equations, and they give you some other point, and they want to know what is the point on the line that is as close as possible to this given point. How are we going to figure that out? So all of these sorts of problems begin with a diagram. Okay. So, and here's what your diagram looks like. Don't try to actually kind of do things accurately. I know things are in 3 dimensions. Don't draw a 3-dimensional coordinate system. Don't do anything like that. Start by drawing a line. So I draw a line. L. Right? I've drawn it horizontally for convenience. I draw a point. P. All right? And now what I need to do is I need to start labeling things and make sure that I'm doing it accurately. So P is equal to 5 minus 3, 7. Now what I need to do is I need to say, well, look, I've got a reference point on my line, right? I've got this point on my line. Let's mark that. Okay. P naught. 2, 1, minus 3. Okay. The direction vector, well, the direction vector needs to be parallel to the line, so let's put that in. So here's my direction vector. V is 4, 0, negative 3. All right. Now let's think about what we're looking for. We're looking for the point on the line that is closest to this point P. So where is that point going to be? Well, the way where we find it is closest point is going to be the one so that when I drop this line down, so let's call that point Q. So what can I say about the relationship here? Well, this line that I dropped down, that's going to have to be perpendicular, right? So I'm going to have to set things up so that this line, this vector, let's put in this vector here, okay? This vector, what is that vector? That's the vector from Q to P, right? And that vector from Q to P has got to be perpendicular to the vector V. How do we know if two vectors are perpendicular? Well, we know that they're perpendicular if their dot product vanishes. So we're looking for this sort of setup. And it turns out the way you do this is you use this orthogonal decomposition using projections, which we discussed earlier. So how do you set this up? So what we need to do is we need to put 2 more vectors in place. So let me put them both in green. So the first vector we need is this guy, the vector from P naught to P. Now, that vector I can project onto the line. Remember, the way projection works is you drop this perpendicular down, you figure out where that point lands, Q, and you draw the line from the common tail to where that perpendicular hits the line. So now we can see what we have to do here. So here's what the solution looks like. So we first find that P naught P is given by, so 5 minus 2 minus 3 minus 1, 7 minus 3. So I get 3 minus 4, 10, and I call that vector W. Okay. And now from the diagram tells me that the vector from P naught to Q is equal to the projection of this vector W onto the vector V, the direction vector, right? Because V is parallel to the line I'm trying to project onto the line. So remember, this is given by V dot W over V dot V, and then we multiply by V. Okay, So here's my W. So let's just kind of write things down here. We'll do some rough work on the side. So V is equal to 4, 0, minus 3. W is 3 minus 4, 10. So the dot product, V dot W, 4 times 3 is 12, plus 0, minus 30. So I get minus 18 for the dot product. And V dot V, you can probably work out that that's going to give you 25. So this is going to come out to minus 18 over 25 times the vector V, which is 4, 0, minus 3. Okay, let me box off my rough work here so we don't get mixed up. So I've got this vector from P0 to Q, and what do I want? I want the point Q. I want to get the coordinates of the point Q. So how do I describe that point Q? Well, the vector from the origin to Q, remember the way that you can do this is, one way to get to Q is first go to from the origin to P0, and then travel from P0 to Q. So I go from the origin to P0, then I go from P0 to Q, and so I do 2, 1, minus 3, and here's my P0 Q, minus 18 over 25 times the vector 4, 0, and minus 3. Okay, and from there you can clean it up. I'm not going to do it because I don't want to drag this thing on, and besides I'm out of room, but we can simplify this expression here and then work out what the coordinates of our point should be. And if we wanted to get the distance from that point P to the line, well, once we've got Q, we can use the distance formula to calculate the distance from P to Q. Another way you could calculate the distance is to take this vector P0 Q, subtract it off from the vector P0 P, and what you'd be left with is the vector from Q to P, and then you could compute its length. There's a few ways to do that, but we'll see more examples in class.
All right, so next up in our material for Math 1410, we move on to, from lines in 3 dimensions, we're going to move on to planes in 3 dimensions. So we have a rough kind of intuitive idea of what a plane is, right? It's sort of a flat level surface. We're used to talking about, the coordinate planes, for example, right? So we're used to, in 3-dimensional space, if we draw our coordinate system out, right? We can sketch out the XY plane, the set of all the points where Z is equal to 0. We can sketch out the YZ plane where X is equal to 0. We can sketch out the XZ plane where Y is equal to 0. We have these coordinate planes, and now of course I've only drawn the portions of those planes where all variables are positive, but you can extend these off into the negative directions as well. So if you want to generalize this idea of a coordinate plane, right, you want to take something that looks like one of the coordinate planes, but you want to change its orientation in space. You want a plane which is sitting there at some sort of angle, and we'll see that one of the ways to describe a plane is by simply taking, this sort of general linear equation that you would give for a line, or if I cover up the c times z, if I just kind of hide this part for a minute, ax plus by equals d. That's the equation of a line in 2 dimensions. Adding one more variable takes you to a plane in 3 dimensions. What's not clear yet is how do you actually kind of get an idea of what this object looks like. How is it oriented in space? What do these numbers A, B, C, D tell you about where and how that plane is located? One other way, just as 2 lines describe, or as 2 points describe a line, 3 points describe a plane. You can kind of imagine that if I have 3 points sitting there in space somehow, I can sort of connect the dots and construct that triangle. And that triangle's got to be sitting in some sort of plane, and so you can kind of think about extending this thing off in other directions to get an idea of what that plane looks like. Or if you had a pair of intersecting lines, right? If I have this line here meeting with that line there, those 2 lines are going to have a plane in common. this notion of span, this is something we might explore later on. This is the idea that, a general point in a plane can be described in terms of vectors, in terms of a linear combination of vectors. And with lines, we saw that with a line, you need sort of one vector, one direction vector, and then every other point on the line is given in terms of that guy, some multiple of that vector. For plane, you need a second direction, so you need a second vector. But the main kind of key ingredient for most of our plane constructions is going to be this normal vector. And most problems where you have to figure out the equation of a plane boil down to figuring out how to obtain a normal vector to the plane. The normal vector is going to be, so the idea is that if you've got a plane, you've accounted for 2 of your 3 dimensions in space. There's going to be one direction which is left over that is perpendicular to every direction that lies in that plane. And that's where the normal vector comes into the picture. Okay, so here's one way to think about a plane. Let's close that bracket. So plane is a 2-dimensional object, right? So let's kind of draw in our coordinate system. All right, so we've got our coordinate system, and we have some point P0, okay, sitting out there in space somewhere. And I draw one vector v at that point. Well, once I've got that one vector, I can extend the line here, right? So I can now think about the line passing through the point P in the direction of that vector v, right? But if I just have a point in one vector, all I'm ever going to get is a line. I have no way of getting off of that line. So how do I get off the line? Well, the way I get off the line is I add a second vector. So if I add a second vector, let's say w, right? This allows me to get off the line. So what I have now is I can think about this. I have a second line which is passing through that point in the direction of a different vector. I can think of that pair of lines as giving me sort of a new coordinate system floating there somewhere in space. Now those lines aren't necessarily perpendicular, right? There's no requirement here that v and w have to be orthogonal vectors. Those lines might meet at some sharp angle, but as long as those 2 lines are not parallel, that second direction is all that I need. So you can sort of start to visualize the plane that you're dealing with here, right? So you've got this plane kind of hanging out in space like this. And if you wanted to get to some other point on the plane, let's say you're trying to get to this point over here, right? How do you get to that point? Well, you can think about drawing 2 lines to that point. You could draw one line which is parallel to W, or you could draw a line which is parallel to V, right? So basically, you introduce a grid system, right? You can introduce kind of a grid, one set of grid lines which is parallel to V, one set of grid lines which is parallel to W. They may not be rectangular grids; these might be parallelograms, but that's nonetheless good enough. So one way I could do this is I could say, well, I have what? I have this vector here, right, which is parallel to V. It's in the same direction as V, but I had to make it slightly longer. So I could say, well, that's going to be, it's some scalar multiple of V. So maybe I say that's S times V. It's some multiple of V. And then I have this guy here, right, which is the same as this vector here. This is one big parallelogram here. So that vector, well, that's parallel to W, but again, it's not necessarily the same length as W, so that's going to be some other multiple of W, say T times W. So now, how do I locate that general point in space? Well, I've got a couple of position vectors, right? I've got this vector here going from the origin to this point P0. I've got this new point, let's call this guy P, maybe, because we're drawing that in green, P over here. And so I can draw the vector going from the origin to that point, like so, right? And I can play kind of the same game that we did with with lines. If I call that R0, and if I call this guy R, I could say, well, this R is given by, well, I go from the origin to this point P0, so I add R0. And then I travel in the direction of V for a little while, so I need to add on S times V. That gets me, so I go from here, now I'm here, I add S times V, now I'm over there. Right, I go here, there, and now I need to get the rest of the way to P. I need to travel this distance, and that means I need to add on T times W. So that's one way of kind of thinking about a plane is, you can describe a plane in terms of a pair of vectors. You need now two parameters, right? So you need two parameters, two vectors. So in this case, S and T, right? So you could think of this R if you want. You can kind of think of it as like a function of two different variables if you want, S and T. So this is one way that you can kind of, work things out, right? And you can, so if you're writing down kind of X, Y, and, so let's say, yes, you would get something that looks like this, right? So you would get something that looks like, X would be like X0 plus SV1 plus T W1, Y would be Y0 plus SV2 plus TW2, Z is equal to Z0 plus SV3 plus TW3. So you could think of a plane like that, and this is a useful way to think about a plane. This is, if you kind of continue on through the calculus sequence, this will eventually be useful to you if you make it as far as, let's say, calculus 4. I know most of you are not getting to calc 4, so this might not come in handy there. It may come in handy later on when we want to, if we get as far as talking about subspaces, vector subspaces, we might spend a little bit of time on that. Then this picture will really come in handy for us. But for doing sort of vector geometry in 3 dimensions, this point of view is not a particularly useful one, or at least it's not a particularly efficient one. The way you want to kind of approach things in 3 dimensions is, rather than giving these two vectors which are parallel to the plane, you want to come up with one vector which is perpendicular. And so you say, you know what I want? I don't want V and W. I want, and let me get this point P0 out of the way. I want, the vector that I want is going to be, well, let's put it back. P0 is there. The vector I want is this guy. N, perpendicular to the plane. So N is perpendicular to both, I want something perpendicular to both V and W, and if it's perpendicular to both V and W, then it's going to be perpendicular to kind of any linear combination of V and W. So it's perpendicular to every vector in the plane. And if you've gone through the cross product videos, then you know actually what this N should be. N should be the cross product of V and W. So we'll see in the next video when we do some of the examples, we'll see that this is kind of a key construction. This cross product construction to obtain the normal vector is a pretty standard trick when you're working with planes. All right. So here's an example. All right, and let's kind of do a quick sketch. This is an example where we want to work with this vector form on the previous slide. So I've got 3 points. I'm not gonna try to draw these accurately. Okay, P, Q, R. This will be a good warm up for things we want to do later. So I need 2 vectors that are parallel to the plane. This plane has to contain these 3 points. So these points are all in the plane. So if I draw a vector between a pair of points, let's say I draw the vector from P to Q, right? That vector has to lie in the plane because it passes between 2 points in the plane. Planes are these kind of flat objects. So if I kind of stretch a string between 2 points that lie in the plane, that string is gonna lie flat on the plane. So we can call that V, and let's just kind of take P as a common anchor. It's often convenient to anchor both of your vectors at the same point. We'll call the other one W. Well, then we know what to do here, right? We know that V is the vector PQ, so we do our head minus tail rule. We do 7 minus 2, 4 subtract minus 5, and minus 5 subtract minus 3, and we get the vector 5, 9, and minus 2 for v. Similarly, w, the vector from p to r, we get 0 subtract 2, 6 subtract minus 5, minus 2 subtract minus 3, and this gets us the vector minus 2, 11, and 1 for the vector w. So those are two vectors that are parallel to the plane, and so if we wanted to describe the plane one way, we could describe any other point on the plane. So any point on the plane would be given by, so one way to describe a point will be x, y, z equals, let's choose this point P as our reference, 2 minus 5 minus 3 plus s times 5, 9 minus 2 plus t times minus 2, 11, and 1 for some s and t. All right. But most of the time, like I said, we're not going to write down our plane in this form. We'll still want to be able to find those two vectors that are parallel, because once we have those two parallel vectors, we can compute their cross product to get a normal vector. All right. So the normal vector allows us to get a simpler equation, and here's how we do it. Okay, so the normal vector, we usually call the normal vector n for normal, is a vector with the property that it is orthogonal to every other vector that is parallel to the plane, right? So in this previous slide, right, the normal vector would have to be something which is parallel to, in particular, to both v and w, but also any other point that lies in the plane. Okay, so once you've got that normal vector, you can describe your plane, because what you do is, so you would kind of illustrate with a picture. So we put our coordinate axes in. Actually, let's not even bother with coordinate axes, because that adds a lot of clutter. Let me just draw, so here's a plane. Okay, so we draw a plane like so. We fix our reference point, P naught, and let's say our normal vector is sitting here, okay? So the normal vector is perpendicular to the plane. So what does that mean to say that the normal vector is perpendicular to the plane? Well, if I choose any other point on the plane, wherever I decide to draw it, let's say here, okay? Here's my point P, right? Well, as soon as I draw a second point on the plane, then I can put the vector between them, right? Like so. That's going to be this guy. This is my vector, P naught P, right? That's a vector between 2 points in the plane, so it's parallel to the plane. And because it's parallel to the plane, by definition of the normal vector, it must be orthogonal to the normal vector. So I must have, so the consequence here is that we must have normal vector dotted with P naught P, right? Those two vectors have to be orthogonal, so that dot product has to be 0. So if we know that that normal vector has components, let's say a, b, c, then we can calculate the dot product. So remember, how does the dot product work? I should do a times the x coordinate here, so a times x minus x naught, then b times y minus y naught, and then c times z minus z naught. I add those up. That gives me the dot product. That dot product should be equal to 0. So I get a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. Okay, so that gives me the scalar equation. You can also clean this up. You can write this as ax. So if you push the ABCs through the brackets, ax plus by plus cz. Now, x, y, z, we think of those as variables. The x naught, y naught, z naught, think of those as fixed. So those are just numbers. So a times x naught is a number, b times y naught is a number, c times z naught is a number. If you combine all of those on the right-hand side, that's going to give you some other number, d. D happens to be equal to, if you want to write it out, d is ax naught plus by naught plus c z naught. If you feel like including that, that's the value of d. Okay, so now, once we've got this idea for the scalar equation, if somebody gives me a point and a normal vector, I can write down the equation for my plane, right? So the scalar equation is given by n dotted with, well, let's take this shorthand, right? R minus R naught is equal to 0, where, as usual, R here has been for us denoting this vector x, y, z. R naught is going to be the position vector for P naught, so 2 minus 3, 1. So if I subtract those two vectors, plug in the values, this gives me 5 minus 2, 3. That's my normal vector, dotted with, so I do x minus 2, right? X minus 2 over here, and then y subtract minus 3 gives me y plus 3, z subtract 1, and that dot product should be equal to 0. Let's kind of separate that. All right, but we can go a bit beyond this. We can simplify, right? This gives me 5 times x minus 2 times y plus 3 times z minus 1 equals 0, and now we've got a sort of a single scalar equation. If you really want to, you can expand and simplify. 5x minus 2y plus 3z is equal to, what is it equal to? 5 times 2 is 10, plus 6, plus 3, so 5x minus 2y plus 3z equals 19, gives you the equation of your plane. All right, so that's it for this one. We'll look at some more complicated examples in the next video. Okay, welcome to the next video in this series of screencast lectures for Math 1410 Linear Algebra. So we're going to continue on now with our study of equations of planes in 3 dimensions. And we're going to look at how do you actually determine the equation of a plane. So one of the things that you'll recall is that if you, so just as a reminder before we begin this example, is that if you're given a normal vector n equal to a, b, c, and a point, let's say x naught, y naught, z naught, then you get the equation, you get this equation for a plane. So the equation for your plane is going to be n dotted with this vector x minus x naught, y minus y naught, z minus z naught equals 0, right? But if you expand out the dot product, what that dot product looks like, you got a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And notice in particular that you have a times x, b times y, c times z. So the components of the normal vector, they show up as the coefficients of x, y, and z in the equation of the plane. So with that in mind, coming to an example like this one, where instead of being given the normal vector and a point, which is kind of the simplest scenario that you might find yourself in where you're trying to write down the equation of a plane, here we're given a point that is on the plane, and instead of being given the normal vector, we're given a parallel plane, right? So maybe the plane we want is here, and we're given the equation of another plane up here, which is parallel, right? But parallel means the normal vectors for those two planes should also be parallel. So in particular, if they have the same normal vector, they're going to be parallel planes. So what we can do is we can determine the normal vector for the plane that we're given, and we can use it as the normal vector for the plane that we want. And so we look here and we say 5x minus 3y, don't forget the minus sign, the 2z, and we compare with the sort of generic equation that we have here, and we say, well, given this equation, 5x minus 3y plus 2z, we compare with the general scenario, and we say, okay, so a here must be 5, right? So this a must be our 5.
The B must be our minus 3. The C must be 2. And so we can now identify that for our given plane, so for the plane with the equation 5x minus 3y plus 2z equals 0, we have the normal vector 5 minus 3, 2. So we can go ahead and use that normal vector to compute the equation for our new plane. So the only thing that we're going to do is we're going to change the point, right? So I don't know what point was used to determine that original equation, but we're going to use this different point here to get the equation for our new plane. So how do we do it? Well, we follow this procedure here in the reminder, and we say, all right, the equation for our new plane, it must have the equation. Well, it must be n dotted with x minus 7, y minus 1, z minus 3 equals 0, putting in the equations for this point P naught. And so what does that give us if we actually write things out? That tells me that 5 times x minus 7 minus 3 times y minus 1 plus 2 times z minus 3 equals 0. Okay, and then there's nothing wrong with leaving your equation like that. If you want to simplify, you can, but there's nothing wrong with leaving it in that form. If we want to do one more step, we might say, okay, so our equation is 5x minus 3y plus 2z is equal to, what are we going to get here? 35 minus 3 plus 6, so 38. Okay, so notice that the left-hand side is the same as it was for the parallel plane. What changes is the right-hand side. So the point on the plane affects that value that you get on the right-hand side. So we see that showing up here. Okay. So moving along, I'll also remind you that last time we said, well, one of the other ways that you can write down, describe a plane is by giving a pair of vectors. So we said, if you have two vectors, right? So this is, like v, and this is say w here, right? This is another way that we can describe a plane because, our picture again, remember, is that we start with our sort of point somewhere in space. Here's our point. Corresponding to this, this is the vector for sort of P naught here, right? So here's our point P naught. And then at that point, we've got our vectors, say, V and W through that point. And then the plane is sort of everywhere that you can reach by traveling in some combination of in the direction of V, going some distance in the direction of V, and then some distance in the direction of W. From the point P naught gets you to anywhere else on the plane. So that's what this equation is describing. So this is fine, and this is certainly one way that you can describe a plane, but it's not as convenient as the scalar equation, right? This equation is a little bit bulkier, so how do you clean it up? Well, to clean it up, we need a normal vector. So how do we get a normal vector? Well, the normal vector should be orthogonal to every vector in the plane. In particular, that normal vector should be orthogonal to both v and w. But we know how to construct a vector which is orthogonal to two given vectors. That's simply the cross product. So we calculate the cross product, v cross w. So this is going to be what? This is going to be, let's write things out. I, j, k, 1, 0, minus 2. 0, 2, 1, and let's work things out. We're going to get for I, right? So I'm doing for the I component, I'm doing this guy here. I get 0. 0 times 1 is 0. Minus 4. 0 subtract minus 4 gives me the plus 4. So let me just get that out of the way. Let's erase that. Right, and then for j, remember we put the minus sign in front of the j. We do, for j, we're going to do 1 times 1, and then we subtract off, well, minus 2 times 0. Well, that's 0, so j, we just get minus 1. So minus 1 times j, oops, minus 1 times j. And then for k, we're going to do 1 times 2, subtract 0 times 0, so that's simply 2 plus 2k. So that's the vector 4, minus 1, and 2. Remember, if you want to make sure that you didn't make a mistake, you can calculate the dot product of this vector with the two vectors you started with. Make sure that you do indeed get 0 for both of them, and you can check quickly that that is the case. Now that you have the normal vector, well, you already have a point on the line. It's this guy. So now that you have a normal vector and a point, you can get the scalar equation. The scalar equation is going to be given by, well, the normal vector dotted with, oops, I think we called that r before. So let's do that again. R minus r naught equals 0. So that comes out to, well, 4 minus 1, 2, dotted with x minus 3, y minus minus 2, so y plus 2, z minus 4. That should be equal to 0, so this gives me 4 times x minus 3 minus 1 times y plus 2 plus 2 times z minus 4 equals 0, so this gives me 4x minus y plus 2z is equal to, let me see, it's going to be 12 plus 2 plus 8, that's 22. Okay. All right. Let's try another example. What if we wanted to go in the other direction? What if we wanted to take something given in scalar form and we wanted to write it in vector form? So one of the things we can do here, well, the first thing we need is we need our, what's our r naught? We need our point, right? We need a point. One of the ways that you can choose a point, and any point will do, is that if you put y equals 0 and z equals 0, what does that leave you with? That leaves you with 3x equals 6, so x is equal to 2. So that means that you can take the point 2, 0, 0, and that's on the plane. Okay. Generally, if you set 2 of the 3 variables equal to 0, then you can solve for the remaining variable and figure out a point. So here we set y and z equal to 0 and solve for x. We could have also set say x and y equal to 0 and got z equal to 3. That would work too, but this is the one we chose to do. Now, what do you do with the rest of it? So what you can do is you can say, all right, let's rewrite this equation here as, let's see, the thing that's easy to solve for here is y, right? Y is equal to 3x plus 2z minus 6. And actually, we can probably skip the step of choosing the point, right? Let's actually, let's leave this out for now, okay? We'll see that we don't need to do it. We can do everything all at once. How do we do it? Well, once we've got y in terms of x and z, right, then x, y, z, okay, I'm going to write that as, well, x, and then 3x plus 2z minus 6, and then z, okay. Now, I'm going to start sort of pulling things apart here. I'm going to break this into 3 vectors. X, 3x, 0, and then 0, 2z, z, and then 0, minus 6, 0. Okay, so all I've done is in the first vector I had all the things that involve x, right? So the x here and the 3x go into this guy. In the second vector I've got all the things that involve z, and in the third vector I have any constants. There's only one. It's the minus 6. Okay, so now what I can do, so the point p naught I'm going to take, it's going to be this guy. This is going to be my p naught. 0, minus 6, 0, right? We can check that that's also a point on the plane. If x and z are both equal to 0, y has to be minus 6. Now I'm going to do one more step here. I can take the x out from this guy, 1, 3, 0. I can take the z out from this guy, 0, 2, 1, and then 0, minus 6, 0. And so this first vector here, right,
this is going to be like my v. This guy is going to be my w, right? I'm using x and z instead of s and t, but you'll notice I still have this form here, right? So, and then this is my r naught here, right? Here is my r. And so I've got things into that same form that we saw on the previous slide. You know, r equals r naught plus s times v plus t times w. We've got it in that form. We just have to set x equal to s, z equal to t, and we've got it. Okay, moving right along. What about the equation of a plane containing 3 points? So for this one, we're going to have to, well, let's draw a diagram. Actually, let's not even bother to put axes in. P, Q, R, okay? So we've got 3 points that we know are in our plane. Well, once we have those 3 points, we can draw 2 vectors, right? We can say here's V, here's W. What are V and W? V is going to be the vector, well, I do head minus tail for the vector PQ. So coordinates for Q minus coordinates for P, minus 2 subtract 0, 3 minus 1, 5 minus 2, I get minus 2, 2, 3. W is going to be equal to, so I do coordinates of the head here are R, tail is P, so I do 1 minus 0 is 1, 1 minus 1 is 0, minus 3 subtract 2, I get minus 5. Okay, so now that we've got those 2 vectors, well, we can compute the cross product, and actually we're going to have to pause this momentarily. I will come back to this, but you're going to see a little interruption here. As we pause this, we're going to return with the rest. Okay, and we're back. Sorry for the interruption. All right, so let's continue with this example. We're trying to find the equation of a plane containing these 3 points. So far what we've done is we've found the vectors. So we found this vector v, so this is the vector from P to Q. We found this vector w, which is the vector from P to R. I've chosen to draw both vectors anchored at the same point P. You know, you can set this up however you want, right? Any 2 vectors will do as long as they're not parallel vectors. So we can go, you could do the vector from P to Q and the vector from Q to R. It doesn't matter as long as you get 2 points or 2 vectors which are parallel to the plane, right? And so any vector between any 2 points in the plane will be parallel to the plane. You might think that it matters. It seems like, you know, if you did see the vector from Q to R, you get something which is completely different from the 2 that are already there, and it seems like, you know, this should make a difference. If you're concerned, feel free to try this. You know, try it a couple different ways. See what happens if you choose different vectors, and you'll find that you end up with the same equation every time. And then you might want to think about why do you end up with the same equation every time. You can play around with these sorts of things. A lot of them can be understood if you kind of carefully study the properties of the cross product. And speaking of the cross product, that's what we need to find next, right? Because the normal vector, we know that the normal vector is going to be the cross product, v cross w. So I, j, k, minus 2, 2, 3, 1, 0, minus 5. Okay, so for the I component, we just have 2 times minus 5, and then it's 3 times 0. So that's minus 10 subtract 0, minus 10i. For the j component, minus 2 times minus 5, that's plus 10, and then minus 3. So we're doing 10 minus 3. So remember that minus sign for the j component, and then 10 minus 3 gives me 7j. And then for the k component, we're doing, well, that's 0, right? And then we're subtracting 2. So minus 2 times k. So our vector is minus 10, minus 7, minus 2. By the way, if you don't like all those minus signs, you can switch them, right? You can, any vector which is parallel to the normal vector will do. So if you want to use, you can use, you know, we can say, you know, let's actually say this is not what I want for my normal vector. I'm going to use the normal vector 10, 7, 2 because that's parallel. It's still going to work. So now that we got our normal vector, we can choose any one of the 3 points that we were given to begin with. I'm going to go with P. I've kind of anchored everything at P, and we can write down the equation of our plane. So our equation is going to be 10, 7, 2, dotted with, so x minus 0, y minus 1, z minus 2. That should be equal to 0. If we clean this up, we've got 10x plus 7y plus 2z equals, what are we going to get? There's a minus 7 equals 11, if you simplify that. Okay, good. So one more example on this video, and then we'll move on to the next one. So the last example we're going to do, equation of a plane containing intersecting lines. All right. Now notice we decided to be nice here. We chose 2 lines that are obviously intersecting, right? We've got that same point on both lines. Otherwise, you might have to first check to see, do these lines actually intersect? Because if they don't intersect, they don't lie in a common plane. And well, then you've got some work to do. By the way, if you want to give yourself a little bit of a challenge, think about how you would write down the equation of a plane containing parallel lines. We could work on that one as well. Maybe we ask me to do that one in class. If we have time, we'll do that as an example. All right. So we've got our 2 lines. We've got the equations for the 2 lines. How do we get the equation for our plane? So, well, we've got line 1. We've got line 2. We've got a point of intersection. So we might as well take that point of intersection to be our reference point on the plane. That's just going to be our point 1 minus 2, 0, right? And then we've got direction vectors for the 2 lines. V, W. Here is V. Here is W. They're just the direction vectors for the lines. And then we know how to calculate the normal vector. From those 2 lines, we calculate the cross product. So we go ahead and we calculate the cross product. V cross W. So as usual, we'll set this up as a little 3 by 3 array. So we have minus 2, 3, 1 for the vector V. We've got 3, minus 4, 2 for the vector W. And we compute this. So for the I component, we've got 3 times 2, that's 6. Subtract minus 4. 6 subtract minus 4, that's 6 plus 4. Gives us 10. I. Let's put that minus sign down right away for J so we don't forget it. And what do we have for J? We've got a minus 4, minus 3. So minus 7, so minus 7. So that's going to come out to be a plus 7. And for K, minus 2 times minus 4, that's 8 plus 8. Subtracting 3 times 3, 8 minus 9 gives me minus 1 times K, so minus K. So overall we get 10, 7, and minus 1 for our normal vector. Now that we've got our normal vector and our point, we know how to write down the equation of the plane. Our equation is going to be 10 times x minus 1 plus 7 times y, subtract minus 2, so y plus 2, minus 1 times, well, z minus 0, so just minus z equals to 0. And if we want to simplify that, and again, you don't have to, but you might want to, 10x plus 7y minus z is equal to 10 minus 14, minus 4. Okay, that's it for this video. In the next one, we'll look at some distance problems, finding distance between points and planes. All right, so this is the first video for chapter 4. So we're moving on now into sort of the algebra portion of Math 1410. We're moving away from the complex numbers, from the vector geometry, and we're moving into the actual algebra part. So we're going to do We're going to introduce matrices and look at the algebra of matrices, and we'll see that as with vectors, we can define addition, scalar multiplication. We'll also see that you can multiply matrices, which is not something you can do with vectors. I mean, there are certain vector products. There's a dot product, there's a cross product, but there's sort of a natural multiplication that you can define for matrices, and we'll be seeing that as well. But first, we'll just introduce the basic idea of what a matrix is. So a matrix is simply an array of numbers, okay? It's a rectangular array, so you take a bunch of numbers and you arrange them into some number of rows and columns. You can consider matrices over different sets of numbers. You can consider matrices with real entries, with complex entries, and so on. We will almost exclusively deal with matrices that have real number entries. So here are some examples of different matrices of various sizes. So this matrix A, for example, we can see that it has 2 rows. Okay, so the rows are the horizontal, the columns are vertical. So there's 2 rows, 3 columns. So this is a 2 by 3 matrix. 2 rows, 3 columns. In general, when you're specifying the size m by n, m refers to the number of rows, n refers to the number of columns. So B, we can see that B has 1, 2, 3 rows and 1, 2 columns. So this is a 3 by 2 matrix. The matrix C has 2 rows, 2 columns. It's a 2 by 2 matrix. This case, by the way, where the number of rows is equal to the number of columns, these are referred to as square matrices. So m is equal to n in this case, right? Both of them are equal to 2. So square matrices will be important later on. So there's language for them because square matrices have certain properties, and there are certain things that you can do with a square matrix that you can't do with other matrices. So if we want to refer to the particular entries of a matrix, we can talk about the ij entry. Okay, I'll use this notation. You'll also sometimes see this referred to as maybe the ijth entry. That's another term you might hear. It's, I don't know, this is sort of a mouthful, I think, ijth entry or ij entry. In any case, we're referring to the particular row and the particular column, right? So, for example, if I wanted to tell you the, say, two entry of A, well, that would be, so I would say I would go row 2, so row 1, row 2, row 1, row 2, column 1, column 2, column 3. So I go to the second row, second column. I'd see what number is there, and I see that I get a minus 2. Okay, and if I wanted to know what is the, let's say the 1, 3, that's not going to work. The 1, 2 entry of B is going to be, well, let's see, I go row 1, column 2, and there's a pi sitting there. So the 1, 2 entry of B is pi. In general, sort of general notation, we can write, say, aij for the ij entry of A. In this notation, one of the things you'll often say, okay, so you'd write A as sort of the matrix aij. We'll see this shorthand notation quite a bit. It simplifies a lot of the discussion. Okay, so why do you consider matrices? Why are they useful? Well, there are many applications where matrices come up. You don't have to search very hard to find applications of matrices. Well, a quick Google search for applications of matrices will, I'm sure, find you a number of examples. You'll find matrices in use for computer graphics. If you want to encode computer graphics, much of that is done using vectors and matrices. Any sort of data mining, data analytics, you'll see matrices in use there. Adjacency matrices for graphs and roads. I mean, this is an interesting one where maybe you have you've got a number of nodes with labels, maybe 1, 2, 3, something like this, and then you've got connections between the roads. So maybe the connections are just telling you how far. So maybe the 1, 2, 3 are labeling cities, and the connections are distances. So maybe the distance from 1 to 2 is, I don't know, 17 kilometers. The distance from 2 to 3 is 21 kilometers, and the distance from 1 to 3, maybe that's I don't know, 30 kilometers. And if you wanted to kind of keep track of all of this information, you could write down a matrix, and maybe you decorate that matrix, but you don't necessarily have to decorate it. So you can put your 1, 2, 3, 1, 2, 3, labeling the rows and columns. And in each entry, so the ij entry for this guy, here the ij entry is going to be the distance from I to j, right? So everything, of course, has distance 0 from itself, so you would get zeros down the diagonal, and then you see the distance from 1 to 2, well, that was 17. And then, of course, the distance from 1 to 2 should be the same thing as the distance from 2 to 1, so we get a 17 in both spots. The distance from 1 to 3 is 30, 30 down here as well, and then 21, 21. And so you can fill something out like this. And there might be scenarios where, maybe you're dealing with one-way streets, or, there might be, the way to get from 1 to 2 might be different from the way you get from 2 to 1, in which case maybe, this number and this number are not the same. I've drawn a scenario where you're dealing with two-way streets, so those numbers are the same. Or maybe this is not, distance on a road. Maybe this represents some kind of, different states of some system, and these are, I don't know, energy levels or something, and you increase by a certain amount going from 1 to 2, and then if you went back from 2 to 1, you would decrease, and so you would have, say, a plus 17 in one spot and minus 17 in the other spot. There are lots of possibilities where this might come up. Another big one, if you're ever curious, you might want to go and find some articles kind of explaining the basics of how the Google PageRank algorithm works. Now, there's a lot going on there. It's much more complicated than simple linear algebra, but there's a gigantic matrix with billions of entries that Google uses to keep track of how different websites are related to each other. Roughly speaking, this is a bit of a simplification, but this is one way of thinking about how Google does its things. There's a lot of sort of matrix arithmetic involved in things like air traffic control, things like this. And some of these are big problems. These are ones that you're not going to do by hand. You're going to use by a computer. And even with a computer, you might have to come up with very special algorithms to do things quite quickly. You can imagine that, Google search algorithm, right? Nobody's happy if it takes more than 2 seconds for the results to show up on the screen. Air traffic control, if you don't get to your answer quickly enough, then even worse things might happen. So essentially, you're using matrices to organize data, right? And you might be using matrices to kind of organize data that tells you about relationships, right? So you can see this in this adjacency matrix. These numbers are telling you about how different locations or different states are related, right? Distance between them, something like that. We can look at some other examples perhaps, but let's sort of introduce some general notation first. So as we mentioned, you can talk about the ij entry of a matrix. So this is something which is, remember, this means row I, column j, and so the rows are the horizontal guys. So you have row 1, row 2, down to row m. These are your rows, and then your columns are going across column 1, column 2, all the way across to column n. Those are your columns. And so often, and especially when you want to write down kind of definitions and proofs involving matrices, you know, in a later video we're going to talk about things like matrix addition, scalar multiplication, and you want to, you know, define these things, and you want to define them as generally as possible, right? You don't want to have to write out a big mess like this every time. It takes up too much room on the page. It's much nicer to simply write something like this. A equals Aij with the square brackets around there to tell you that you're talking about a matrix. And you know, sometimes you might want to decorate this notation. You might want to say put m by n if you want to specify the size, or maybe you want to be even more explicit. So you want to say it's, you know, a matrix Aij where like 1, so I goes from 1 to m, and j goes from 1 to n, something like that. But normally, once the context has been established, you don't really need all of this information. You can just use this sort of basic notation here. Okay. Moving right along. If we want to talk about matrices, we want to establish properties of matrices. Well, one of the things we need to be able to do is say what it means for two matrices to be equal. So, you know, when you think about equality, equality is something you're quite used to, right? If I wanted to write down a definition of what does it mean for two numbers to be equal, you would probably find it kind of silly to even bother, you know, explaining, you know, what does it mean to say that two numbers are equal? It means they're the same number. It's, you know, it's equality with numbers is something which is so natural we don't even really bother to define it. But once you get to something like a matrix, a brand new object, and you want to say, well, you know, you have to actually specify what it means for matrices to be equal. So, what does it mean to say that two matrices are equal? Well, first of all, they have to have the same size. And for two matrices of the same size, equality means that they have the exact same entries, right? So if I have two matrices A and B, so A, I write the entries of A as Aij, I write the entries of B as Bij. A and B have to have the same number of rows and the same number of columns, and if I choose a particular row and particular column, I have to find the same number sitting inside of the matrix A as I find inside of the matrix B. So, I mean, this is a pretty straightforward definition of what it means for two matrices to be equal. And of course, if all the numbers are filled out, this is kind of an obvious thing what that means. But we'll want to be solving equations involving matrices, and we want to be able to make definitions, and we want to say, you know, make a definition where we say that a certain matrix is defined as being equal to some expression involving other matrices. So we need this notion of what matrix equality is. Okay, so that's the basic idea of what a matrix is. We're going to continue in the next video to talk about addition and scalar multiplication. Okay, welcome back. This is the second screencast for Chapter 4 on matrix algebra. So now we're still in section 4.1. We're going to introduce the notions of matrix addition and scalar multiplication. And if you remember how things go with vectors, you'll find this pretty straightforward. The way of adding matrices and the way of multiplying by a scalar is exactly the same way that you did it for vectors, right? To add vectors, you added the corresponding entries, and it's going to be exactly the same story for matrices. So you want to add two matrices together. Well, the first thing is they've got to be the same size, right? Think about when you're dealing with vectors. It wouldn't make sense to add a two-dimensional vector to a three-dimensional vector. The two vectors have to belong to the same space. They have to have the same number of entries. And same thing for matrices. If I want to add two matrices together, they have to be the same size. And once I have two matrices of the same size, how do I add them together? I simply add the corresponding entries. So if A has entries Aij, B has entries Bij, then the sum is obtained by simply adding those numbers together. Here you see why this notation, this index notation, is quite useful. Writing A in terms of entries instead of writing Aij, rather than kind of writing this thing out in full. If I wanted to define A plus B, writing out my matrix in full, it would take up the whole page if I was trying to do it quite generally, right? So what does that mean in practice? Well, it means if I wanted to do, say, A plus B, I check, okay, so A is, what's the size of A? A is it's got 2 rows, 3 columns. A is a 2 by 3 matrix. B is a 2 by 3 matrix. They're both the same size, so I can add them. So 1, minus 2, 3, 0, minus 4, 2, minus 3, 0, 1, 0, minus 3, 2. And my rule says that the way I define this sum is I simply add the corresponding entries. So 1 plus minus 3, minus 2 plus 0, 3 plus 1, 0 plus 0, minus 4 plus minus 3, 2 plus 2. Okay, so I add the 1, 1 entry, so the 1, 1 entry for A is a 1. Right here, the 1, 1 entry for B is a minus 3, and adding those together gives me the 1, 1 entry for A plus B. Similarly, the 1, 2 entry for A, minus 2, 1, 2 entry for B is a 0. Adding them together gives me the 1, 2 entry for the sum, and so on. So then, to simplify, I simply carry out these additions. Minus 2, 4, 0, minus 7, 4, and you'll notice that the result is the same size as the two matrices you put in. There's a third matrix C there. I could try to talk about addition involving the matrix C, but there's not much I can do, right? A plus C, B plus C, those are undefined, right? Because C is a 2 by 2 matrix, and so it does not make sense to add C to either A or B, right? If you try to sort of do A plus C, you'd look at those numbers in the third column, you know, this 3 and that 2, and you'd say, well, what do I add them to from the matrix C? I need a corresponding entry in the other matrix to add to those guys, and nothing is there. And so you simply just don't define that. But the only thing you could do is C. I guess you could add C to itself. You could do C plus C, you could do that. And in fact, you can see what you would get. You would get, well, 1 plus 1, minus 2, minus 2, 2 plus 2, 4 plus 4. So you double everything. 1 plus 1 gives you 2, minus 2 minus 2 gives you minus 4, 2 plus 2, 4, 4 plus 4 gives you 8. And you might guess that, you know, there should be some sort of operation, some scalar multiplication operation that would allow you to say that this is equal to 2 times C. And we'll see that indeed that is the case. We'll be there pretty soon. But we got to finish our discussion of addition first. So let's move forward. What sort of properties does this matrix addition have? I'm listing them all here. I'm not going to go through the proofs. We can do a couple of them if you're interested in. You can ask Jeff to do them in the tutorials if you want. The addition of matrices satisfies most of the properties that you expect it to satisfy. Okay, you have a commutative law telling you that the order in which you add your matrices does not matter. A plus B is the same thing as B plus A. If you want to extend the definition of addition to sums of 3 or more matrices, then you need to have an associative law. You need to know that it doesn't matter how you group those matrices together, you will always get the same answer, right? So this associative law is what tells you that simply writing A plus B plus C is unambiguous. Right. You can interpret that either as first doing A plus B and then C, or you could interpret it as doing B plus C and then adding A. You'll get the same answer either way. Okay. The zero matrix, as you might expect, the zero matrix is the matrix whose entries are all 0. Okay, so Aij equals 0 for each I and each j. The zero matrix, well, if you just look at the definition of matrix addition here, right, if B is the zero matrix, if all of the B's are equal to 0, then when I do A plus B, I'd be adding 0 to each of the entries for A, and I know that adding 0 does nothing. So adding the zero matrix doesn't do anything, right? So 0 acts as an identity element. Adding 0 doesn't do anything. So A plus 0 is equal to A, no matter what the matrix A is. And You can define the negative of a matrix by simply flipping the sign of each entry in the matrix, and as you might expect, adding a matrix to its negative, everything cancels out, and so you get 0. And one of the reasons that you want to define a negative is that once you've defined negatives, you can then define subtraction. So the way you define a minus b is you say, well, a minus b is the same thing as adding the negative of b to a. So a minus b is a plus the negative of b. This is how you define subtraction. Very much the same as you do when you're dealing with real numbers. And by the way, if you wanted to prove some of these, let's say you wanted to prove the commutative law. Let's say we want to do this guy, right? So if you wanted to write out a proof, and obviously I don't have room to write everything down, and I should be kind of trying to write things out in full sentences, but if I said, okay, let me let a equal to aij, and let me let b equal to bij, right? Then I'd say, well, a plus b, I know by definition, is aij plus bij. And the reason why the commutative law holds is that the commutative law holds for numbers, right? Aij plus bij, each within the matrix, I'm adding numbers. I'm adding the ij entry from A to the ij entry from B. This is a sum of numbers. And I know that order of addition doesn't matter for real numbers, so aij plus bij is the same thing as bij plus aij. And then I simply reverse the definition of addition to say, well, this is by definition b plus a. Okay, and similar arguments can be used to establish the other properties here. Okay, all right. Let's do a computational example just to kind of play around with things, see how this works. So if I wanted to do a minus b, I would say, okay, that's the same thing as a plus minus b. You don't have to do it this way. You can simply, as you might expect, subtracting matrices means subtracting corresponding entries. But one of the ways to make it less likely that you're going to make a sign error, because each of these matrices has 6 entries, and that means 6 opportunities to mess up with a minus sign. You might want to actually sort of first switch the sign and then add. So if I want to form this matrix minus b, I have to go into the matrix b and I have to swap all of the signs. So I have a minus 1. So I start with 1, minus 1, 1, 0, 2, 4. That's b, but then I switch all the signs. So I get a minus 1. This becomes plus 1, minus 1. Well, minus 0 is still 0. Minus 2, minus 4. So I swap all the signs and then I add. So 3 plus minus 1 gives me 2, minus 1 plus 1 gives me a 0, 0 plus minus 1, minus 1, 2 plus 0, 0, 4, minus 2 is 2, minus 5, minus 4 gives me minus 9. Oh, what happened here? That's not right, is it? 2 plus 0. 2 plus 0 is 2, it's not 0. Okay. So we've done the subtraction, a minus b. If I wanted to do a plus c, well, we've already gone over that. We add the corresponding entries. So maybe we'll just sort of jump ahead, add the entries. So 3 plus 1, minus 3, 0 plus 2, 2 plus 5, 4 plus 0, minus 5 plus 4. And that's going to give me 4, minus 4, 2, 7, 4, minus 1. If I wanted to do the last one, a plus b minus c, I might do it as, let's do it this way. Let's do it as a added to b minus c. So I'm going to do it like this. There are a number of ways that we could do this, but here's how I want to do it. I'm going to write down a. And then I'm going to do b minus c. So what is b minus c? 1 minus 1, minus 1 subtract minus 3, 1 minus 2, 0 minus 5, 2 minus 0, 4 minus 4. Okay? So this is b minus c. So I've done the entries of b and I subtracted off the entries for c. So that's going to give me 3 minus 1, 0, 2, 4, minus 5, added to 0, minus 4, minus 1, minus 5, 2, 0. So I add those together. Let me put it up here. So let's kind of wall things off. I'm going to get, so 3 plus 0, 3 minus 1 minus 4, minus 5, 0 minus 1, 2 minus 5 is minus 3, 4 plus 2 is 6, minus 5 plus 0, minus 5. Okay, so far so good. Let's talk, well, let's do one more example. I thought we were on scalar multiplication, getting ahead of myself. Okay, let's say I want to find this matrix X. How do I solve for X? Well, we know how this story goes. We've seen examples like this with vectors, with complex numbers. If this is A and this is B, right? So I have A plus X is equal to B. Then I should say, well, I add minus A to both sides. Minus A plus X is equal to minus A plus B. So I add the same thing to both sides. And so I know that if I group things together here, those A's are going to cancel out. Minus A plus A gives me 0. Adding 0 to X just gives me X. So X is equal to B minus A. So X is going to be 5 minus 7, 0, minus 3, subtract 2, 4, minus 1, 3. And so I've got 5 minus 2 is 3. 7 minus 7 subtract 4, negative 11. 0 minus minus 1, make sure you get that double negative, plus 1. Minus 3 subtract 3, minus 6. That's your X. And if you want, you can go back and check that if you do add this matrix to 4 minus 1, 3, you end up with the matrix 5 minus 7, 0, minus 3. Right? As usual, there are ways of checking your work. Okay, last up for this video, scalar multiplication. Again, defined exactly the way you expect. If you want to multiply a matrix by a scalar, you just multiply every entry in that matrix by that scalar, right? So in almost all the problems that we're going to do, scalar means real number. We're working with matrices with real entries, so scalars are real numbers. And we know how this works, right? It's the same way we did scalar multiplication for vectors. So for example, if I wanted to do, let's say, 3 times the matrix minus 1, 2, 4, 0, I would say, well, it's 3 times minus 1, 3 times 2, 3 times 4, 3 times 0, minus 3, 6, 12, 0. Okay, so scalar multiplication is what you expect. You just multiply every entry in the matrix by that scalar. And scalar multiplication satisfies a lot of the properties you might expect scalar multiplication to satisfy. One thing you'll notice is, well, because you're just multiplying each entry in the matrix by a scalar, you're not changing the number of rows or columns, so scalar multiplication preserves the size of your matrix. And well, if you multiply by the scalar 0, then of course everything multiplied by 0 just becomes 0 and you end up with the 0 matrix, right? So multiplying A by 0 gives you 0. And also if you start with the 0 matrix, it doesn't matter what scalar you multiply by, you're still going to have the 0 matrix. And you can turn that around and you can say, well, if I had a product equal to 0, if I had, like k times a equals 0, then I conclude that either k is 0 or a is 0. Often where that comes in handy is you end up somewhere where you've concluded that, let's say, 2a equals 0, and then from there you can get rid of the 2 and say, well, then I must know that a equals 0. So scalar multiplication, as with vectors, satisfies distributive properties, and as with vectors there are two, because this plus sign here is matrix addition, right, as it is here. And here, this plus sign here is addition in are, right? You're adding the scalars together. That's why there's two different distributive properties, because one is distribution over matrix addition, the other is distribution over scalar addition. And as usual, this second one is what allows you to group like terms, right? So this would tell you that, for example, if I had 3a plus 4a, that's 3 plus 4a, so I get 7a, as you would expect. Okay, and multiplying by 1 doesn't do anything, and if you want to multiply by one scalar and then another, that's the same as multiplying the scalars together and then multiplying by a, right? So these are all exactly the same properties for addition and scalar multiplication that we saw for vectors. And in fact, if you were kind of doing abstract linear algebra, you might say, well, that the set of all matrices of a particular size is what's called a vector space. It satisfies the same rules as algebra for vectors. So you say, well, this algebra is the same as vector algebra, and so you in some ways you can treat them as vectors, as a certain type of vectors. But that's not an approach that we take in this course. For us, vector spaces are generally going to be vectors in Rn the way we've usually been thinking about them. Okay, that's it for matrices. We'll be looking at vectors again in the next few videos. Only this time we're going to be changing notation. We're going to be thinking of vectors as either row vectors or column vectors. So a vector will be either a 1 by n or an n by 1 matrix. So we'll be thinking of vectors as special types of matrices going forward from here, starting in the next video. Alright, so we're ready to move on to the next section in Chapter 4, Section 4.2, which is on vectors in n dimensions. So this is a generalization of the vectors that we considered in 2 and 3 dimensions back in Chapter 3 to any number of variables. And the reason we're doing this here is we want to view n-dimensional vectors as being a special case of matrices. And so we introduced matrices in section 4.1. We went over those in the last couple of videos. And one of the kind of big shifts we'll do here, there's two shifts we're going to make. One is allowing for any number of variables. The other shift we're going to make is a shift in notation. So in chapter 3, we used angle brackets to denote our vectors. Right, and so we had kind of this. So in chapter 3, we said, something like, maybe x, the vector x looks like maybe x1, x2, x3. In chapter 4, when we want to write that same vector, we're going to think of it as an n by 1 matrix, as a column vector, right? So it's a single column, some number of rows and only one column. So this would be a 3 by 1 matrix. And we'll see that this is going to be a useful notational shift for us, because it's going to allow us to use matrices to describe systems of equations, write systems in matrix form. It's going to allow us to talk about how matrices define functions that take vectors to other vectors. And so it's going to be a much more useful notation for us. We mentioned back in chapter 3 that the main advantage of the angle bracket notation is that it fits a little bit better on the page. Okay, so there are two types of vectors that we run into: row vectors, column vectors. Row vectors we don't see that much of. So a row vector would be something that looks like, say, maybe x equals x1, x2, down to, say, xn. Right, so it's a 1 by n matrix, right? One row, n columns. A column vector, maybe we'll call this guy y. You have several rows, but only one column. So you have a y1, y2, down to, let's say, ym. Oh, I said n by 1 on the slide, so let's stick with n. N. Okay. So, of course, you can see that both of these give you the same information, right? If I gave you, so let's just make this as a note. If I gave you the vector x equal to, say, 2,
So 2 minus 1, 4. Y equal to 2 minus 1, 4. Well, these give me the exact same information, right? They give me the same three numbers, simply presented in different ways. And depending on the context, you may want to present these numbers in one way or another. But most of the time, we'll be dealing with column vectors. There are very few places where we want to deal with row vectors. In more advanced courses, you might think of row vectors as being somehow dual to column vectors. But that's far beyond what we would talk about in a course like 1410. Okay. All right, a few more examples. We could do say column vectors in let's do four-dimensional vectors. Why not? We could do say u equals 2 minus 1, 3, 4. V equals 0, 1, 0, 2, and so on. We could do rows in let's get really crazy. Let's do R7, right? We could do X equals 1, 2, 4, 0, minus 5, 6, 1. There's 7 numbers, right? Y equals minus 1, 2, 0, 1, 3, 4, 2. Right? So there's nothing all that tricky here. It's simply a matter of either you take a bunch of numbers, you write them as rows, or you write them as columns, whichever way you want to do it. One more example. Let's say these are going to be in R3, right? 3 numbers. We'll do columns. We might do something like, let's say, A is going to be, they don't have to be integer entries. 2/3, 1 plus the square root of 2, 0. That's a perfectly good three-dimensional vector. Right? We can put whatever we want in these guys. Any real numbers we can stick into these vectors. You can even put complex numbers in them if you want, but that's not something that we're going to spend very much time on. Okay. Now, because these guys are special cases of matrices, they satisfy the same properties as matrices, and we saw these in the previous video, right? So we know that x plus y is the same thing as y plus x for any matrices, so in particular for any vectors. We've seen this before. We know that addition is associative. We know that there's a 0 vector, so x plus the 0 vector is going to be equal to equal to x, where our 0 vector, we know what the 0 vector looks like. The 0 vector looks like, if we're dealing with, well, here I've said vectors, but really I guess I should say, let's do column vectors, but it's equally true for row vectors. So 0 being the vector consisting entirely of zeros. Negatives, we know that negatives work. X plus minus x equals the 0 vector, and as usual, we know that minus x is just minus x1 down to minus xn. You just change the sign on each one of the entries. It's still true that if you multiply by the scalar 1, nothing happens. Scalar multiplication is associative. C times dx is the same thing as c dx. And we have two distributive properties, right? We know that if I do c times x plus y, that's cx plus cy. And if I do c plus d times x, that's equal to cx plus dx. Okay, so you have all the usual properties. These 8 properties, by the way, in sort of a more general context where these vectors, maybe they're column vectors, maybe they're row vectors, maybe they're matrices. There are other scenarios where these things apply. You might be dealing with, you could deal with functions, polynomials. There's all sorts of things. These 8 rules collectively are known as the
as the vector space axioms. And there are lots of other sorts of sets that behave algebraically in the same way that row vectors and column vectors behave. And if you go on and you take a course like 3410, you will see this sort of general picture developed there. Okay, so as I mentioned, vector space, you have sort of any set of objects where you have an addition and you have a scalar multiplication and they obey these rules. So we've seen some examples, right? We've seen, well, we know that this works for row vectors. We know that it works for column vectors. We know that it works in general for matrices of a given size, right? Other examples might be things like you could do something like this. You could do, say, we'll use this notation, P3 of R. The set of all polynomials of degree 3 or less, so things that look like a0 plus a1x plus a2x squared plus a3x cubed, where all of these a's are real numbers. That also works as an example of a vector space. You can play around with that and see that it works. You could consider, the set of all. You consider the set of all functions. Maybe functions defined on maybe some interval a/b. Real valued functions defined on some interval. Lots of possibilities, but for us, the only real one that we are going to work with is the case of column vectors, and occasionally matrices. And if you want to consider vector spaces in general, you can study those in Math 3410 once you're done with this course. Okay, that's it for this. In the next couple of videos, we're going to be getting a little bit more abstract. We're going to be talking about some of the kind of inherent properties of vector spaces, things like subspaces, span, linear independence. These are concepts that a lot of students find kind of tricky. They are some of the more difficult concepts that we consider in this course, but they're concepts that we'll return to a number of times, and hopefully with repeated exposure, by the end of the course, you guys will have the hang of these things. All right, so this is the first of several videos on the material in section 4.2 of the textbook on some of the sort of algebraic theory of vectors in n dimensions. So there are going to be several concepts that we're going to introduce over the next few videos, and they're all fairly abstract theoretical concepts, and they're ideas that take a little bit of time to get the hang of, so don't worry if the first time you see it you don't quite understand what's going on or you don't get it immediately. It takes time to get the hang of these things. So we're going to introduce subspaces in this video. In the next one we're going to talk about span, after that linear independence, and finally basis. Right now we're just going to introduce these ideas conceptually. We're not going to do very much with them because in order to kind of handle things computationally, you need techniques for solving systems of equations, which is coming up in chapter 5. So before we get to solving systems, we're just going to introduce these ideas, and then we're going to come back to them again once we have techniques for solving systems. We're going to come back to these ideas 2 or 3 times in the hopes that by the third time you'll be familiar enough with these concepts that you kind of get a feel for what's going on. It helps going through this material to have some good geometric intuition for what's happening, which is why we've already kind of gone over vectors in R3 and vector geometry. We'll see that for this topic of subspaces in 3 dimensions, the main examples you want to keep in mind for subspaces of R3 are going to be lines through the origin and planes through the origin. You explored this somewhat on your second assignment, the last problem on the second assignment. Essentially what that second assignment was asking you to do was to establish that lines and planes through the origin are indeed subspaces. We'll see that as we move forward through this video. Okay, so what is a subspace? So a subspace, first of all, is a subset. set. So remember, subsets were introduced way back in chapter 1. It was considered some of our review material. We covered this in the very first week. A subset is just, some collection of objects which is contained within a larger set. So in this case, our large set is Rn. And so when we say that U is a subset of Rn, we mean that U is some collection of vectors or points in Rn, depending on how you want to view things, but we're going to view elements of Rn here as vectors. So it's some collection of vectors. They're all n-dimensional vectors, but we're not necessarily considering all possible vectors in Rn, only some vectors in Rn. And what makes a subset a subspace is if if you look at those vectors in that subset and you check all of these 8 axioms for a vector space, right? The associativity of addition, commutativity of addition, existence of zero, distributive properties, all of these guys, that those properties hold when you apply them only to the vectors in the subset and not to Rn as a whole. And so it turns out that most of those properties are sort of automatic because you're using the same addition and the same scalar multiplication. We should probably specify that when we say that it satisfies the 8 vector space properties, we've already defined what it means to add vectors in Rn and to multiply a vector by a scalar in Rn. We're using the same addition and the same scalar multiplication. We're just not adding all possible vectors. We're only adding some vectors. And it turns out that the only thing that can really go wrong is that you add 2 vectors that are in your subset and you end up with something that is no longer in the subset, or you multiply by a scalar and you get something which is no longer in the subset. So there's one kind of base condition, which is that U has to be non-empty. And that means that it has to have at least one element. There has to be at least one vector in there. And usually what we do, because we know that every vector space needs to contain a 0 element, generally what we do here is we check that the 0 vector belongs to U. So if the 0 vector is in there, then we know that there's at least one vector in there, so it's not empty. And the 0 vector is a good one to check because it has to be in there. The next one is that U is so-called closed under addition, and U is closed under scalar multiplication. What do these closure properties mean? So property 2 just means that if U and V are vectors in U, then U plus V is also a vector in U. 3 means that if U is in U and C is any scalar, then C times U has to be in U. Okay, so if you have one vector in there, then you have to have every scalar multiple of that vector has to also be in the set. Okay, so this is basically what the third condition is saying. So one of the things that tells you, just kind of think about the three-dimensional picture. If you have one vector that's in there, right? So there's, say, your U, right? Then every scalar multiple of U has to be in there. So we can multiply by positive scalars and get other vectors that are in this direction, right? We can multiply by negative scalars, get vectors that are in that direction. It means that, well, basically, the position vector for every single point on that line through the origin in the direction of U has to be included in the subspace. So if U belongs to the subspace, then every point along that line in the direction of U also belongs to the subspace. And then if you were to add another vector V, right? So let's say I threw in a V,
b is here, right? Well, then u plus v would have to be in there, so we would do our tip to tail rule. U plus v has to be in there. Well, in fact, u plus v has to be in there, but also any scalar multiple of u has to be in there. Any scalar multiple of v has to be in there, and so that would mean that in fact, any linear combination, anything that looks like, say, a times u plus b times v, would have to be in there. And so if there's a second vector v in there, then in fact what you would get is you would get the entire plane that contains those two vectors, right? And that would be your subspace in that case. So we'll explore these ideas going forward. All right. So first thing we're going to do is we're going to just check to see, okay, here are some subspaces, right? We're going to define some sets, some subsets of vectors in R2, and we want to understand whether or not these guys are subspaces. So the first one is a set of all vectors of the form x and x squared. So in other words, what we're saying here is that if v equals xy, and that's an element of say u, implies y must be equal to the square of x. So we might ask, okay, is that guy a subspace? Well, we can see that the zero vector belongs to the set. So no problems there, right? I can set x equal to 0 and I get the vector 0, 0. Is it closed under addition and scalar multiplication? Well, let's consider. We could consider the vector 1, 1. That belongs to u, right? Because 1 squared is equal to 1. But if I did 2 times 1, 1, that would be 2, 2, right? That does not belong to my set because, well, why not? 2 squared is not equal to 2. We know that. 2 squared is equal to 4. And so we've just given an example of a scalar multiple which doesn't belong to this set, and that guarantees that this can't be a subspace, right? Because it's not closed under scalar multiplication. Now, what about the next set? Set of all vectors such that x plus 2y equals 1. Well, we know what that looks like kind of graphically. If we think of vectors, if we identify vectors with points, then what we're dealing with here is we're dealing with a line, right? This is basically a line, x plus 2y equals 1. Right? And one of the things you'll notice about this line is that it doesn't pass through the origin, right? 0 plus 2 times 0 is equal to 0, not equal to 1. So the 0 vector is not in my subspace, and if the 0 vector is in there, it can't possibly be a subspace. So that means that this is not a subspace, right? And same here, this is not a subspace. All right, what about our last example? Set of vectors of the form 2t and minus 3t. Well, one thing you might notice off the bat, and this will be a useful observation going forward into the next video, is that a vector of the form 2t and minus 3t, we can write that as simply t times v, where v is the vector 2 minus 3, right? Okay, so now if I had, say, 2, well, first of all, we notice that t equals 0 gives the 0 vector in u. And if so if I had 2 vectors, say u1 equals t1v, u2 equals t2v, if they belong to u, well, that would imply that u1 plus u2, so that's t1 times v plus t2 times v. I can factor out the v. I can write that as t1 plus t2
times v. It's still of this form, scalar times v, right? So in this case, t, this would be t, right? T would be equal to t1 plus t2 in this case, right? If t1 is a real number, t2 is a real number, then t1 plus t2 is also a real number, and the condition here says t could be any real number, and so that means that this sum also belongs to you. And then similarly, you could check that, it's closed under scalar multiplication. Why is it closed under scalar multiplication? Well, if I did say c times tv, that's equal to ct times v, right? And so then again, c times t is going to be a real number, so c times t all multiplied by v, that is something of the proper form. And that tells you that your set is closed under scalar multiplication as well. So this guy is a subspace. All right. Notice that that in this case, our subspace, it's the set of all scalar multiples of a single vector. That's going to be a very kind of common observation for a lot of subspaces. This would be an example of what we might refer to as a one-dimensional subspace, because there's one vector that generates the entire set, right? This vector v, every other vector in the set can be written as a multiple of v. So there's one vector that kind of produces every other vector. Okay. So here's another example. What if we had two vectors? So that final subspace example we just dealt with, there was a single vector that generated the entire set. What if I had two vectors generating the set, right? Now, I'm not saying anything about what these vectors are, but let's suppose I have these two vectors. I'm going to consider the set of all vectors of the form a times x plus b times y, so all possible linear combinations of these guys. We want to show that this is a subspace. So let's call this set, we'll call this set U. And so we check. So first of all, if I set a and b equal to 0, well, that's going to give me the 0 vector. All right, so the 0 vector is an element of U. And now let's suppose that I have, let's say v is, let's say ax plus by in U, and w is, let's say, cx plus dy in U, right? So a, b, c, d here, all scalars, right? So in this set U, I can choose any values that I want for these scalars a and b. So c and d might be different from a and b. And what do I get for v plus w? So I start with ax plus by, cx plus dy, right? But using the properties of vector algebra, I know that I can rearrange this equation. I can group things together. I can write this as a plus c times x, and then b plus d times y. And this guy is again going to be a real number. This guy is going to be a real number. And that tells me that this is an element of U. And finally, we can also notice that if I do say k times v, that's k times ax plus by. And if I distribute the scalar multiplication and group things together, I can write that as ka times x and kb times y. And again, k is a real number, a is a real number, so k times a is a real number. This is a real number, and that tells me that this is also an element of my subspace. Okay, so that tells us that this set is indeed a subspace. So any set that is kind of generated in this way by considering kind of every vector that's generated by those two vectors is going to be a subspace. And if you think back to chapter 3, remember when we presented the vector equation for a plane in 3 dimensions, you might notice that what you have here is in fact a plane that passes through
the origin, right? If you think of a plane described in terms of its vector equation, you would get all possible points that are of this form, right, for two vectors, x and y. Okay, so a plane through the origin also looks like a subspace. These types of sets, we'll talk about this in the next video. The way we might describe this is we say, well, this set here is what's called a span. This is the span of the vectors x and y. And it will be true in general that the span of any collection of vectors is a subspace, and we'll explore that in the next video. All right, so welcome back to this series of video lectures for Math 1410, Linear Algebra. In the previous video, we introduced the concept of a subspace of Rn, so a collection of vectors within Rn that viewed as a whole behave like a subspace. So the idea with a subspace is, you want to think of a subspace as sort of like this. So if U in Rn is a subspace, you want to think of this as sort of being like a copy of R, let's say K, inside of Rn, where K here is less than or equal to n, right? So like if you have a line through the origin, a line is like a copy of R. A plane is like a copy of R2, right? So subspaces are basically like copies of lower dimensional Rn's sitting inside of a higher dimensional space, but they might be oriented at some funny angle. It's not necessarily, let's say, a coordinate axis or a coordinate plane. It could be any line or plane that passes through the origin. And the final example in the last video showed that one of the ways you can generate a subspace is by considering the set of all vectors that are generated by a pair of vectors using addition and scalar multiplication. This sort of operation, this is what's called a linear combination, and we'll see that in general, linear combinations are what allow you to generate subspaces. Okay, so what is kind of the proper definition of a linear combination? A linear combination is really just any expression that can be written like this. So if we wanted to say that the vector v is a linear combination of the vectors v1 up to vk, what we're saying here is that we can find scalars c1, c2 up to ck that satisfy this equation, right? So we would say, so the way you would read this is you would say v is a linear combination of these vectors v1 up to vk. So that's the context in which you would discuss a linear combination. And of course, if you have a bunch of vectors, you can form a linear combination. So for example, let's say v1 looks like, say, 2 minus 1, 0, 3. Maybe v2 looks like 0, 2, 5 minus 4. v3 is equal to minus 1, 0, 1, 3. Right? So a linear combination could be something of the form, let's say v is equal to 2v1 minus 3v2 plus 4v3, right? So the 2 here, the 2 is like your c1, the minus 3 is your c2, and the 4 is your c3 in this case. And of course you can simplify this expression. So what does this work out to? Well, 2 times v1 would be 4 minus 2, 0, 6. Minus 3 times v2 would be 0, minus 6, minus 15, and 12. And 4 times v3, I get minus 4, 0, 4, 12. And I can add those together. I would get 0, minus 8, minus 11, and 30. Right? So this is my vector v, right? This is v. V is this guy here, right? And
what I've done is I've shown that this vector v, the vectors 0, minus 8, minus 11, and 30, can be written in terms of the vectors v1, v2, v3. Now, going in this direction, of course, this direction is easy. If you're given the vectors and you're given the scalars, we know how to do scalar multiplication. We know how to do addition, so it's not that hard to construct the vector v. The more challenging problem is going in the other direction, working backwards. If I give you the vectors, if I give you v, and I give you v1, v2, and v3, can you figure out these scalars, right? So if I give you the vectors, can I figure out what these values are, c1, c2, c3? Can I determine those values that satisfy this equation? That's a much harder problem. That leads us into the territory of solving systems of equations, and when we explore that in the next chapter, we'll find that, well, in some cases, the answer is that it just can't be done. There are no values. And in some cases, you will find exactly one set of values that work. And in other cases, you will find that there are, in fact, infinitely many possible choices of values that you could make for those scalars that works out. So the reverse problem is much more difficult. Kind of, reverse engineering this to recover the scalars. This is sort of a much more involved algebra problem, and it's something that we'll explore later on in the course. All right. So once you understand what linear combinations are, you can sort of consider linear combinations in the abstract, and you can say, well, what if I, instead of just considering one set of numbers to form a single linear combination, what if I consider all possible choices for those c's? I consider all possible choices for my scalars. I consider all possible linear combinations. This is what the span is. So the span, so the notation we'd use is this. The span of the set of vectors, say v1 up to vk, okay, would be equal to, so it would be the set of all vectors of the form c1 times v1 plus c2 times v2 and so on down to ck times vk, right, where c1, c2, ck, these guys are real numbers, right? So it's all vectors. So this is some vector, right? This is my v. So it's all possible vectors v that you can create by forming linear combinations of the vectors v1, v2 up to vk. Right. And so this is what a span is. And we've seen some examples of span. We've seen that the span of a single vector looks like a line. The span of two vectors looks like a plane. We'll keep these examples in mind as we go forward. So if we were doing a quick example, say we wanted this span of the vectors, maybe 2, 0, minus 3, 1, 0, 4. So that would be the set of all things that would look like, say, s times 2, 0, minus 3 plus t times 1, 0, 4, where s and t are real numbers. So that would look like, all vectors of the form 2s plus t, and then a 0 in the middle, and then minus 3s plus 4t, where s and t are real numbers, right? So with a set like this, if somebody handed you a vector and you wanted to figure out whether or not it had any chance of belonging to that span, well, there's one easy thing you would check in this case, right? Is that middle component of your vector, is it equal to 0? If it's not equal to 0, there's no way that it could possibly be written as a linear combination of these two vectors, because anything that's written as a linear combination of these two vectors ends up with that 0 in the middle spot. But in many cases, it's not quite so easy to tell if a given vector is in the span. Okay. So here's another example. Here's a pair of vectors. What does the span of u look like? So the span of u. So here we're dealing with just a single vector, right? So that would be all things that simply look like, say, t times u, where t is a real number, right? So if you only have one vector, a linear combination involving a single vector is simply a scalar multiple of that vector, right? So here you get all things that just look like 2t minus t and 4t, where t is a real number. And we know that what this would look like if we were trying to sort of plot it is, so u would be a vector kind of, maybe u is say like that. And the set of all scalar multiples of u would simply be a line passing through the origin in the direction of u. So that's what the span of u would look like. For the span of u and v, so then we're looking at all things that look like, let's say, s times u plus t times v, where s and t are real numbers. So this time we get things that look like 2s minus t minus s plus 3t, 4s plus t, where s and t are real numbers. So what I've done there, just to kind of, let me fill in one more step there, right? S times u, if I take the vector u and I multiply by the scalar s, I have 2s minus s, 4s. If I do t times v, I have minus t, 3t, and t. So s and t here are real numbers. One of the skills that you're going to need to develop going forward through some of this material is the ability to kind of go back and forth here. So if I give you the two vectors u and v, you want to be able to write down a general linear combination like this as a single vector. In other cases, you might be given that vector, you're given the single vector like that, and you need to kind of reverse the steps here. Take this vector, which involves these two parameters s and t, split it up into a pair of vectors, one which only involves s, one which only involves t, and then as a final step, factor out the s here, write it as s times the vector u, and factor out the t from here and write it as t times the vector v. That's sort of a computation that you're going to find yourself doing frequently moving forward. Okay. So in general, if I have a collection of vectors, I have a span of a bunch of vectors. I claim that this is a subspace, and the proof is actually it's the same as the argument we gave in the previous video. And so basically, I think we maybe don't want to go through all the details, but let's sort of sketch things out. How do we show it's a subspace? So remember, so if v is an element of v, so that's equivalent to saying v looks like, say, a1 v1 plus a2 v2 down to ak vk for some scalars a1, a2 up to ak, and maybe I have a second vector w. Let's throw another vector w in there. So if w is in there, then we know that w can also be written as a linear combination, but it's a different vector, so probably it's going to involve different scalars. So we'll call those ones b1 up to bk. Okay. So one thing you might notice is that if I put a1 equals 0, a2 equals 0, if I put all of the a's equal to 0, that would tell me that 0, the 0 vector, belongs to v. Right? So I know that the 0 vector is in there. Remember, that's the first thing you generally check when you want to make sure that you've got a subspace. And now if I take a general v and w, so the a's aren't necessarily 0 anymore, if I do v plus w, well, you can see what happens if I add them, right? I'm going to add the v1 terms. I'm going to get av1 plus bv1, and I can factor with the v1 and just write that as a1 plus b1 all times v1, and then I do it for v2 all the way down to vk, and so I'm going to get something that looks like this: a1 plus b1 times v1 all the way down to ak plus bk times vk. And again, that's this is a linear combination of the v's because I've got my vectors v and they're all multiplied by scalars. And if I were doing, say, k times v for some scalar k, if I simplify that, I'm going to get, ka1 v1 down to ka. I guess I shouldn't have used k. I've got a k here. All right. What's a letter I haven't used? I haven't used c. Let's use c. C times v. C times a1 down to c times ak times vk. And again, that's of the desired form. And so this tells you that your set v, it contains a zero vector, so it's non-empty. It's closed under addition. It's closed under scalar multiplication. And so you know that it has to be a subspace. Okay, so let's end with one example. How do I show that this set is a subspace? If I can show that this set can be written as a span, then I know that it is a subspace. So what we do here is we say, all right, so here's my solution. If v is sort of any vector in v, then I know that I can write v as x, y, and then 2x minus 3y for some real numbers x and y. But that tells me that I could write v as, so I'm going to split it up like this. It's going to be x, I'm going to do x, 0, and then 2x plus 0, y, minus 3y. Right, so in the first vector, I put everything that depends on x. In the second vector, I put everything that depends on y. And now I can write this as x times 1, 0, 2. And I can write this as y times 0, 1, minus 3. And what that tells me is that v belongs to the span of the vectors 1, 0, 2 and 0, 1, minus 3, right? And in fact, this is sort of an if and only if, right? So if v belongs to the span, then v is of the correct form. And if v belongs to this set, capital V, then definitely it belongs to that span. And so what we get is that this set here, this must be equal to v, right? So v is a span, and since v is a span, it must be a subspace. That's the argument we make here. Okay, so that's it for this video. In the next video, we're going to move on to a discussion of linear independence. All right, so now we're going to move on to the next of the major concepts that's discussed in section 4.2, which is linear independence. These concepts of span and independence are two of the kind of primary ideas that drive most of the theory in linear algebra. Most problems in linear algebra can be understood in terms of span and independence. They are fundamental concepts to the entire subject area. So where this idea of independence, where this comes in, is we saw in the last video that if you want to describe a subspace, one way you can describe a subspace is as a span of a set of vectors. If I have a collection of vectors, I can consider the set of all linear combinations of those vectors, and I know that that will generate a subspace. If I want to kind of get a better handle on what sort of subspace I'm dealing with, in particular, if I want to know, like, is my subspace, is it going to look like a line? Is it going to look like a plane? I want some idea of, what is the dimension of the subspace? Is it, do I have one direction I can move in? Do I have two? Do I have three? It's not simply a matter of counting the vectors that I have, because, if I take a set containing two vectors, but those two vectors are parallel, then they're not going to generate a plane, they're only going to generate a line. So independence is a condition that you can impose on that set of vectors to make sure that you know exactly what sort of geometric object is going to be generated when you consider the span of those vectors. To kind of get an idea of where the independence comes in, we can say, well, what does the span of one vector look like, right? So we could say, well, the span of, let's say, v, right? So we know that by definition, that looks like the set of all scalar multiples of v, right? So all things that look like t times v, where t is a real number. But there are two possibilities here. One is that, well, what if v is just the zero vector? I didn't say anything about what v is. V could be the zero vector. If v is the zero vector, then what is this span? If v is the zero vector, then the span of v, there's nothing in there but the zero vector. That's the only vector in the set, right? On the other hand, if v is not equal to 0, if v is not equal to the zero vector, then we know that what we get is, well, we've got our vector v, and all scalar multiples of that vector produces a line through the origin, right? So if v is non-zero, then I get a line through the origin, and that's what the span of my one vector looks like, right? So similarly, if we were dealing with the span of two vectors, say u and v, right? So we know that by definition, this would be the set of all things that look like, say, s times u plus t times v, where s and t are real numbers. But then again, you kind of look at, well, what are the possibilities? There's sort of, some cases here. So case one, the first case would be, well, if u and v, if they're both equal to 0, that's not a very interesting case, but it's a possibility, right? So if u and v, if they both equal 0, then what I get is simply, I still get the set containing the zero vector and nothing else. Another possibility is that maybe v is a scalar multiple of u, right? U and v are parallel. Then su plus tv would look like su plus t times c times u, which would be s plus tc times u, right? You'd be dealing with just scalar multiples. So in here, let's say that, this is not the zero vector, right? So then the set of all linear combinations of u and v just reduces to the set of all scalar multiples of the vector u, right? Because any linear combination of u and v, in this case, you could write as simply a multiple of u. And so then once again, in this case, you're dealing with a line through the origin, right? The final possibility here would be that, so possibility C would be that u and v are both non-zero and non-parallel, and in that case, well, we know what we would get. We would get, so here's our coordinate system. Maybe here's u, here's v, and the span of u and v in this case is going to be the plane containing the vectors u and v. They're going to generate an entire plane, right? We know that because this sort of expression here is exactly what showed up when we wrote down the vector equation for a plane, given two vectors that are parallel to that plane, right? And then similarly, if you're dealing with the span of three vectors, well, I guess there are four possibilities, right? If they're all equal to 0, you just get the zero vector. If they're all parallel, you get a line. Another possibility is maybe you have, say, you're dealing with, say, so maybe v is a linear combination of or you have a vector w, which is a linear combination of, say, u and v. In this case, the span of u, v, w is going to be a plane, right? Because adding that vector w into the span, right, you're adding a third vector, but that third vector can be written in terms of the two you already had, so it's still a vector in that same plane, right? So it's not something you can use to get out of the plane. So you're still dealing with a plane. Even though you have three vectors, the span is still a plane. And of course, your final possibility is that u, v, and w are sort of, well, the right word here is going to be independent, but they're not, you know, they're not all in the same plane. And in that case, the span is going to be, well, you're going to get everything. You'll get all of R3. If you take three vectors that all three are non-zero, none of them are parallel, they don't all lie in the same plane, then you generate the entire space. And so this would be the situation where you would say that those three vectors are independent, right? So a single non-zero vector is something you would say is independent. It doesn't depend on anything else. If you've got a pair of vectors, as long as they're not parallel, you would say those are independent. With three vectors, if they're not in the same plane, you say that they're independent. Not it, yeah, that they're independent. So this is the idea of independence. So how does this look like in general? What does it mean to say that vectors are linearly independent? Well, we'll start by saying what it means for them to be dependent. So if one of the vectors can be written as a linear combination of the others, right? So if let's say it's the last one, right? And I'm not really, it seems like I'm sort of maybe not making a very general statement here because I'm choosing one of the vectors. But the order in which I write these vectors down is irrelevant. So I could always kind of write them down in an order where the last vector is the one that's a linear combination of the others. So if vk could be written as, say, c1 times v1 plus c2 times, say, v2 up to c, say, k minus 1, v k minus 1. That would be a case where you would say that the set of all vectors v1 up to vk is dependent, right? Notice also that if one of the vectors is the zero vector, right, then you could just set all those c's equal to 0. So the zero vector can always be written as a linear combination of any other vector. So if the zero vector is in there, your set is definitely dependent. And one of the things you might notice here, you might note if you kind of play around, it takes a little bit of work to prove this in general, but you can probably guess this from the discussion on the previous slide. So if I started with the span of v1 up to vk minus 1, right, adding in that last vector, adding in vk, I gain nothing by adding it. So adding that vector in does not add to the span, right? Anything that can be written as a linear combination of all of these guys could be written as a linear combination where we don't bother to use that last vector. Okay, so the vector vk is redundant if we're interested in sort of generating subspaces using linear combinations. We don't really care about that last vector, so we could always throw it away. All right. So linear independent means that none of the vectors can be written in terms of the others. One of the ways that you can rephrase this is you can kind of make the definition like this. So the way you might make the definition is as follows. So you might say that a set v1 up to vk of vectors in, let's say, Rn is going to be linearly independent. Let's underline that. That's the term we want to define. It's linearly independent if whenever we have c1 times v1, c2 times v2, whenever we have a linear combination that equals the zero vector, then it follows, I meant to say must, we must have c1 equals 0, c2 equals 0, down to ck equals 0, right? So this is one way to define independence. Independence means that the only linear combination of those vectors that can give you the zero vector is if you multiply all of the vectors by 0, right? And so that's basically saying that the zero vector can be written uniquely in terms of these guys. And in fact, any other vector that would be in the span of those, one of the consequences of independence is that if I had some vector that could be written as a linear combination of v1 up to vk, if those vectors are independent, then there is only one linear combination that will work. So independence is sort of a uniqueness condition. There's only one way to do the job. Whereas with a dependent set, there could be many ways of doing the same job, right? If I include that vector vk, I could choose to write down one linear combination that involved it and another that didn't. There's going to be more than one way of doing the job. Okay. Notice that if I have a non-zero solution to this equation, if I had one of these scalars, let's say ck is not equal to 0, for example, if this scalar is non-zero, I could take this last vector, I could move it over to the other side of the equation, and I could divide everything by ck, c1 over ck, c2 over ck, divide everything by ck. I could solve for that vector. I could solve for one of the vectors in terms of the other, right? So if your set is not independent, then it's dependent, because if there are non-zero solutions to this equation, that means you can solve for one of the vectors in terms of the other, like this. Okay. So, examples of dependent, independent sets containing one vector. So linearly dependent. There's only really one example I can write down, and that's the set containing nothing but the zero vector, right? If the zero vector is in there, that set is automatically dependent, right? Because if I, for example, so to be independent would mean that if I wrote down c times 0 equal to 0, independence would mean that I would be forced to take c equal to 0, but we know that you can take any value you want for c and it will satisfy this equation, right? I can make this work with a non-zero value for c. So that set is dependent. A linearly independent set, any non-zero vector will do. There we go. Okay. What about with two vectors? Well, there's a couple of ways I can create a linearly dependent set containing two vectors. One would be to just choose one of the vectors to be the zero vector. Another one would be to choose two non-zero vectors that happen to be scalar multiples of each other. Say 1, 2, 0, and maybe -3, -6, 0. Right? Where the second vector is -3 times the first vector. Those are both examples of dependent sets, right? Because if this is v and this is w, we'll notice that 3v plus w equals 0. Here's a sort of non-trivial linear combination that adds up to give me the zero vector. For an independent set, I could take, well, any two non-parallel vectors, 1, 2, 0, and I could take 0, 1, 1, let's say. Okay. With three vectors, again, if any of the vectors is the zero vector, you're dealing with a dependent set. If any two of the vectors are parallel, you're dealing with a dependent set. But the other possibility with three vectors that you could come up with, if you want non-zero, non-parallel vectors, is you could be dealing with a situation where maybe I have my vectors 1, 2, 0, 0, 1, 1. So those guys are independent. But my third vector is some linear combination of the first two. So maybe it's 2 times the first vector plus 3 times the second vector. So I would get 2, 7, 3. Right. So if this is u and this is v, then this is going to be 2u plus 3v. Right. All three vectors lie in the same plane. For a linearly independent set, you have to find three vectors that don't all lie in the same plane. One option might be to maybe take the cross product of those first two vectors. That gives you something you're guaranteed is orthogonal to the ones that you put in. So we could do that. We could do 1, 2, 0, 0, 1, 1, and let's do it up here. What is u cross v? U cross v. I, j, k, 1, 2, 0, 0, 1, 1. I'm gonna get 2i minus j plus k. So I could throw in the vector 2 minus 1, 1. And I would be safe in the knowledge that that set was linearly independent. Okay. All right, here's another example. Is this set linearly independent? How could we decide that this set is linearly independent? Well, the key observation to make here is notice the two of these three vectors have zeros in them. The third one does not. Okay, so if we label these U, V, W, so what we can say is we know that V does not belong, so here's one way we can say it, right? I want to specify that V cannot be written as a linear combination of U and W. And so that's the same thing as saying that V does not belong to the span of U and W. And we know this because the third component is non-zero. Right? Okay. So we know that V can't be written in terms of U and W. So then we might ask, well, can we have, let's say, U equal to, say, AV plus BW for scalars A and B? Well, if we wanted to write U as A times V plus B times W, we know that we'd need A equal to 0. Why do we need A equal to 0? Well, if A is not equal to 0, I would have, I would have 3A in the third component for that V. I'd be doing 3A time, and I'd be adding 0, whatever multiple I have here for my W, right? I'd be doing B times 0 in that spot. So I'd have 3A plus 0, and so I would have, I'd have this. I would have 3A plus 0. Well, that would have to equal 0. And so that tells me that A has to be equal to 0. But if A is equal to 0, that would just give me U equals B times W. And so that would mean that U is a scalar multiple of W. That would mean that U and W have to be parallel. And we can see by inspection that these guys are not parallel. And a similar argument would establish that you cannot write V as, say, A times U plus B times W. We've done the V. W cannot be written as A times U plus B times V, right? Because, again, in this case, you would have to set B equal to 0 to deal with the 3, and then you would say, well, W and U are not parallel, right? So I can't write V. I can't write V as a linear combination of U and W. I can't write U as a linear combination of V and W. I can't write W as a linear combination of U and V. None of the vectors can be written as a linear combination of the others, and so that tells me that the set is linearly independent. Okay. One more example. Somebody hands me two vectors, U and V. I want to consider a set UVW, and I want to extend this set in one of two ways. I'm going to extend it first so that my set is independent, and then I want to extend it so that it's dependent. How do I extend it to an independent set? Well, here's one trick that's always going to work, but this is a trick that really only works for R3. Right, so I'm really relying on the fact that I'm dealing with three-dimensional vectors here. We would have to think a little bit harder if we were in other dimensions. So you've got your U, you've got your V, right? So we want to make sure that we want W to be, this is bad grammar. Sorry, guys. Terrible, terrible grammar. Let's do it this way. We want to make sure that W is not a linear combination of U and V. And you know, so because if W is a linear combination of U and V, then we know the set would be dependent because we could write W in terms of U and V, and so we want to make sure it's not. How do we make sure it's not? Well, we just need to make sure that W is not in the plane that's spanned by U and V, and one way to certainly guarantee that W is not in the plane spanned by U and V is to choose W to be perpendicular to the plane spanned by U and V. And we know that one way to get a vector which is perpendicular to a plane is to use the cross product. So we can take the cross product U cross V and use that as our W. I'll leave it for you guys to actually compute the cross product, but it's clear that if we add the cross product of U and V into the set, those three vectors will be independent. What about dependence? For dependence, there are lots of options. We could do, so here would be an easy option, 2 minus 1, 3, minus 3, 5, 2. Throw in the zero vector. Any set containing the zero vector is dependent, so why not throw the zero vector in there? Then you know it's dependent. Or if you don't want to throw the zero vector in, maybe you say, oh, you know what, that's too easy, that's way too easy. Maybe you then say, you know what I'm going to do? I'm going to put 4 minus 2, 6, right? I'm just going to do 2 times U, right? So then that third vector can be written in terms of the last two, right? Because, well, one way I can think of it, this is you know, it's 2 times U, but I can think of that as 2 times U plus 0 times V. So that is certainly something that you can write as a linear combination of U and V, and so you have a dependent set. Or really any, you know, put any linear combination of U and V that you want in there, and you're going to get a dependent set. Okay, I know that was there's a lot to digest in one video, but this is the idea for independence. We've got one more idea to address, which is the idea of a basis, and then we'll be done with section 4.2. Okay, so this is our last video for section 4.2. I'll try to keep this one relatively short. We're going to introduce the idea of a basis. So far we've encountered the idea of a subspace, right? So really when we say basis here, we mean basis for a subspace. Okay. So what exactly is a basis? Well, we've kind of addressed the idea that any subspace, you know, should be written as a span. So we look for a collection of vectors so that we can write our subspace as a span of vectors, because we know that any span is definitely a subspace, right? But we know that not all spanning sets are created equal, because, you know, if you work with a dependent set, then you have some redundant vectors in there, right? If you want to describe, let's say, a subspace, which is a line through the origin, you want to describe that as the span of a single vector. You wouldn't want to describe a line through the origin as the span of 2 parallel vectors, because that's just redundant. You want to simply use that one vector in there to describe your span. Similarly, if you're dealing with a plane, you would want to describe a plane as a span of 2 vectors. You wouldn't want to be dealing with 3 or more vectors. So a basis is basically what you take if you start with a spanning set and then you get rid of any garbage that's in there, you get rid of any redundant vectors, and what's left over once you throw away the redundancies is an independent set. So a basis is going to be a set of vectors which is independent and also spans your subspace. So here's the definition, right? So you have a subspace of Rn, and you have a bunch of vectors V. So the key thing here is that these are all vectors in V, right? So each Vi is, when we say that's a subset, we just mean that each Vi is a vector in the subspace, right? So I going from 1 up to K. So we want the span of this set to be equal to V, right? So we want V to be the set of all things that look like C1, V1, down to CK, VK, where all these CIs are just scalars. But we want those vectors to be linearly independent. So what this means is that when you add the independence in, what the independence means is that, well, every V in V can be written. So So every v and v can be written as a linear combination. V equals C1 V1 down to Cn Vn. This is the so the can be written. The fact that it can be written. This is the span. This is the spanning condition. The independence condition is that not only can it be written as a linear combination of this form, V1 up to, sorry, Vk, it can be written uniquely. Okay. So the uniqueness here, this comes from the independence. Okay. The independence condition is what guarantees that there, for each vector in the subspace, there's only going to be one set of scalars that does the job. Okay, so you have both spanning and independence. This is what sets a basis apart from other spanning sets. All right, so here's an example. We want to find a basis for a subspace. Okay, so at this point, we might, the first thing we might say is, is it actually a subspace? Should we verify it? Well, we know what this equation describes. We know that this describes a plane that passes through the origin. And we've already discussed the fact that any plane through the origin can be viewed as a subspace. It is a subspace. If you wanted to verify that this is indeed a subspace, there's a couple of ways that you could do it. One would be to sort of say, okay, if I had v equal, let's kind of check things quickly here. Okay, so let's say v is equal to, let's say, a1, a2, a3. W is b1, b2, b3. So if I said that v and w are both in that subspace, well, what I would be telling you is that 2a1 minus a2 plus 3a3 has to be equal 0, and that 2b1 minus b2 plus 3b3 has to be equal to 0, right? Notice in particular that, 2 times 0 minus 0 plus 3 times 0 equals 0. The 0 vector is in there. And if you take two vectors of this form and you add them together, if you kind of add these equations, you can see that 2a1 plus b1 minus a2 plus b2 plus 3a3 plus b3 equals 0. And so what are these numbers? A1 plus b1, a2 plus b2, a3 plus b3. That tells me that that v plus w is in the subspace. And then you could do a similar argument for the scalar multiplication. But rather than kind of verifying things directly, we know that the other way you can establish that this set is a subspace is to show that it can be written as a span. So what I'm going to do is I'm going to say, all right, so notice that, so let's say my vector v looks like x, y, z. And I can solve this equation that I've been given, the equation of my plane. I can solve for any one of the variables in terms of the other two. Y looks like the easy candidate here. So y I can write as 2x plus 3z. There's no reason I couldn't solve for x or z, but this allows me to avoid fractions. So I can write v as x. Y is now going to be 2x plus 3z. And then I have z. So I split this up. So I write one vector containing everything that depends on x, and another vector containing everything that depends on z. And then I can factor out the scalars. So this is going to be x. Let me move my equal sign. X times the vector 1, 2, 0 plus y times the vector 0, 3, 1. Which suggests that I should be able to give this as my answer. I should be able to give b equals 1, 2, 0, 0, 3, 1. Okay, why is that a basis? Well, this what we've done over here, right? So this tells me that my vector, my subspace v, is certainly the span of this set B, right? Because I started I started with an arbitrary vector v in my set, and I established that it can be written as a linear combination of these two vectors. So every vector in this subspace can be written as a linear combination of those guys. So every vector is in the span. So these two vectors, they span v. And we look at them, we can see they're not parallel. There's only two vectors, right? There's two vectors, they aren't parallel. So we know that B is linearly independent, and that tells me that it's a basis. Okay. One more example. Here's another subspace. Now I've written things in this form here rather than as column vectors. So maybe we should have done this sort of as angle brackets. But let's flip our notation. Let's stick with column vectors because that's what we're used to. You know, this fits a little bit better on my page. So let's say V looks like. So what it looks like here, I've got 2x minus y, x plus 2y, x, and then minus x plus 4z. Okay. And so again, what I want to do here is I want to split this up. 2x, x, x, minus x. It's everything that depends on y. Minus y, 2y, 0. 0, that's all the stuff that depends on y. And z shows up down there at the bottom. Okay. So this is x times 2, 1, 1, minus 1, plus y times minus 1, 2, 0, 0, and z times 0, 0, 0, 1. Okay. So this suggests that my basis B should be 2, 1, 1, minus 1, minus 1, 2, 0, 0, 0, 0, 0, 1. Okay. And of course, you have to do some checking. We know that it's certainly a spanning set. Why is it independent? One way to see that it's independent is to notice that you've got zeros in the third position for the second and third vectors, but not here. And so we certainly know that the first vector can't be written as a linear combination of the other two, and those remaining two are not independent, the remaining two are not scalar multiples, they're not parallel. And so the three of them together have to be independent because the first one is not in the span of the second and the third, and the second and third themselves are independent. So three of them together gives you an independent set. So then we know that that's a basis. By the way, one of the important reasons for studying basis is if you want to actually define dimension. Let me just make this as a remark before we end the video. The way you define dimension is the dimension of a subspace is the number of vectors in any basis. Okay. Now, there's a theorem you have to prove before you can make this dimension, or before you can make this definition of dimension. You have to prove that any other basis for this same subspace would have to have the same number of vectors. So whatever basis we choose, if one basis has 3 vectors, then every other basis would also have 3 vectors, because there are many possible choices of basis that you can make, infinitely many, in fact. But what's invariant across all possible choices is the number of vectors in that set. And so this is how you actually define dimension, right? So in this case, we could say something like this. We could say the dimension of V is equal to 3 because there are 3 vectors in that basis, right? In the previous example, there were 2 vectors in the basis, so we would say that the dimension is 2, right? And this sort of coincides with our intuitive notion, our intuitive understanding of dimension, right? That a line should be one-dimensional, and of course we can write it as the span of a single vector. A plane should be 2-dimensional. We write it as a span of 2 vectors. 3-dimensional space, there it is, dimension in the name, right? So R3, we need 3 vectors to span all of R3. A basis will have 3 vectors. So this idea of dimension, it fits with our kind of common understanding of what dimensions should mean. Okay, so I know those are some tricky concepts, but we're done with them for now. We're just introducing the ideas, like I said at this point. We'll come back to these ideas later on in chapter 6. We'll look at them from sort of a more computational perspective and try to understand things in terms of systems of equations and try to get a better handle on things then. All right, so this is the first of 3 videos on matrix multiplication that we will go through for the material in section 4.3 of the textbook. So for those of you who found section 4.2 to be a little bit abstract, you might be happy with this section of the book. Everything here is very concrete and computational. The only thing with matrix multiplication is that the process is a little bit counterintuitive, and it's something that you might need a bit of time to get used to, but as with most of the computational things in this class, with a bit of practice, matrix multiplication becomes pretty routine. It becomes something you can do without having to think too hard about it. So let's, to introduce the idea, we're going to warm up with a, I put practical in quotes because I don't know. I have no idea if this example has any connection to reality or not. It probably doesn't. But we could imagine some sort of scenario where we've got a farm that raises livestock. We've got cows and pigs in this case, and then each one is provided with some grain feed. I've gone with corn and barley in this case. So whether or not these are appropriate feeds for these animals, ethics of grain-fed versus grass-fed cows, we're not going to get into any of those sort of details here. We just want to solve one particular problem, which is if these feed crops are grown using some sort of chemical fertilizers, and there's a certain amount of chemical that is absorbed by each crop when these fertilizers are applied, how much of these chemicals are passed along to each animal? So how do we figure that out, right? So the first matrix that we have here, the first matrix keeps track of how much of each chemical is absorbed by each type of feed, right? So the first matrix establishes this relationship between the chemicals and the feed. We can think of this, if you like, you can think of this matrix as establishing some sort of function that assigns to each type of chemical, assigns the amount of that chemical present in the feed. The second matrix, if you like, looks like some sort of, again, what this one is doing, if we want to think of it as a function, this one is a function which for each type of feed assigns to that feed the amount of feed that is eaten by each animal, right? So corn is assigned to the number 27 for cows. Cows eat 27 kilograms of corn, and 15 for pigs. Pigs are eating 15 kilograms of corn. Again, these numbers might be completely unreasonable. Maybe 15 kilos is probably way more than a pig could eat in a week. But yeah, who knows? Maybe it's accurate. I'm not sure. The numbers are completely made up. The problem, however, is a reasonable one. How much of each chemical is consumed by these animals? So think about doing, let's say we want to know how much of chemical 1 is consumed by the cow. Well, how do we figure this out? We say, okay, so the cow eats 27 kilograms of corn. And since we know how much corn the cow eats and we know how much chemical is in the corn, we can multiply those. So 27 kilograms of corn times 1 milligram per kilo of the first chemical. That tells us how much the cow is consuming by eating the corn. But we also have to add on the amount that is consumed from eating the barley. So there's an additional 15 kilograms of barley. And we multiply by, so the first matrix says that there are 2 milligrams of the second chemical for every kilo of barley. And so what do we get? We get 27 times 1 plus 15 times 2. And so we get 57. 57. Make sure I add correctly. Let's fix that up. 30 plus 27 gives me 57 milligrams of the first chemical. One of the things you may want to notice here is that you get something that looks suspiciously like a dot product, right? And you could do this again for, let's say I want to do it for, maybe I want to do the pig, and I want to do maybe chemical, let's say 2, right? So what would I do for, if I wanted to know how much of chemical 2 is consumed by the pig? Well, I would do my 15 kilograms of corn coming from here. I would multiply by the amount of chemical 2 that's in each kilogram of corn, which is a 2. And then I would do so the pig is eating 5 kilograms of barley, and in each kilogram of barley there is 1 milligram of chemical 2. So I would do 5 times 1, and so I would get 30 plus 5, I would get 35 milligrams. And again, we get this sort of dot product, right? So notice that what we're doing here is we're basically taking a row from the first matrix, and we can think of this as a row vector. It's a two-dimensional row vector. We're taking a column from the second matrix, which is also a two-dimensional vector, in this case a column vector, and we're combining them in sort of a dot product operation. We're putting the two together and we get out a number, right? And so we can do this for each row and for each column. And so what we're trying to figure out overall is, we want to figure out, okay, we have chemical 1, chemical 2, chemical 3, we have our cows, we've got our pigs, and we want to end up with, knowing how much of chemical 1 is consumed by a cow. So we worked that out. That was 57, right? And notice that that's the entry in the first row and first column here. And the way we obtain it is we take the first row from the matrix on the left and we multiply by the first column of the matrix on the right. If I want to know how much of chemical 2 is consumed by the cow, well, then I should be doing, so chemical 2, this is going to be that's row 2, column 1, right? Second row of this matrix, first column of that matrix, how much of chemical 2 is consumed by the cow. So I go over to the second row for this matrix to get chemical 2, first column for this matrix to get the cows, and I'm going to be doing 27 times 2 plus 15 times 1. I'm going to get to 69 milligrams there. And then if I wanted to know what goes in the third row, first column here, how much of chemical 3 is consumed by the cow, I'm going to go to the third row here, and I'm still in the first column here. So 3 times 27 plus 2 times 15, that's going to give me 111. Then I do the same thing for the pigs, right? So I go back now, the pigs are in the second column, so I want to do first row times the second column to give me the amount of chemical 1 that the pigs consume. So I get 1 times 15 plus 2 times 5. I get a 25. Row 2, column 2, that's the amount of chemical 2 consumed by the pig. We did that one already. And then the last one would be chemical 3. If I take the third row, that's the chemical 3 times the second column. That should go in the third row, second column here. So 3 times 15 plus 2 times 5, and I get 55 there, right? So we can work out those numbers. That, in a nutshell, is how matrix multiplication is going to work. We'll see that is basically a specific case of the general procedure. Okay, so we saw that the kind of essential ingredient here, that we do, for each row and for each column is we take a row from the left, we take a column from the right, and we multiply them together. So those are sort of the building blocks, right? So the building blocks are this row times column procedure. And doing a row times a column, it is really just a dot product, right? So it's going to be A1 times B1, right? First entry from R times the first entry from C plus A2 times B2. I multiply the second entries together and so on down to AN times Bn. So I form each of those products and then I add them all up. It's just like doing the dot product, right? Once I've added everything up here, I get some sort of number that comes out, right? So for example, let's say my row looks like 3 minus 1, 4. Now, so if my column was, if my column was something like, 2, 1, okay, well, I can't do anything with that because, if I wanted to do row times column, I can do 3 times 2, I can do minus 1 times 1, but then the 4 doesn't have a friend over here in the column, right? Because there's only 2 numbers in the column, there's 3 in the row. Each entry in the row needs to have a buddy over here in the column that they pair up with, and so my column is the wrong size, so this wouldn't make sense. The way I get these things to work is I make sure that they're the right size. So maybe I do 2, 1, and maybe minus 1. Okay, then I can do R times C. R times C is going to be 3 times 2 plus minus 1 times 1 plus 4 times minus 1. So I get 6 minus 1 minus 4. I get 1 for that product. Okay. So the next step is to basically extend this a little bit and consider the case where we have several rows. Of course, eventually we'll be having sort of many rows from the left and many columns from the right, but we'll just to kind of warm up, we'll go from one row on the left to having several rows on the left. So what we'll do here is we'll say, okay, I've got a matrix A, it's an m by n matrix, and I want to think of this m by n matrix as a collection of rows. So I have A11, A12, down to A1n, A21, 22, over to A2n, okay, down to AM1, AM2, and across to AMN. Okay, so there's my m by n matrix, and I want to kind of divide things up like this. I want to think of this as being like row 1. Here is row 2, and so on down to the last row, row m. Okay, and what's important here is not the number of rows. The only thing that the number of rows is going to affect is basically the size of the output, right? So m is going to be the number of entries in the final product. When I do A times X, I'm going to get an m by 1 matrix. So the number of rows is going to determine the size of A times X. But as far as whether I can even carry out the product in the first place, what matters is that if each row of A has n entries, A11, A12 down to A1n, right, there are n entries there are n columns, then X also needs to have n entries, right? So X here, X looks like X1, X2, down to Xn. Okay. So I can form this product A times X because I can do A11, right? I can do A11 times X1, I can do A12 times X2, and so on down to A1n times Xn. I can form that product. So basically I can form row 1 times X. I can do row 1 times X, that's defined. I can do row 2 times X, that's defined all the way down. And so what I do is I say, okay, A times X, I'm going to think of that as row 1, row 2, down to row m times X. And the result is going to be a m by 1 column vector where the first entry is the dot product of row 1 with X, the second entry is the dot product of row 2 with X, and so on down to the last entry, which is the dot product of the last row times X. So just to give you a quick example, if A looks like, maybe A looks like, let's say 3, minus 1, 2, 4, minus 1, 5, and X looks like, let's say 2, 3. Right? So A times X is going to be what? So I do the first row, so we divide things up. So row 1, row 2, row 3. So the first row times X, I do 3 times 2 plus minus 1 times 3. That's row 1 times X. Now we do row 2 times X. 2 times 2 plus 4 times 3. Then I do row 3 times X. Minus 1
times 2 plus 5 times 3. Okay. And I carry out each of those products. 6 minus 3 gives me 3. 8 plus 12 gives me 20. Minus 2 plus 15 gives me 13. Okay, and I get that product. All right. But there's actually another way that you can think about computing this product. The other way that you can do it is you can take your matrix A, A11, A12, all the way down to A1n, 2, 2, 2, over to A2n, and all the way down to A M1, M2, Mn. So there's A, here's my X, and X1, X2, down to Xn. And so the other way to do it is to say, well, you know what, I could divide A up into columns, column 1, column 2, down to column n. And I could basically say, you know what, for each column in A, I have a corresponding number in X, right? So I kind of column 1 I can match with X1, column 2 I can match with X2, all the way down to column n times Xn. And so I could also make this definition. I could basically think of this as like a dot product, except that, you know, I'm doing x1 c1 x2 c2 down to xn cn, but these c's are not numbers anymore, they're vectors. And so when I form this, right, a times x, what I'm going to do is I'm going to say a times x should be x1 times c1 plus x2 times c2 down to xn times cn, right? And so what have I got? Well, what I've just done is I formed a linear combination. Right? So the other way of doing a matrix times a column is you can think of it as forming a linear combination of the columns in the original matrix. So let's check that this actually gives us the same result. You can work it out for yourself if you want. I think we'll skip, because we don't want this video to get too long, we'll skip working out the general details, but you can kind of see what will happen. All the numbers in column 1 will get multiplied by x1, all the numbers in column 2 get multiplied by x2, and so on. And when you add everything up, you do get the same thing that you got before. You'll still get all these numbers times x1, all these numbers times x2, and so on. And to see that that is indeed what you get, let's try this example that we have here. So if we take the same matrix, 3, minus 1, 2, 4, minus 1, 5. Let me just double check to make sure that that's what I had. Okay. X being the column 2, 3. So this this recipe says that to do A times X, I should do first entry in X, which is a 2, times the first column in A, 3, 2, minus 1, plus the second entry in X times the second entry in A, minus 1, 4, 5. So this gives me 6, 4, minus 2, minus 3, 12, 15. And when I combine those, I get 3. I get 3, 16, and 13. Okay, and that's not the same. It's not the same because I messed this one up. 2 times 2 is 4, guys, not 8. 4 plus, yeah, there we go. I'm doing these videos before I finish my coffee. 4 plus 12 gives me 16. So they do come out to give me the same result, whichever way we do it. Good. We'd be worried otherwise. Now, the other thing you could think about is you could think about doing a row times a matrix. This is something that that you'll sort of see less often. But if you want to, you can think about doing a row times a matrix. So A1, A2, down to AN, right? And we know how to do a row times a single column. So if we think of B as consisting of many columns, B1, B2, down to B3,
P, right? So if I think of this, so this is my R, right? Then I can do that row times the first column, so row times B1, and then row times B2, and so on down to row times BP, right? So if I have one row on the left and many columns on the right, I just do row times column for each one of the columns, right? Whereas when we were doing a matrix times a column, we said, well, we have many rows on the left, one column on the right, we do each row times the column. So of course you can see where you go from here. If you want to do general matrix multiplication, we'll consider that in the next video. If I have many rows on the left times many columns on the right, then I'm just going to do each row times each column. I'm going to do row times, so that's kind of the general picture. So the general case would be, you think of your matrix on the left as a collection of rows. So, row 1, row 2, and so on. You think of your matrix on the right as a collection of columns, B1 down to BP. And as long as the number of entries in each row matches the number of entries in each column, then you can do row 1 times B1. You can do row 1 times B2, and so on down to row 1 times BP, and then row 2 times B1, and so on. And that's going to be how we do matrix multiplication in general, and we'll explore that in the next video. Okay, so this will be the second of 3 videos on matrix multiplication for Math 1410, Spring 2017 semester. In the previous video, we looked at a number of special cases, and now we want to extend to the general picture. So the cases that we looked at on the last video, we said, okay, if I want to do a row times a column, so if I have, so if my R looks like, say, A1, A2, down to AN, and I have a C which looks like maybe B1, B2 down to BN. And the key thing here is that the number of entries in my row matches the number of entries in my column. So each number in the row R has a partner in the column C. I can pair them all up, and I pair them up using essentially this dot product process, right? So if I want to do R times C, I do A1 times B1, I do A2 times B2, and I continue all the way down to AN times BN, right? So each number from the row on the left can be paired with the corresponding number from the column on the right. We multiply those guys together, and then we sum all of those products. That gives us row times column. If I wanted to do a matrix times a column, right? If I wanted to do so if A is my matrix and X is my column vector, so X here looks like maybe X1 down to Xn. What I do is I say, you know what, I can think of that matrix A as being composed of several rows. Row 1, row 2, down to, say, row M, multiplied by X. So each one of these rows here, maybe row I, is going to look like AI1, AI2, down to AIN, right? And again, the N here matches the N there. And so I can do each of these row times column products, and I simply do row 1 times X, row 2 times X, all the way down to row M times X. Okay, and similarly, we can do a row times a matrix. If I have Y, maybe Y looks like Y1 down to YM. Okay, and I want to do Y times B. So I think of B as being composed of columns. Column 1, column 2, down to, not down. Columns go across. Let's fix that. Column 1, column 2, down to column,
let's say n, and I do the row times the first column, so y times c1. I do y times the second column, and so on down to y times the last column, right? Where each one of these columns looks like a1i down to a-mi. And again, the m matches with the m. The number of entries are the same. Okay, so we want to put these together now. We want to say, okay, well, if I want to do a general matrix, if I want to form a product A times B, I will think of the matrix A as being composed of rows. I will think of the matrix B as being composed of columns, and I will do each row from A multiplied by each column from B. Okay, so if I want to do AB, right? So I want to do A times B, right? And if A is going to be, let's say, an M by N matrix, and B is going to be, well, for now, let's say it's maybe it's a K by L matrix, okay? K by L. Okay, so I want to do this kind of row times column thing. So I want to think of A as consisting of several rows. Row 1, row 2, down to, well, row M. Okay. I want to think of B as consisting of several columns. Column 1, column 2, down to column L. Okay. And now what do I know? I know that row I from A is going to look like AI1, AI2, down to AIN. I know that column, let's say J, is going to look like B1J, B2J, down to BKJ, right? Where this N matches with that N, and this K matches with this K, right? And I want to form this product. I want to form, in order to form these products, row I times Cj, what do I need? I need the number of entries in my row to match up with the number of entries in my column, so that every one of these A's has a corresponding B that it can multiply by. And that means I need N to equal K. Okay? So these guys here, these guys must match. All right? Once I know that they match, I can form my product. So how do I do this product? I do the first row times the first column, and that's my first entry in the new matrix. I do the first row times the second column, and that's the next entry, and so on all the way down to the, let me move things over a little bit so we can fit. So row 1, column 1, row 1, column 2, down to row 1 times the last column, column L. Then I would do the second row times each of the columns, so row 2, column 1, row 2, column 2, down to row 2, column L, and so on down to row M times column 1, row M, column 2, row M, column L. And that's my matrix product. And notice that the result here is an M by L matrix. Okay, so those numbers, that M and that L on the outside,
they tell me the size of the product that results from multiplying those two matrices. So that's the general procedure. If I want to do a matrix A times a matrix B, the first thing I have to check is, can I even multiply them? And the way I check is I check those two inside numbers and I see if they match. If they do, I know that the product is defined. I know that the size of the product is given by the M and the L, the numbers on the outside, and then I work out each of the dot products, each of these row times column dot products, right? So a general entry here is going to look like row I times column J. Okay, so here are some examples. We want to form some matrices. So first of all, let's note the sizes. Okay, so A has 2 rows, 3 columns. B has 2 rows, 2 columns. C has 3 rows, 2 columns. So which of these can I form? I can't do A times B because the 3 here does not match the 2 there. Those two numbers are not the same. So A times B is not defined. What about B times A? So this would be, I would be doing a 2 by 2 matrix times a 2 by 3 matrix. That works. Okay, 2 and 2. Those ones are defined. A times C. A is 2 by 3, C is 3 by 2, the 3 and the 3 match, so that one is defined, that one is defined. C times A, I would be doing, what would I do for C times A? It would be a 3 by 2 matrix times a 2 by 3 matrix. Well, that's okay, right? 2's match up, so that one is defined. B times C, I can't do B times C because the 2 doesn't match the 3, so B times C is out. Okay, what about C times B? C times B I can do because C is a 3 by 2 matrix. B is 2 by 2, and so those numbers do match up. Okay, so 4 out of those 6 matrices are defined. Now that we know they're defined, we can work out what they are. So B times A. The size is going to be 2 by 3. Here's how you can kind of think about how to compute this and how to kind of make sure you get the size straight when you do it. If I'm doing B times A, I can put my matrix B on the left, 2, 0, minus 3, 1. I'm going to put A on the right, but I'm going to shift it up. I'm going to put it here. 2, minus 1, 3, 4, minus 3, 5. Okay? And then you can kind of see that things line up for you. Right? 2 rows from the left, 3 columns from the right gives you a 2 by 3 matrix overall. And each of the entries, you can work out what each of the entries should be. If I want to do, let's say, this entry here, this entry corresponds to this row, and it corresponds to this column. So I should do row 1 times column 1. So I do 2 times 2 plus 0 times 4 gives me a 4 that goes in there, right? So basically I multiply this, that gives me a 4, that gives me a 0, and I add them together, and that goes in there, right? And then for the first row and the second column, I do the same sort of thing, but now the 2 matches up with the minus 1, the 0 matches up with the minus 3, so I do 2 times minus 1, 0 times minus 3, and I'm going to get minus 2, and so on. So then if in this entry here, I'm doing this row, this column, so I get 2 times 3 plus 0 times 5, I get a 6. Right? And then again, if I want to know what goes in this spot, I'm in row 2, column 1. And so I do 3 times 2, and I do 1 times 4. So 3 times 2 plus 1 times 4, minus 6 plus 4, I get a minus 2. And so on. So let me fill out the rest. So 3 times minus 1 plus 3 minus 3, I get a 0 here. And then 3 times 3, that's a minus 9. 1 times 5 is plus 5. Minus 9 plus 5 gives me minus 4. Okay. Okay. So that's B times A. So B times A is this matrix right here. Okay. And we can do some of the other ones. So I'm not going to do all of them. We don't have room to do all of them, but let's do at least one more. Let's do A times C. So A times C, what's the size going to be? Well, A is 2 by 3, C is 3 by 2, so I look at the numbers on the outside, a 2 and a 2, the size is going to be 2 by 2. Now, I'm not going to compute both of them, but notice that if I did C times A, okay, C times A, the numbers on the outside are 3 and 3. Size 3 by 3, okay. So these two matrices are not even the same size, right? These are different sizes. And what does that tell me? That tells me that regardless of what the entries are, A times C is not going to be the same thing as C times A. They're not even the same size, so there's no hope that these could be the same matrix. So they have to be different. All right, so we'll compute one more just to kind of, again, get a feel for it. Let's do A times C. So let's do A. We'll squeeze it. Actually, let's do C times A. I think that fits in a bit better. 3 minus 4, 1, 0, minus 2, 6. Put A up here. Sorry, let's push that down a bit more. Okay. C, 3 minus 4, 1, 0, minus 2, 6. There's C. A, 2, minus 1, 3, 4, minus 3, 5. Okay. And the resulting product, we can see that the resulting product this time has 3 rows and 3 columns. It's a 3 by 3 matrix. And to work out what the entries are, we do this sort of dot product thing, right? So in the first row, I do 3 times 2 plus minus 4 times 4, so 6 minus 16 minus 10. And then I do 3 times minus 1, 4 times minus 3, so 12 minus 3. I get a 9, and so on. 3 times 3, 9 minus 20, negative 11. 1, 0, that 0 there makes it, I just have to multiply, so 1 times 2 plus 0, so I get a 2 minus 1, 3. That one was easy. And then for the last row, minus 2 times 2, I'm down here now. Minus 2 times 2, 6 times 4, so 24 minus 4 gives me a 20. And then minus 2 times minus 1, 6 times minus 3, minus 18 plus 2 gives me minus 16. And then finally, minus 2 times 3, minus 6. 6 times 5 is 30. 30 subtract 6 gives me a 24. Okay, and I formed that product. Okay, good. One more example, just to kind of play around with these ideas, right? Understanding when is matrix multiplication defined and what can you do with it. I've got two matrices there, A and B. I want to find a matrix X so that A times X equals B. The first thing we might ask is that even possible? Can I do A times X and get B? So I'm trying to solve A. So A is going to be 2 by 2. X is, well, we don't know yet. We want to end up with B. B is 2 by 3. Okay? So that 2 and that 2, that matches up. And we know that x has to be, because of the 2 here, we know that x has to be 2 by something. And what is the other thing? Well, the 3 that we have over here, that guy, tells me that I need a 3 there. So x has to be size 2 by 3. Okay? So that means that x looks like, well, x looks like x11, x12, x13, 21, 22, 23. Can I find the entries of x? Well, let's think about what determining the entries of x. What would that entail, figuring out what those numbers are? Well, I would have to first form, I'd have to do a times x. So what would I get when I do a times x? I would get first row times the first column, I would get 2x11 minus x21. Okay, what I'm doing here is I'm doing this 2 times that guy minus 1 times that guy. So first row here times the first column here. Then I do this row times this column. So I'm going to get 2x12 minus x13. Then I'm going to get, that's wrong, x22. Then I'm going to do 2x13 minus x23. And then when I get to the next row is a little bit easier, 3, 0. So I'm just going to do, it's going to be 3 times that, and then 0 times that, so I don't worry. And then 3 times this guy, 3 times this guy. So I'm going to get 3x11, 3x12, 3x13. Okay. And that has to be equal to minus 1, 0, 3, 0, 2, 4. And now we say, okay, two matrices, they're the same size, so it's possible for them to be equal, and we know that equality means that each entry has the same size. Looking at the second row first is a little bit easier, right? Comparing this entry with this entry tells me that x11 has to be 0. x12, comparing this guy with this guy, we see that x12 has to be equal to 2/3. x13 has to be 4/3. And once we know those values, we can go on and we can figure out what x21, x22, x23 are, because we can take those values, we can plug them in up here and solve the remaining equations. Okay, so part C, I'll let you guys think about that. Can you think about the relative sizes of the matrices? Can you answer the problem, if we're doing x times a instead of a times x? What if we're doing b times x equals a? Do the sizes match up? In which of these scenarios is it even possible to consider the problem? If you can consider the problem, can you figure out what the entries are? Some cases might be easier than others. Okay, so we'll stop here. Okay, so this is our final video on matrix multiplication. In the previous video, we explored essentially the definition. We explored how to compute a matrix product, how to do a times b, and we saw that the general algorithm is you follow this row times column mantra. Rows from the left times columns from the right. You essentially form these dot products, and you take each of those dot products and set them as the entries for a new matrix, which we call the product. So the definition, if you want to write down a formal definition, is given as follows. So we want to form a product a times b. So as we saw in the previous video, if I want to do a times b, then the numbers of entries in the row, each row of a, has to match the number of entries in each column of b. So these two numbers have to match, okay? N and N, they have to match. The numbers on the outside, the M and the P, they tell you what the size of the product will be, right? So checking that those numbers match on the inside makes sure that the product is defined in the first place. The numbers on the outside will tell you the size of what that product should be. Now, once you know what the size of the product is, you need to compute the entries within, right? It's supposed to be a matrix. So what are the entries of that matrix? So the entry that goes in row I and column J is you take row I from A and you multiply by column J from B, right? So for row I, column J, it's row I times column J. But the row I comes from the matrix on the left, the column J comes from the matrix on the right. So if you want to, you can, if you want to kind of write everything down in terms of index notation, if we want to say, well, the product A times B is going to be an M by P matrix with entries Cij, where the formula for each entry Cij is given by an expression that looks like this, right? So notice that the index I for the A's tells you that you're in row I from the matrix A. The J here for the B's tells you that you're in column J for the matrix B. So that's the definition. Rather than trying to kind of remember this formula, which, admittedly is a little bit intimidating with all the I's and J's and the numbers and the A's and the B's and, and if you want to make it really scary, you can use summation notation. Don't worry if you never dealt with summation notation, it's not something that you need in this course, but it certainly allows you to clean things up if you are familiar with it. Here's a nice schematic. This is I didn't make this myself. I borrowed this from a website called TixZ examples. So this TixZ is a package for producing diagrams in documents like this, and so somebody came up with this one. So here's a way of visualizing matrix multiplication. When you want to do the product A times B, arrange them like I did in the last video. Put the matrix A on the left, put it over here. Your matrix B goes on the right, but you shift it up. You put it up and to the right. You put it over here, right? And then you align the rows of A with the columns of B, and that tells you what the entries in your new matrix should be. So each entry here in one of the rows has a corresponding entry in each one of the columns, and we multiply these together. So we do the A's times the B's, A21 times B12, A22 times B22, and so on. We form all those products, we add them all up, and that gives us the entry. So this schematic, I think, gives us a nice way of visualizing matrix multiplication. Okay. So let's do one more example just to make sure we've got the hang of things. Here are two matrices, A and B. Let's compute the product. So if I want to do A times B, right, then for A times B, I should do this. So I put my matrix A on the left, 2, minus 3, 1, minus 4, 0, 3. So there's A. B goes on the right, but I slide it up. Minus 1, 7, 3, minus 4, 2, 0. Okay. So we've got two rows on the left, we've got two columns on the right, and the product has 2 rows, 2 columns, as it should. I'm doing a 2 by 3 matrix times a 3 by 2 matrix. The 3 matches with the 3, so we know the product is defined, and the 2's on the outside tell us that the outcome should be 2 by 2, right? So if we do row 1 times column 1, so row 1 from A times column 1 from B, we've got 2 times minus 1 plus minus 3 times 3 plus 1 times 2, right? So we're doing 2 times minus 1 minus 3 times 3, 1 times 2. We're doing those 3 products. We're adding them all up, so we get minus 2 minus 9 plus 2. We get a minus 9 going in there. Row 1, column 2. So row 1 from A times column 2 from B. So we're going to do 2 times 7 minus 3 times minus 4, 1 times 0. Okay, so that's going to be 14 plus 12 plus 0 gives me 26. And then I can do row 2, column 1. Right, so I'm doing now
entries from row 2 times the corresponding entries in column 1. So do those three products there. Minus 4 times minus 1 plus 0 times 3 plus 3 times 2. So 4 plus 6, I get a 10. And row 2, column 2, same story. Minus 4 times 7 plus 0 times minus 4 plus 3 times 0 leaves me with minus 28. Okay, so that gives me AB. So AB is this matrix, minus 9, 26, 10, minus 28. That's my AB. Okay, what about doing BA? Okay, if I wanted to do B times A, then I put my matrix B on the left, minus 1, 7, 3, minus 4, 2, 0. I put my matrix A on the right, and I slide it up, 2, minus 3, 1, minus 4, 0, 3. And as before, we kind of line things up. We see that the outcome should be 3 by 3. 3 rows on the left, 3 columns on the right. That agrees with our definition. And we go about computing the row times column product. So this time I think I won't bother to write it all out. I'll just kind of work through it. So we do for first row times first column, minus 1 times 2, 7 times minus 4. So minus 2, minus 28, I get minus 30. Minus 1 times minus 3, 7 times 0, so I get a 3. Minus 1 times 1, 7 times 3, so 21 minus 1, 20. Row 2 times each of the columns, 3 times 2, minus 4 times minus 4, so 6 plus 16, it gives me 22. 3 times minus 3, minus 4 times 0, so that gives me minus 9. 3 times 1, minus 4 times 3, so 3 minus 12, minus 9. And then for the final row, 2 times 2, 0 times minus 4, 2 times 2 gives me 4, 2 times minus 3 gives me 6, 2 times 1 is 2, right? I didn't worry about what was in the second row there because those guys are getting multiplied by 0. So that gives me B times A. Minus 30, 3, 20, 22, minus 9, minus 9, 4, minus 6, 2. Okay. And again, one of the things you should take away from this is that B times A is decidedly not the same thing as A times B, right? They're not even the same size, let alone do they have the same entries. And you may be wondering, what if I came up with an example where AB and BA did have the same size? Would it be true then? And the answer is still no. It's quite rare, in fact, for matrices that A times B equals B times A. In almost all cases, the order actually matters. So the order in which you multiply matrices matters. And so this is something that we don't encounter with numbers, real or complex. Most of the multiplications that we've seen so far in our lives are ones where A times B is always the same thing as B times A. But for matrices, this is just not true. And maybe one way to think about why it's not true, if you think about the example in the very first video, I mentioned that you can kind of think of each matrix as defining some sort of function associating one set of variables with another set of variables. And multiplying matrices, it turns out that multiplying matrices is kind of like composing functions. And you might remember from high school that the order in which you compose functions matters, right? F composed with G, F of G of X is not always the same thing as G of F of X. You probably saw some examples like that. And so if you think of matrix multiplication as related to function composition, then the fact that A times B is not equal to B times A might make a little bit more sense. Okay, so that property is out the window. We don't have commutativity for multiplication, but we do have some other properties. So it is distributive. And by the way, because A times B is not equal to B times A, I actually have to give two distributive properties, right? One for multiplication on the left and another one for multiplication on the right, because multiplying on the left is not the same thing as multiplying on the right, because A times B is not the same thing as B times A. So two different distributive properties.
I have an additional property saying that if I have a scalar inside of a matrix product, I can move that scalar around. I can pair that scalar with B, I could pair it with A, I can put it here, I can put it here, or I could bring it right out front. I could do the matrix multiplication and then do the scalar multiplication. And so although matrix multiplication is not commutative, it is associative. If you want to multiply 3 or more matrices, as long as the sizes match up, right? So those have to be the same and these have to be the same, right? As long as those guys match up, then I can do A times B times C. And it doesn't matter whether I first do B times C and then multiply by A, or whether I do A times B and then multiply by C. And by the way, this one really is necessary here, right? With addition, you can mentally do addition of 3 or more things without having to group things together. You can kind of add 3 things at a time. If you're doing matrix multiplication, this is really a necessary step. If I want to multiply 3 matrices together, I have to choose to group them one way or the other and do one multiplication followed by another. There's no natural way of doing all 3 multiplications at once. You really have to do one pair at a time. You've got to break it up like that. Okay, so almost done. One last thing to note is there are a couple of matrices that pop up that are of worth mentioning. One is the zero matrix. We've seen the zero matrix before, right? The zero matrix. So there's one for each size. So this is just the matrix with all zeros. Right? And we already know that the matrix, the zero matrix, acts as the additive identity for matrix addition. But it's also true that if I take the m by n zero matrix and I multiply by any other matrix, say n by k, right? Multiplication by 0 gives me 0. But notice that the size might vary. If I take an n by k matrix and I multiply by the m by n zero matrix, I get a zero matrix, but it's of size m by k. It would also be true that if I took say, if B was an m by n matrix and I multiply by, actually it's, maybe B is size, let's say P by Q, and I want to multiply by a zero matrix, then that zero matrix, well, it's going to have the right size, so it's going to have a Q there, Q by R, let's say. That also will give me the zero matrix, but it's going to be a zero matrix of size P by R. Okay. Now, the identity matrix. So the identity matrix, what you're looking for here is you're looking for a matrix, say IN, and it's always going to be a square matrix, and you're looking for something that acts like 1 with respect to multiplication, right? So you would want A, if A is, say, m by n, and you multiply by the n by n identity matrix, you want to get back A, and if you multiply on the other side, well, you've got to adjust the size. It's going to have to be m by m times A, m by n. That nothing should happen. So you're looking for a matrix where multiplying by that matrix does nothing. It turns out you might think your first guess might be to take a matrix consisting of all ones, right? Since the zero matrix consists of all zeros. But if you think about the way, because when you do matrix multiplication, you are adding when you form those dot products, right? If you put everything equal to 1, you would just be adding up all the entries in each column, and you wouldn't have this property. So what you actually want is you want ones just down what's called the diagonal. So you want ones down the diagonal, and you want zeros everywhere else. 0, 0, 0, 0, 0. So that's what the identity matrix looks like. Ones down this this so-called main diagonal, like so, and zeros everywhere off of that diagonal. That's the identity matrix. And you can check that it satisfies these properties. Okay, that's it for matrix multiplication. Okay, so this will be the first of 4 videos on matrix transformations for Math 1410 linear algebra for the spring 2017 semester. So the idea here is that we want to sort of think of this matrix multiplication that we've defined, this sort of strange definition for matrix multiplication, and we want to make sense of this definition as a function, as a way of turning one vector into another vector. Right? So the idea here is that if I start with the matrix A, right, so A11, A12, down to A1n, and A21, 22, down to A2n, and so on down to say M1, M2, down to Amn. Right? So this is an m by n matrix, and x, my column vector, is x1, x2, down to xn. That's an n by 1 matrix. So we know that the sizes here are compatible, right? The n here matches with the n here. These are the right size where we can multiply them. We can do this matrix times column multiplication like we've done now many times when we're doing matrix multiplication. We know how that works. And notice that what we get a new vector, so we get y, right? So y is going to be, y1 down to ym, right? And we want to define y as a times x, right? So if I actually carry out that multiplication, right, I'm going to get a11 times x1 plus a12 times x2, and so on down to a1n times xn, right, and so on all the way down. That's the first entry, all the way down to the last entry, a m1 times x1, a m2 times x2, down to a mn times xn, right? And don't be thrown off by the fact that this matrix on the right is really wide, right? Because we've got a sum. Each entry is a sum. This is a column. This is a column vector. This is an m by 1 column vector, just as this is an m by 1 column vector, right? This is a column. This is a column. Both of these guys are column vectors. It's just that each entry in this column on the right is expressed as a sum. So it takes up a lot of room on the page, right? So one way that you can think about this is one way you might think about it is you can think of this as defining each of the entries in this vector y. You can think of it as defining each of these entries as a function of the entries in the vector x, right? So yi is equal to ai1 x1 down to ain xn. All right, so we can think of this as a sort of linear function of these variables x1 down to xn, right? And so you can think of this as you sort of start with n variables, x1 down to xn, and you have sort of m new variables, y1 down to ym. And so you can think of this, if you like, as a function, right? So we get what we get is a function let's call it t so it's going to go from Rn to Rm, thinking of these as spaces of vectors, and so t of x is equal to a times x, right? This is sort of the many variables analog of a linear function in one variable, right? Think about in one variable, you're thinking about something like y equals a times x. That's your sort of very basic example, where you can think of that number a as like a 1 by 1 matrix, if you like. So basically what we're trying to do here is we're trying to generalize this humble little linear equation here. Notice that I didn't do ax plus b. We're in the context of linear algebra, so remember, we usually in linear algebra we want to preserve the origin. Think about when we talk about subspaces, right? 0 plays an important role, and we want to make sure that if we think of the graph of this thing, that's something which passes through the origin. Okay. So we have this idea of using matrix multiplication to define a function. By the way, one of the things that we're not going to discuss in these videos, I'm not going to go through the details. There are some details in the textbook if you're interested in. If you want to kind of understand this strange definition for matrix multiplication, one way to understand it is that once you sort of think about defining functions in this way, where you define a new vector as taking an old vector and multiplying by a matrix, if you move on and you think about composition of functions, so doing a times x to get a new vector y, and then if I did b times y, which would be b times a times x, this is sort of like composition of functions. And it turns out that if you take functions of this type and you compose them, you are sort of forced in to the definition of matrix multiplication that we have. Okay, so just to recap, we can do this generally. We think of this as a function, so we think of this t as a function. This is a linear function. So it takes vectors in Rm. So we want to think of these guys here as spaces of vectors. Right, so for every vector in Rn, it multiplies by the matrix A, giving us a vector in Rm. I should be careful here. This should be an M there in that last entry. Okay. So as we said, we can think of this as, if you like, as a function of several variables, or as several functions of several variables, one for each of the y coordinates. Each of the y coordinates is defined as a function of the x coordinates. Okay. So here's a very simple example. We want to use this matrix A to define t from R2 to R2 by t of x equals a times x. So we can play around with that. We can say, okay, so let's just kind of let x equal to x1, x2. What does t of x look like? T of x looks like 2, 3, minus 1, minus 2 times x1, x2. And we can write that as 2x1 minus x2, and then 3x1 minus 2x2. And by the way, notice one of the things we did when we were playing around with subspaces and other examples like that is that, we can take something like this and we can decompose it, right? We have a matrix with two variables in there. One of the things we might do is we might say, let's write this as 2x1, 3x1 plus minus x2 minus 2x2. Let's write that as x1 times 2, 3 plus x2 times minus 1 minus 2. And notice that what you have here, this is sort of the first column of A. This guy is the second column of A. This is sort of a general pattern that we're going to see. We talked about this a little bit when we talked about doing matrix multiplication. We talked about doing this matrix times column product. We said there are two ways you can do that, right? You can do it by doing this row times column rule that we always use when we multiply matrices, but we also said that actually when you're dealing with a column, matrix times column, you can think of that product as forming a linear combination of the columns of your matrix A, where the coefficients in that linear combination are the entries in this column vector here. And we see that in this case. And so one of the things that might tell you is that if y is equal to t of x, then y belongs to the span
of these two vectors, 2, 3, and minus 1, minus 2, right? Every possible output from this function is a linear combination of those two vectors, right, for some choice of coefficients x1 and x2. And this will be relevant because one of the questions that you might have to answer if you're dealing with a function like this, one of the related questions is, you know, if I give you y, you might ask, well, can you solve the equation, you know, a times x equals y? Can you solve this for x? And you know, if you can solve it, can you do it uniquely? That's also a related question. So there are a lot of problems like this that you can ask about these matrix transformations, which are related to a lot of problems in linear algebra and to systems of equations that we're going to encounter as we move forward through this material. So you can play around with something like this. You can plug in different values for x1 and x2, and you can see what you get. But one of the things that you will notice is that you always have this pattern that when you calculate the output of a matrix transformation, the output is always given by taking some linear combination of the columns of the matrix that you use to define that matrix transformation. And by the way, in this case, you know, if we wanted to answer this this question in this particular example, the answer to both of those questions is yes. Why is the answer yes? Well, if you look at the two columns of this matrix, those two vectors are not parallel. They're clearly not parallel. They're not scalar multiples of each other. And we know that any two non-zero, non-parallel vectors span a plane. That plane in question in this case is all of R2, right? So the span of those two columns is in fact all of R2, and that means that every single vector y in R2 belongs to that span. So we can find an x so that a times x equals y in each case. And the uniqueness, we'll see later on that the uniqueness follows from the fact that those two vectors are in fact independent. Okay. Now, these sorts of functions that you define using matrices, these are special cases of what are called called linear transformations. Linear transformations are studied in an abstract linear algebra course. In fact, they're kind of the main object of study in an abstract linear algebra course. But if the only vector space you're going to look at is Rn or Rm, then the only linear transformations that you need to look at are matrix transformations. And there are a couple of important properties. So for any matrix transformation, T from Rn to Rm. By the way, this notation, if you've never encountered this notation before, this is just a way of saying that the inputs all come from Rn, and the outputs, they all land in Rm. And so we know that our matrix transformation is going to look like T of x equals a times x, and we know that this a has to be m by n. Now, just working with properties of matrix transformations, you get a few things for free. You get that T of x plus y, okay. Well, by definition, that's a times x plus y. And we know that matrix multiplication is distributive, so I can write this as a times x plus a times y. But if we use our, you know, that's by definition of our matrix transformation. This is T of x plus T of y, okay? And so this tells you that that this plays nice with respect to addition. In fact, it kind of turns one addition into another addition, because this this addition here
is addition in Rn, right? X and Y are both vectors in Rn. This addition over here, well, t of x and t of y, those are both vectors in Rm. Okay, so not only does it turn vectors in Rn into vectors in Rm, it also turns the addition in Rn into the corresponding addition in Rm, right? And the same thing is true for scalar multiplication. Okay, if I take any vector x and any scalar c, right, then that's a times c times x. And again, one of the properties for matrix multiplication says you can take that scalar and you can pull it out in front. You can write that as c times ax, which is c times t of x, right? And again, on the left, the scalar multiplication is taking place in the domain Rn, and the scalar multiplication on the right is taking place in the codomain in Rm. So this is one of the reasons why linear transformations are important, is that they not only take you from vectors in one space to vectors in another space, but they also kind of match up the addition in one space with the addition in the other space, and the scalar multiplication matches with the scalar multiplication in the other space. And so, some consequences of this are, well, one thing you might note right away, if you set c equal to 0 in the second property, one of the necessary conditions for any linear transformation is that it has to take the 0 vector in Rn and maybe put a little n there to say that's a 0 vector in Rn. That has to be transformed to the 0 vector in Rm. And the other thing you might note is that you can consider sort of any linear combination ax. If you combine 1 and 2, you have a times t of x plus b times t of y. All right. So that's those are the basics for matrix transformations. We'll look at some specific examples in the next video. All right, this is the second in our series of videos on matrix transformations. So in this video, we're going to concentrate on, well, matrix transformations of the plane, meaning that we're only going to look at the case of transformations going from R2 to R2. So that means we're looking at matrix transformations of the form t of x equals a times x, where a here is going to be a 2 by 2 matrix. So the reason that to concentrate on the case of transformations of the plane is that we can actually visualize things a little bit better. Now, to kind of get us started here, let's think about a general 2 by 2 matrix, A, B, C, D. Define our matrix transformation in terms of A. And let's think about what happens to these 4 vectors under this transformation. Now, you may be wondering, why do we care about those 4 vectors? Well, the reason we care about those 4 vectors is that those 4 vectors, they represent the 4 corners of the so-called unit square. 0, 0, 1, 0, 0, 1, 1, 1. And so if we want to understand a matrix transformation visually, it's often useful to think about what happens to this little square in the plane. If we understand what happens to that square, we can understand a little bit better what happens to vectors generally, and we can get a nice visual picture. Now, one of the things you might want to do here is you might want to note that, well, the 2 of the 4 sides of that square, this guy and this guy, those are just your basic unit vectors in the plane, I and j. Of course, this corner here is just the 0 vector. The far corner, well, we know that that's I plus j. Now, we know from what we worked on before, we know that t of the 0 vector is always the 0 vector. We know that that stays put. What happens when I put in 1, 0? Well, let's actually work that out. B, C, D times 1, 0. I get a times 1 plus b times 0. I just get a. Then c times 1 plus d times 0. I get c. I get, you might have guessed this, I get the first column of a. And you can probably guess, if you haven't already,
what happens when I plug in 0, 1. When I plug in 0, 1, I get the second column. Okay, so there's the second column. Now, as for the far corner of that square, 1, 1, recall that one of the things we can do with a matrix transformation is it distributes over sum. So t of I plus j is t of I plus t of j. So if I add those two together, I'm going to get a plus b, and I'm going to get c plus d, right? So notice that if I want to visualize this, once I know where t of I and t of j go, I can add them together to figure out where the far corner goes. So what ends up happening is t of I ends up, and the actual location of these guys can be pretty unpredictable, but maybe there's t of I there, and maybe t of j ends up, maybe it's there, okay, and for t of I plus j, we can do our parallelogram trick. We know it ends up over there. That's t of I plus j, which is t of I plus t of j. Okay. And so what we end up with is something that looks like that. So our little square that we had gets transformed into a parallelogram. And of course, the exact details of what happens are going to depend on the numbers, right? Maybe we might not even get a parallelogram. Maybe t of I is parallel to t of j, and everything just collapses down to a line. Maybe this thing gets flipped. Maybe it gets rotated. Maybe it's bigger. Maybe it's smaller. There's lots of possibilities that can happen here if we want to look at a general transformation. So this drawing is not representative of every possible transformation, but it does represent one possibility. To look at another possibility, let's try an example with concrete numbers. So let's plug in some numbers. We'll let t of x equal to a times x. Right? So we know that t of I is going to be 1, 3. We know that t of j is going to be minus 1, 4, right? Plugging in 1, 0 gives me the first column. Plugging in 0, 1 gives me the second column. And if I wanted to kind of sketch things out here, in this case, we put in our little unit square. Here's I. Here's j. So t of I, well, 1, 3, so I go over 1, up 1, 2, 3 is going to be there. Okay. There's t of I. T of j, I go 1 to the left and up 1, 2, 3, 4. There's t of j. And for the sum, well, we know how to do that. We add these guys up, and we get this guy here. And there's t of I plus j, right? So t of I plus j, we know that's t of I plus t of j. So that's 1, 3 plus minus 1, 4. I get the vector 0, 7. And you can check that that's the same thing that I would have got if I had started with 1 minus 1, 3, 4, and then multiplied by the vector 1, 1. Okay. So in this case, we can see that our little unit square, it grew quite a bit. But you can sort of see how the transformation goes. You can imagine sort of grabbing this corner and stretching it up until it reaches that far tip up there. And if everything else kind of stays if everything that's currently a straight line remains as a straight line, and everything transforms proportionally, when I stretch that far corner up, I'm going to get that parallelogram. Okay.
here's one more example. We've got a few particular vectors here. We just want to see what happens to those when we transform them. So we can calculate t of x, 1 minus 2, minus 2, 4, minus 1, 1. Now this one's a little interesting. What happens here? I get, let's see, minus 1, minus 2. I get minus 3. And then I get 2. And then I get 2 plus 4. I get 6. Okay. What about t of y? Let's just do the other ones quickly. T of y, I'm going to get, well, it's just going to be 2 times the first column. I'm going to get 2. I'm going to get minus 4. T of z, let me throw that one up here. I'm going to get 3 times 1, that's 3, minus 2 gives me a 1. 3 times 2 is minus 6, and then I'm adding 4, I get minus 2. One of the things you might notice here is that all of these guys are parallel. So notice that in this case, t of x is minus 3 times t of z, and t of y is equal to 2 times t of z. And what's interesting is we also know from the linearity properties here, we know that scalars can move in or out. So this is the same thing as t of minus 3z. This is the same thing as t of 2z, right? But what's minus 3z? Minus 3z is, that's minus 9 minus 3. And and what's 2 times z? 2 times z is 6, 2, right? All of these come out to be the same thing. So t of x, this minus 3, 6, I would get the same thing if I, so here I'm plugging in minus 1, 1. I would get the same thing if I plugged in the vector minus 9, minus 3. This vector here, 2 minus 4 for t of y, I would get the same thing. Instead of plugging in 2, 0, if I plugged in 6, 2, I would get exactly the same thing. Okay, so that's quite interesting. What happens, if we tried to sketch things? I'm not going to sketch them all, but let's sketch a couple of them. So where's x? X is here. Y is there. Z is there. And where's t of x? T of x is going to be kind of minus 3 up 6. T of x is going to be kind of around here. Okay, t of y over 2 down minus 4. T of y is kind of down here. T of z. T of z is half as long as t of y. T of z is sitting there, right? So the output, in this case, the output is always a multiple of this vector 1 minus 2. Now, you might notice that, we can guess why, right? Why is this happening? This is happening because this guy here, the vector minus 2, 4, well, that's minus 2 times the vector 1 minus 2, which is the first column. So the second column of my matrix is a multiple of the first column. The two columns as vectors, the two columns are parallel, and so we know that if I was doing, in general, if I was doing a times x1, x2, I would be getting x1 times 1 minus 2 plus x2 times minus 2, 4, right? But that's going to be the same thing since this guy here, this is minus 2x2 times 1 minus 2. I get x1 minus 2x2 times the vector 1 minus 2, right? So everything is parallel to that vector 1 and minus 2. The other thing you might notice is that from here's my coefficient. So, if x1 is equal to 2x2, then I get 0. So there are lots of, in fact, we know that the 0 vector goes to the 0 vector, but in this case, there are actually lots of non-zero vectors that also go to the 0 vector. So, just as an example, a of 2, 1 gives me the 0 vector. We'll discuss later on that there are some connections here. If you have non-zero vectors that get sent to the 0 vector, that's basically your clue that something like this is going to happen, where the output of your matrix transformation, instead of giving you that nice parallelogram that we saw in the previous example, everything just collapses to lie along the same line. So in this case, if you want to think in terms of, say, the range, right? The range of this as a function is only vectors that are parallel to this guy, 1 and minus 2. Right? So the range ends up being a line through the origin. The range is one-dimensional, whereas in the previous example, the range is two-dimensional. And this is, so the fact that in this case there's a non-zero vector that gets sent to 0, that is actually not a coincidence, and we'll talk about that later. Okay, now, we saw in the last few examples that if you know the matrix, then it's easy to calculate t, the value of t on both 1, 0 and 0, 1, because those are just the columns of your matrix. Well, you can reverse this process, right? We know that if t of x is equal to a, b, c, d times x, then we know that t of 1, 0 is a c, which in this case has to be this vector 3 and minus 1. We know that t of 0, 1 is b, d, and in this case we're told that that is the vector minus 2 and 4. And so now we know what A is, right? So if this is my matrix A, then A is going to be 3 minus 1 minus 2, 4, right? So knowing the value of our matrix transformation on just those two vectors completely determines its value on every other vector. But that's not so surprising from the properties of matrix transformations, right? It's not surprising that those two vectors are all we need, because if I wanted to do sort of t of xy, right, I can think of that as, so x times I plus y times j, and now I use the fact that I can distribute that across the sum. X and y are scalars. I can pull it out. I get x times t of I plus y times t of j, right? So as soon as I know these two values, the value of t on I and j, I know the value of t on every single vector, because I can always form this linear combination. So there are two ways that you can compute. If you have another vector that you want to compute the value of t on, either you can, if you know the value on 1, 0 and 0, 1, you can reconstruct the matrix, and you can use the matrix to calculate the value of t on some other vector, or you can appeal directly to the properties. You can simply push t through, as we've done here, and calculate it that way. So, for example, if I wanted to do t of 2, 3, I would get 2 times t of I, which is 3 minus 1, and then 3 times t of j minus 2, 4, and then I can simplify that. And what do I get in this case? 0 and 10. Okay, now there are a number of sort of common transformations of the plane that are sort of geometric. They're easy to understand. These are ones that that you may have run into in the past, but you probably ran into these in the context of graphs, transforming graphs, reflecting a graph across an axis. rotating, stretching, shrinking. The one that we don't look at here is translations. We don't look at translations because translations do not preserve the origin, so they're not a linear transformation in the sense that we consider, right? So there are a number of reflections that we can consider depending on how you want to reflect. So for reflections, we can think about ones that go across the x-axis, across the y-axis, or even across the origin. Rotation by some angle of, say, theta, stretches, shrinks. There are a number of transformations that you can do. So if I want to think about, for example, let's say I want to reflect across the x-axis. Okay. So what does that look like? If I think about it in terms of points, right? If I have a point up here, xy, and I reflect across the x-axis, right? So I'm constructing the mirror image on the other side of the x-axis from that point. Well, the x-coordinate remains unchanged. The y-coordinate is now the opposite sign of what it was before, right? It's the same distance away from the x-axis, but on the other side. So you can think about that in terms of, you can think about it two ways. You can think about it like this. You can think about it as, t. So think of these guys at those points as vectors. Then what this says is that t of xy should be x and minus y, right? And so I want to write that down as a matrix. So what should the matrix be? Well, what happens to 1, 0? Nothing happens to 1, 0. T of 0, 1. Well, that's going to become 0 and minus 1, right? But we can see that if we, if you draw those guys in, right? I, J, right? So if I reflect I, nothing happens because it's already on the x-axis. It's got nowhere to go. But this guy, if I reflect, well, it's going to get flipped over. T of J is down here, right? But now I know what my matrix should be because I know that the values of t on these two vectors give me the columns of my matrix. I get 1, 0, 0, minus 1 times xy, right? And every other transformation can be figured out in a similar way. The only one that it takes a little bit of work, it takes a little bit of trig knowledge to figure out is the rotation. If I start with a vector v, t of v is here, and if t of v is obtained by simply rotating through an angle of theta, then it turns out that t of v, the matrix for this rotation, is cos theta and then minus sine theta, and cos theta. Well, times v. Maybe I should just simply say that the matrix in this case is given by that. So this rotation matrix, this works whatever the angle theta happens to be. If you're dealing with a rotation through an angle of theta, a matrix of this form will do the job for you. So you'll see a few of those pop up in the examples in the textbook. All right. So here's an example. Here's a common example thinking about transformations of the plane. Now, a general transformation of the plane might be formed by doing several of these basic transformations in some sort of order. Okay, so we want to think about it this way. We start with so think about doing kind of a general. There's a couple ways to do it. But think about doing a general vector. So I start with some v, right, and v is going to go first. So first we're going to stretch, right? And so I'm going to apply a stretch transformation. I'm going to call that T1. Okay? So I get a T1V. Okay? Then I'm going to rotate. Right? So what am I rotating? I'm not rotating the original vector. I'm rotating the one that I've already stretched. So I've got a new function t2. And what do I plug into t2? I put in t1. Okay. And then I'm going to reflect. And so when I reflect, I've got a new function. I've got a function t3 that does the reflection for me. And what do I plug in? Well, I plug in this guy here, the one that's already been rotated and stretched. So t3, t2 of t1 of v. And here we see that we have this function composition going on. Now we want to think about this in terms of a matrix, right? So t1v, this has to be given by a1 times my vector v, right? And now t2, that's given by multiplying by some matrix a2, right? But I'm multiplying, you know, the input always goes on the right, so it's a2 times a1 times v. And then similarly here I have a3 times a2 times a1 times v. Okay, and so this guy here is, I could write this as simply a times v, where a is a3, a2, a1, right? Be careful of the order. Notice it goes 3, 2, 1. It doesn't go 1, 2, 3, and that's simply because the input always goes on the right. And so when you apply, each time you apply a new function, that function is applied to the left of what you already have. So how do we do a vertical stretch? What does a vertical stretch look like? Well, a vertical stretch means that you're leaving this guy alone, right? So I doesn't have any vertical component to it, so it gets left alone. J, on the other hand, gets stretched up by a factor of 4, right? So T of J is here. So what does A1 look like? A1 must look like, well, nothing happens to I, but J gets multiplied by 4. So my vertical stretch looks like that, 1, 0, 0, 4, right? We're multiplying the Y value, but not the X value. That rotation through an angle of pi over 3, A2, if I use the formula I had before, that's cos pi over 3 minus sine pi over 3, sine pi over 3, cos pi over 3. And so that is going to be 1/2 minus root 3 over 2, root 3 over 2, and 1/2. A3. A3 is a reflection across the y-axis. Let me just hop back for a second. If I were to reflect across the y-axis instead of the x-axis, that would mean reflecting this way. That would mean changing the sign of the x-coordinate instead of the y-coordinate. So instead of having a -1 down here, I would have a -1. So this, instead of this -1, I would put a -1 there. So the x gets multiplied. So I get -1, 0, 0, 1. Okay. So my matrix T. Oh, you guys again. All right. So T of x is equal to A times x, where A is just this product. So I'd have to do A3 times A2 times A1. Multiply those three guys together, and that would give me my my matrix. Okay. Okay, so this is the third of 4 videos on matrix transformations for Math 1410 Linear Algebra, Spring 2017. And this is just going to be a quick overview of a couple of things we've done, and in particular, generalization of something we saw in the last video, which is that for a transformation of the plane, for a matrix transformation from R2 to R2, if I only know the value of my transformation on the basic unit vectors, I and j, 1, 0, and 0, 1, then I can reconstruct the matrix used to define that transformation. This turns out to be something that's true in general. If I know the value on sort of my basic unit vectors, whatever the dimension happens to be, that's enough to figure out my matrix transformation in general. Right? So recall that for any linear transformation T going from Rn to Rm, the two rules that it has to follow are that T of x plus y has to equal T of x plus T of y. So this is true for any x, y in Rn. And 2, if I have any scalar c in vector x, I can pull the scalar out. Okay, and this is true for any scalar c and any vector x in Rn. Okay, and so one of the things you'll note in general is that if we let, let's call them maybe E1, so E1 being 1, 0, everything else is 0. E2 is going to be the vector with a 0 and then a 1, and then everything else is going to be a 0. So 1 here, and then everything else is 0, and then so on down to, let's say, En, 0, 0, and 1 in the last spot. Then if I have any general vector x equal to x1 down to xn, I can write it as x1 times E1 down to xn times En. And if I wanted to calculate T of x, right, using properties 1 and 2, it tells me that T of x is going to be x1 T of E1 down to xn T of En. If I use these properties repeatedly, I can get down to this sort of situation here, right? So it's always true that if I know the values of my transformation on these basic vectors, then I can get the value of that transformation on any other vector. But we can also work out what the matrix is, because remember that the value of T on each of these guys, T of E1, that's going to be the first column of A, T of E2 will be the second column of A, and so on. Okay, so here's an example. I give you a formula for the transformation, right? So I tell you, it goes from R3 to R3, so my input is a general vector x, y, z. The output is more complicated, but we notice that all 3 entries are linear functions of x, y, and z, so I expect that this guy should be linear. I'm going to leave this as an exercise for you guys to check, because it's not hard, but the details aren't going to really fit very well on one slide. So you'd want to check that, for example, T of x1 plus x2, y1 plus y2, z1 plus z2, right? So this would be, if I put in the vector x1 plus the vector x2, you'd want to check that that would be the same thing as doing T of the vector x1 plus the vector x2, and so on. So checking that it's linear is just verifying those 2 properties from the previous slide, but even for something reasonably simple like this, it's a little bit tedious. Probably the easier way to check is is to kind of play a game similar to what we did with subspaces and say, well, you know what, I can write this as x times 2, 1, minus 2 plus y times minus 1, minus 3, 0 plus z times 4, 0, 5, right? Decompose this vector, which depends on 3 variables, into the 3 vectors depending on 1 variable each. And if you kind of reverse engineer this row matrix times column rule from matrix multiplication, remember we said one of the ways you can do matrix times column is you form a linear combination of the columns of your matrix. If you kind of back that up, you can work out that what you should get here is, well, you should get 2, 1, minus 2, minus 1, minus 3, 0, 4, 0, 5 times x, y, z. Okay, so we can, we can kind of, reverse the steps. Start here, right? Start here, and kind of work backwards. Do the matrix multiplication and confirm that these guys here are in fact equal. And you can just simply do that matrix multiplication. You can see that they are exactly the same. And now that we know it is a matrix now we know it's a matrix transformation, we know that it's linear because every matrix transformation is linear. And that sort of negates the need to do this exercise, to do it manually, right? So you could do it by hand, you could do it by brute force, but it's not really necessary. So the way you can do this, rather than kind of, playing around with this sort of algebraic hocus pocus, is you simply, like we mentioned, calculate the value on each basic vector. So t of 1, 0, 0, I put x equal to 1, y and z both equal to 0, and what do I get? I get 2, 1, minus 2, right? And you'll notice I get it here, and I get it there, right? If I do t of 0, 1, 0, what do I get? I put x equals 0, z equals 0, y equals 1, I get minus 1, minus 3, 0, and again we see that those guys match up. Okay, and finally, if I calculate t of 0, 0, 1, I put x and y equal to 0, z equal to 1, I get 4, 0, 5, and we see that those guys match up, right? So calculating t on basically I, j, and k gives you the columns of your matrix and allows you to reconstruct your matrix A. Okay, good. So here's another example, this time going from R3 to R2. So I've given you the value on I, j, and k. I want to calculate the value of t on some other vector, 2, 1, minus 3. So there are 2 ways that you can do this. One way that you can calculate this is you can say, all right, so t of 2 minus 1, 3, right? If I take that vector and write it in terms of I, j, and k, that's 2i plus minus 1j plus 3k. And using the properties of matrix transformations, that's going to be the same thing as 2 t of I minus t of j, minus 1 times t of j, plus 3 times t of k. So that's 2 times the vector 3 minus 1, subtract the vector minus 4, 5, plus 3 times the vector 1 minus 2. And if I simplify that, I'm going to get 6 plus 4 plus 3, I get 13, minus 2 minus 5 minus 6, I get minus 13. Okay. All right. So that's one way to do it. The other way to do it is I just simply construct my matrix, right? So I can say the other way to do it is I simply say, well, t of x is equal to a times x, where what is a? A is, well, these 3 guys here, they form the columns of my matrix. 3
minus 1, minus 4, 5, 1, minus 2. And then I can check that if I take A and I multiply by 2 minus 1 and 3, I get 2 times 3 minus 1 times minus 4, 3 times 1, so 6 plus 4 plus 3, 13. And the second entry, minus 1 times 2 minus 1 times 5, 3 times minus 2 minus 2 minus 5 minus 6. I get minus 13. The same as before. So either method works, and you can work with whichever one you want to do. If you're simply doing one computation, you might want to stick to the option on the left. If you need to calculate the value of t for several vectors, then it's probably worth your while to first work out what the matrix is, because once you have the matrix, you can then calculate the value of t of x on any other vector. Okay, so this is our last video on matrix transformations for Math 1410 for spring 2017. This is sort of a slightly more advanced topic associated to matrix transformations, something that if you do take Math 3410, you will see a lot of this sort of thing, but it's worth kind of taking a quick look at this, because it's something that that kind of, well, one, helps us understand what's going on with some of these examples we've seen. Especially that example we saw where, a transformation of the plane, where when we transformed our little square, we didn't get a parallelogram, we just got a line. So what's going on there? And it's also going to give us kind of a good segue into talking about systems of linear equations, which is coming up in the next section. Okay, so we mentioned before that you can, because we're thinking of our matrix transformations as functions, one of the things you can talk about with a function is you can talk about the range of a function, right? You can talk about all the possible outputs that a function produces. So, as you consider every possible value for this vector x in Rn, what are all the vectors of the form a times x that you can produce? Right, so in other words, which vectors y in Rm, in the codomain, which vectors y can be written as t of x for some vector x, right? What are all the possible outputs, right? So you might want to know, can you solve this equation? And this equation here, this turns out to be a system, right? This is a system of linear equations. And so practically the question of whether or not you can actually solve this thing is a question about solving systems of equations, and we need to develop some machinery for doing that. The uniqueness question, well, the uniqueness is also going to pop out when we look at solving the system of linear equations. But it turns out that uniqueness is related to finding vectors that get sent to 0. Okay. Now, well, let's just think about this in this example. Okay, t of x equals a times x. We were wondering, okay, what does the output look like? What does the range look like? Okay, so we write x is equal to xy, right? And we look at a times x. So a times x is going to be 2, 4, minus 1, minus 2 times xy. Okay, so I'm going to get, let me do it this way, x times 2, 4, plus y times minus 1, minus 2. Okay, but one of the things I can do here is I'm going to do, so this is 2x times 1, 2. I'm going to pull out, there's a common multiple of 2 there, and I'm going to pull out a minus sign from the other one. 1, 2. So I get 2x minus y times this vector 1, 2, right? And so what this tells me is that
the only way that y can equal a times x the only way that's actually possible is if y is some scalar multiple of this vector 1, 2, right? So y has to belong to the span of this single vector 1, 2, so the solutions all lie along a single line, right? And that means that, any vector which is off of that line, not parallel to that line, you're not going to be able to solve. So the answer to whether or not you can solve is, well, no. The other thing you will notice is that this solution is not unique, right? Once I give you a y, there's actually many possible solutions. And the reason there are many possible solutions is that if I do a times the vector 1, 2, okay, what do I get? 2 times 1 minus 2 times 2, I get 0. 4 times 1 minus 2 times 2, so I get 0, right? So interestingly enough, 1, 2 plugged back into A gives you 0. So somehow this vector 1, 2. Now this is purely coincidence in this case. Normally this doesn't necessarily happen. It's interesting that it happens here. That this vector, which plays a key role for the outputs, is also relevant to the inputs. Usually these are different vectors, but this time they come out to be the same. So that's true. So if I call this guy, let me call this thing x sub 0, okay? So because I have that, what that tells me is if I had, any other x, I could add on a scalar multiple of this x sub 0, and I know that that would be equal to a times x plus t times a x 0. But this guy is just the 0 vector, so I get a times x, right? So if I have one solution, if I have one value of x that works over here to solve for my y, I actually have infinitely many solutions because I can augment that particular vector x with any scalar multiple of this vector 1, 2. So I get an infinite number of solutions. Okay, now the key thing to note here is that the values of y where I can solve are the ones which happen to be scalar multiples of this vector 1, 2. And that vector 1, 2 generated both of the columns, right? The first column was 2 times that vector. The second column was minus 1 times that vector. This vector 1, 2 is sort of a basis for the set of all linear combinations that you can form from the columns of A, right? It's a basis for the span of the two columns. So this this has a name, okay? So the column space of A is denoted by col A, and it's simply the span of the columns using this notation up here, column 1 down to column n, right? So the column space is just all the possible linear combinations you can form from the columns. And so what we kind of, understood through our example, and it turns out this is true in general, is that the column space of A is equal to the range of T, where T of x equals A times x. So in other words, this equation y equals A times x can be solved for x if and only if y is in the span of the columns, if y belongs to the column space. Okay, right? And we can see that up here, right? Anything which is in the range, anything which is a multiple of A, so if y is equal to A times x, then it's automatically in the column space because A times x can always be written as a linear combination of the columns. And then conversely, if I was given a y and I knew that it was that I could write it as a linear combination of those columns. I could figure out what the coefficients are and use those to form my vector x. Okay, so that's how the column space is. It's just all the vectors that you can form by taking linear combinations of the columns of your matrix, and that turns out to be exactly the range of the corresponding linear transformation. Okay, all right. So a couple more examples. In the case of this guy here, we notice that the column space of A, well, it's going to be the span of the vectors 1, 2, minus 1, 1. And those are two independent vectors. They're not parallel, or sorry, they're not parallel to each other. Neither one of them is 0. And that means that you can actually get every vector in R2 using these two vectors. Figuring out what they are, that takes a little bit of work, right? So if I had x, y is equal to a times 1, 2 plus b times minus 1, 1, well, then I could try to solve for a and b in terms of x and y. A minus b would have to be x. 2a plus b would have to be equal to y. And I could do it. 3a would give me x plus y, so a would be equal to x plus y over 3. B then would be equal to what? Y minus 2a, so it would be equal to minus 2x plus y over 3. I think that works. Let me check. I did that a little bit fast. If I do x plus y over 3 and I subtract that, yes, that works out. Okay, right. So you can always solve this, right? And not only can you always solve it, you can actually solve it uniquely, right? That's the only possible solution that's going to work in this case, right? So the span of these two columns is all of R2, because whatever x and y happens to be, right, I can find a and b. So every single vector is in the span. For b, on the other hand, I notice that 3 minus 3 is 3 times 1 minus 1. So the column space for b, well, by definition, it's the span of both vectors, 1 minus 1, 3 minus 3. But the second vector is redundant, so we don't need to include it. Anything that can be written in terms of both vectors can be written in terms of the first vector alone, right? And so in this case, we simply get we get a line, right? We get a line. In this case, it would be the line. I guess y equals minus x, right, through the origin. If we wanted to describe that column space geometrically. Okay. The other thing that you can associate to a matrix is the null space. By the way, before we jump to the null space, let me point out that the column space is it's a subspace of Rm. Why is it a subspace of Rm? Well, it's a span of column vectors, m by 1 column vectors. It's a span of vectors in Rm. So we know that the span of any set of vectors is always a subspace. The null space turns out to also be a subspace. The null space is going to be a subspace of Rn. Okay? And the null space consists of all vectors that get sent to 0. Okay? Why is it a subspace? Well, notice that if x and y belong to the null space, and what does that mean? That means that a times x equals 0, a times y equals 0, then a times x plus y is ax plus ay is 0 plus 0, which is 0. And so that tells me that x plus y is in the null space. And similarly, we know that C times X is in the null space whenever X is in the null space. Okay. So the null space is closed under both addition and scalar multiplication. Of course, it's non-empty because the zero vector is in there. The zero vector is always in the null space because A times 0 is always 0. Right? So the null space passes the subspace test. So the other thing to note, and we kind of mentioned it already in our example, is that if I have some vector, say x sub 0, and it's in the null space, then for any other x in Rn, a times x plus t times x0 is ax plus t times ax sub 0, which is ax plus 0, which is a times x, right? And so that means that there are going to be infinitely many vectors that all get sent to the same y value. So if this is y, right, this is y over here as well, right? And so that's going to play a role if you're interested in solving systems of this form y equals a times x when there's something non-trivial in that null space. Of course, if x naught is the zero vector, then adding t times x naught doesn't do anything. But if x is if this x sub 0 is non-zero, then suddenly there are lots of different vectors that all get sent to the same value. Okay, so in our examples, let's look at the same two matrices we had before. If I looked at the null space for A, okay, so think about having A times any vector x, so xy equal to 0, 0. What does that tell me? Well, that tells me that x minus y equals 0 and 2x plus y equals 0. And so this one says that x equals y, and if we plug x equals y into here, then this says 3x equals 0. And well, if 3x equals 0, then x equals 0 and x equals y, so y is also equal to 0. So, so in this case, x equals 0 and y equals 0, and that tells me that the null space for A, the only thing that's in there, is the 0 vector. However, if we look at the matrix B, if we multiply by this guy, 3 minus 1, I'm going to get 3 minus 3. I'm going to get minus 3 plus 3. I get 0, 0. So this vector, 3 minus 1, belongs to the null space of B. And in fact, you can play around with this and you can see the null space of B, it's actually everything that's in the null space is a scalar multiple of this vector. Although, being 100% sure that that's the only vector in, that single vector generates the entire null space, we maybe need a few more techniques to understand why that's the case. Although one way to think about it is that if that null space was the span of two non-parallel vectors, well, we know that two non-parallel vectors in R2 should span everything, and clearly not every vector in R2 gets sent to 0. The only way everything in R2 would get sent to 0 is if B was the 0 matrix. Right? There are lots of values that we could plug in that don't get us to 0. So we expect that the null space is one-dimensional in this case. Okay, that's it for matrix transformations. All right, so this is going to be the first in a number of videos on solving systems of linear equations. The problem of solving systems of equations is the subject of both chapters 5 and 6 in the text. We're going to go over the basic mechanics from the point of view of simply systems of equations first. Then we're going to tie things back into vectors and problems involving linear combinations of vectors and matrix transformations and things like that that we've encountered from chapter 4. We're going to bring things back and look at things from the vector point of view, and we're going to do that once we get to chapter 6. But to begin with, we're just going to go through the basics, make sure we've got all of our terminology straight. So first of all, what do we mean by a linear equation? So a linear equation is something like the expression you have here. We have a number of variables. This could be a very large number of variables. The problems that we're going to do, of course, we usually are going to be dealing with 2, 3, maybe 4 variables if we want to get really crazy. But the sort of linear equations that you see in practice might involve hundreds or thousands or even hundreds of thousands of variables, which is why we're using subscripts to label our variables, right? Because we might run out of letters in the alphabet, but we'll never run out of numbers, so we'll use x1, x2, up to xn to kind of describe the general situation. Okay, so the fact that it's linear means that you've got your variables, right? Each one multiplied by some constant. So the a's are all constants. So it's simply, if you like, a linear combination of the variables, right? First variable times a constant plus the second variable times a constant, and so on down to the last one. And that might be equal to some other number b, right? So what you don't see in a linear equation is you don't see, there's not going to be anything like an x1 squared or, sine of x2. There's not going to be any complicated functions of our variables here. Simply linear functions of our variables. So x1, x2, and so on. Okay. So examples of linear equations might be something like 2x minus 3y plus z equals 4, which, by the way, we know what that is. That's a plane, right? That's a plane through the origin. 2u minus 3v equals 0. 7x plus root 2y minus pi times z plus 3/4 w is equal to 73. Something like that is linear, right? Now notice that okay, there were some complicated looking coefficients here, right? But the coefficients can be any real numbers, right? So root 2, that's fine. It doesn't have to be an integer. It doesn't have to be a fraction. It could be root 2. It could be pi. It could be any real number. The key thing here is that the variables x, y, z, w, they show up only multiplied by a constant. We're not doing anything else to them other than multiplying by a constant. Okay, now a system of equations is when you have a collection of 2 or more equations that you want to solve simultaneously, right? Now the system that I have here, right, this is not linear. The fact that you see the x squared, the y squared, tells you that this is not a linear system, but it is a system of equations, right? It's a system of equations that you could try to solve. Now, in general, solving non-linear systems of equations is very difficult. This is one that I can tell you how to solve. If I add these two together, notice that if I label these as 1 and 2, if I take equation 1 and I add equation 2, I get that 2x squared is equal to 6. So x is plus or minus the square root of 3. I could plug those values back in and solve for y. If I plug those back into the first one, I would find that 3 plus y squared is equal to 5, which tells me that y should be plus or minus the square root of 2. Here you actually notice you get 4 equations, right? Root 3, root 2, root 3 minus root 2 minus root 3 plus root 2 minus root 3 minus root 2. There's actually 4 different equations. You can think about this graphically, by the way. The first equation describes a circle. Okay. The second equation actually describes a hyperbola. The second equation looks something, the graph of it looks something like this. Okay, and you see that there are 1, 2, 3, 4 points of intersection, right? Now with linear equations, this sort of thing where you've got the graphs are curves that might intersect in complicated ways. This is not going to happen, right? Linear equations, they describe lines, they describe planes, and basically we'll see as we move forward, there really are only 3 possibilities. There might be no solution at all. Things might not intersect. There might be a single solution, like think about 2 lines intersecting in a point, right? Or there might be infinitely many solutions. Think of, 2 parallel planes that intersect in a line. Every point on the line is going to be a solution. And now I could write down, more complicated things, more complicated examples that are, harder and harder to solve. Even polynomial equations can be really difficult to solve exactly. So we stay away from things like this because they're really hard to solve. We will stick to linear equations because we'll see that there are systematic methods for solving linear systems. Okay, so an example of a linear system might be something like 2x minus y is equal to 4, and maybe minus x plus 2y is equal to 1. Okay, that's an example of a linear system, right? I can solve this either, I could solve this graphically, or I could solve it, algebraically. Of course, we're interested in the algebraic solution. We want exact answers. But if we wanted to kind of visualize things, okay, the first line, this is y equals 4 minus 2x. Okay, that's a line with intercept of 4, slope of minus 2. We got a line that goes like that, right? There's the line y equals 4 minus 2x. This guy here, this is y equals 1/2 plus 1/2 x. Okay, so the intercepts here are going to be 1/2. When x equals 0, y is equal to 1/2 somewhere down here. When y equals 0, x is equal to minus 1 over here, right? And so the other line is there. And we see that there is some point of intersection, right? And if we want to know what that point is, what are some ways that we can do it? Well, if we label these guys 1 and 2, we could do things like we could do equation 2. We multiply everything by 2 minus 2x plus 4y is equal to 2. Add equation 1, 2x minus y equals 4, right? Add those up. What are we going to get? We get 3y equals 6. So y is equal to 2. And then I can take that value y equals 2. We can put this into, well, whichever one we want. Let's try putting it into 1. If we put that into 1, we get 2x minus 2 equals 4. So 2x equals 6. So x equals 3. Right? So that tells me that this must be the point 3, 2. That must be the point of intersection. How do we verify that that is the right point, that we have a solution? Let's say we want to verify. Make sure I haven't made any mistakes. Well, if that's a solution, it has to work for both equations. So if I do 2 times 3 subtract 2, does that give me 4? It does. If I do minus 3 plus 2 times 2, does that give me 1? It does. Okay, so it works for both equations, right? And in this case, it's the only answer that's going to work, right? You can, no matter how we manipulate things to come up with a solution, that's the only solution that's going to work. We can see that graphically. It's the only possibility in this case. Okay. Here's some more examples of systems of linear equations. All right. One equation in one variable. Well, that's not very interesting, right? You can solve immediately. X is pi divided by the 4th root of 7. one equation in two variables, well, we can do that, one equation, two variables, but actually here, notice that here there's just one single solution, right? X is some value, and that's it. That's all we can say. If I have two variables in a single equation, well, now I get a line, right? I get, in this case, I get a line, right? When y equals 0, x is equal to 1, 2, 3. When x equals 0, y is equal to minus 2. So I get a line like that. And every single point on the line is a solution to that one equation in those two variables. So I have an infinite number of solutions. Right? Two equations, three variables. Well, that's just like the one we just looked at. We can think of this as two different lines, right? Here we can see, well, these are definitely different lines, and so we can expect. And also, are they parallel? Because that's one possibility, right? One possibility is you might be dealing with parallel lines, something like this. They never intersect, and then there's no solution at all, right? Or maybe the second equation is just a multiple of the first, so you only really, it looks like you have two equations in two variables, but really you only had one equation because the second equation was just a way of rewriting the first one. But here we can see that no, what we have is actually two different lines with different slopes, so they're not parallel, and so we know that they are going to intersect just like in the last problem, right? There's going to be one line, there's going to be another line, there's going to be a point of intersection. Okay, and then you go on from there. One equation in three variable. Well, we know that this is just the equation of a plane, right? In fact, we know what it's a plane with a normal vector. We know what the normal vector is going to be, 1, 2, minus 3, right? We just look at the coefficients of x, y, and z. And so every single point on that plane would be a solution to one equation in three variables. And so we have an infinite number of solutions in this case. But somehow it's an infinite number of solutions, but it's actually a sort of a two-dimensional set of solutions, right? Every point on the plane works, whereas here, in the case of a line, it's a one-dimensional set of solutions. And you can go on from there. Two equations in three variables, right? So now you have two planes, right? This is a pair of planes. And so, if I were to sketch things out, maybe one of my planes is here, and maybe the other one is maybe there, right? And maybe they meet. They're going to intersect along a line, right? So there's going to be some intersection. So every point along that line is going to be, so every point here is going to be a solution to that system, right? And so again, you get a whole line's worth of solutions. You get an infinite number of solutions. Okay, and you can go on from there. So you can consider any number of equations in any number of variables. And of course, what we're going to be interested in is how do you solve? How do you figure out what the solutions are? Even when there are infinitely many solutions, how do we describe them? What's kind of a general way of generating all the possible solutions to that system? So that's what we'll be looking at over the next few videos. Okay, so this is the next in our series of videos on systems of linear equations. So in this video we're going to go through sort of the basic terminology and notation that we will apply for linear systems. So a general system of linear equations can be a pretty complicated looking thing. All right, there can be any number of equations, any number of variables. So this might be, hundreds of thousands of equations relating millions of variables. This could be some very complicated problem that we're trying to solve here. And one of the things we'll see is that even for very, very, very large systems like that, there are computer algorithms that work reasonably quickly for solving these things. Now, for extremely large systems, the algorithms that we learn in this course, they're not good enough. It turns out that there are other algorithms which solve systems very, very fast, but only approximately, and you can sort of decide how much error you're willing to accept in your solution if you get there much, much faster. And by error, we're talking, the value of x1 might be off by 0.001 or something like this. So a general system looks like this, right? We have you've got a whole bunch of variables, x1 up to xn. Each equation, the x's are being multiplied by some numbers, right? So a11. Notice that there are two subscripts here. One subscript, the second subscript tells you which variable, right? 1, 1, 2, 2, and n, right? The first subscript tells you which equation we're talking about, right? First equation, second equation, third equation, down to the mth equation, right? And then we have some constants on the right-hand side. So these are called the coefficients. Notice that one thing you get, this is going to be important for us later on, you can form a matrix of coefficients, right? So you can form a matrix A whose entries, Aij, are simply the numbers that you see up in this system of equations. So one of the things that we'll do when we're developing our methods for solving systems is, rather than work with this system itself, we're going to work with matrices. We're going to work with this matrix of coefficients, and we'll see how to solve the system by working with the matrix rather than with the system itself. So a bit of terminology on this slide. A consistent system is one that has at least one solution. Okay, it might be one solution, it might be an infinite number of solutions, but there's at least one solution. An inconsistent system is one where there is no solution at all. Now, where do these systems come from? There are all sorts of practical applications to solving systems of equations. Ones that you might see in your other science courses here would be something like a problem involving electrical circuits in a physics class, balancing chemical reactions in a basic chemistry class. In economics, you might study input-output models. And there are other problems, Markov chains, which involves matrix multiplication, but there are still some systems you might have to solve there. There are a number of situations where you have to solve some system of equations, right? Any time that you're dealing with some number of variables and the relationships among those variables are linear, you're dealing with a linear system. There are lots of mathematical sources from within this course that we've seen that lead to systems of equations, right? Intersections of lines, we saw that when you're back in chapter 3, when you tried to determine whether or not two lines intersect, you ended up with 3 equations in 2 variables. Intersection of planes, that's 2 equations in 3 variables. Any question involving linear independence or span is really a question about systems of equations. We'll see that when we move on to chapter 6, right? Problems where you're trying to compute a basis, often you have to compute, you have to solve a system of equations, right? Solving matrix equations, these ones that might come up from, say, working with matrix transformations, you're solving a system. Also related to matrix transformations are the column space and null space. Computing these, again, leads to systems of equations. Lots of problems in linear algebra, which can be stated rather abstractly, eventually boil down to simply solving a system of equations. Okay, so what are some basic examples? We saw some of these previously. Okay, here's a system of 2 equations in 2 variables. How would you solve this? Well, we could solve it graphically. I could draw the lines if I want. Actually, why don't I'll let the computer draw the lines for me. Okay, so here's an example. Here are the 2 lines, right? So the first line, F there. So this is the graph of 3x minus 2y equals 4. The second line, G, that's the line given by minus 2x plus 5y equals minus 2. And I could ask for the intersection between these two, and it's this point here, right? This software, by the way, is called Algebra, and it will do things like intersections for you, right? I can say, you know what, I want the point of intersection between this line and that line, and it'll do that for me. Of course, I already did it once, so I don't need to do it again. Okay. So we get that point. The maybe one downside here is that GeoGebra doesn't give me exact answers. It gives me decimal answers. 1.4545, 0.1818. Those sound like repeating decimals to me. Let's see. Let's add a few more decimal places. Oh, those definitely look like repeating decimals. So repeating decimals, those came from some sort of fractions, so we got some rational answers. What are the exact answers? If we wanted to give these things in fractions, what do they look like? Well, again, we haven't developed systematic methods yet, but let's label these 1 and 2. I could do equation 1 times 2. That would give me 6x minus 4y equals 8. Let's do equation 2 times 3. That's going to give me minus 6x plus 15y equals minus 6. Let's add those up. Right? Now 6x minus 6x, you can see why I want to add them. Those cancel out. I get 11y equals 2. That's telling me that y should equal to 2 over 11. Okay, so 2 over 11, that must be that 0.1818181818. That must be 2 over 11. What about x? Well, let's take that value, y equals 2 over 11. Let's plug that into, I don't know, let's plug it into the first equation. So 3x minus 2 times 2 over 11 equals 4. So 3x is equal to 4 plus 4 over 11. That's 44 plus 4 over 11, so that's 48 over 11. Dividing both sides by 3, 48 over 3 is 16, so x should be 16 over 11. Okay, so 16 over 11, that must be that 1.45454545 that the software gave us. If we want to verify this, make sure this really is a solution, okay? I've got it on my slides, I must have done it right, but how do we actually double check, make sure that we've done things correctly? Well, if you just want to verify that some numbers actually solve your system, you don't have to go ahead and if I give you the numbers, right? You don't have to go and solve the system and reduce it down and find out that that's your answer. No, you got the numbers, plug them in. 3 times 16 over 11 minus 2 times 2 over 11 is 48 over 11 minus 4 over 11. That's 44 over 11. That's 4. That's what I'm supposed to get. Okay. Minus 2 times 16 over 11 plus 5 times 2 over 11 is minus 32 over 11 plus 10 over 11. That's minus 22 over 11. That's minus 2. Works in the second equation as well, right? So when we say that these values are a solution to the system, we mean they don't just work in one of the equations, they work in all of the equations. In this case, there are 2 that we have to check, so we plug it into both. Okay. Here's another example, 2 equations, 2 variables, no solution. Again, we can see this graphically. Why don't we get a solution in this case? Let's open up this guy. What do we have? Okay, nothing yet. I haven't plotted the lines. Let's plot the first line. Okay, x minus 2y equals 4. There it is. The other one, the software simplified it for me. What was my other one? Minus 2x plus 4y equals 0. If I plot that line, there it is. Those 2 look suspiciously like parallel lines, right? Those are lines that are never going to meet. So it makes sense that there's no solution to this system, right? We've got 2 parallel lines, they never intersect, so we can't solve the system. How do we actually see that algebraically, that there's no solution? Well, let's do equation 1 times 2. We get 2x minus 4y equals 2 times 4, so that's going to be 8. Okay. Minus 2x plus 4y equals 0. Right? We can add these together, right? If the left-hand side equals right-hand side for both of them, then adding the left-hand sides should be the same thing as adding the right-hand sides. And what do we get? 2x minus 2x, we get 0. 0 equals 8. Well, that's a problem, right? 0 is not equal to 8. So there's no way to solve this system, right? Simplifying the left-hand sides, everything collapses down to 0. The right-hand side doesn't collapse down to 0. So there's no way to solve this, right? 0 can't equal 8. So there's no possible choice of values that is going to work for this system, right? No matter what you plug in for x and y, there's no values of x and y that are going to make 0 equal 8. 0 is just never equal to 8. Okay. Here's one more example, two equations in three variables. Let's say I want to solve all solutions to this system. Okay, this takes a little bit more work. What we might do here, there's a few ways to do it. One way we might do it is we might do this. We might say, okay, here's equation 1, equation 2. Let's do equation 1. Let's do kind of something like this again. Equation 1 times 3, and we'll do equation 2 times 2. Actually, let's do not just 2, but times minus 2. So 6x minus 12y minus 3z equals minus 18 minus 6x minus 2y minus 4z equals minus 8. I add these up, I'm going to get, what am I going to get? Minus 14y, right? The x's cancel, minus 7z is equal to minus 26. And then I might try to say, okay, you know what, why don't I solve for, let's divide through by 7, maybe divide through by minus 7. So 2y plus z is equal to 26 over 7, right? So z is equal to 26 over 7 minus 2y. So I can write z in terms of y. I could then say, well, if I can write z in terms of y, and then I could probably solve for x in terms of y. I could take this, I could plug it into here. But the best I can do is I could eliminate y, right? Or I could eliminate z, right? So I could plug that in there. I would get 2x minus 4y minus 26 over 7 plus 2y is equal to minus 6. And so I could solve here for x, right? I could get x would be equal to, so I've got minus 2y, bring it over, divide by 2y, and then I've got minus 3 plus 13 over 7, right? That's some number. Okay, and so now I've written x in terms of y, I've written z in terms of y, but I can't, there's no way to kind of solve exactly for x, y, and z here, because y can take on any values I want. In fact, choosing any value of y would give me a solution, right? If I put y equal to 0, that would give me a solution. Putting y equal to 2 would give me a solution. I get an infinite number of solutions. What do those solutions look like? Oops. Why don't we plot them? So let's open up this guy here. Okay. All right. So each equation defines a plane, right? Here's the first equation, right? I plot that. You can see that I've got a plane sitting there. Okay. I do the second equation. I get a second plane. You can see now there's those two planes, right? And what are the solutions? The solutions are all the points that are common to both planes. And you can kind of see that there are some points common to both planes. What are they? Well, again, I can ask the software to intersect my planes. And I get everything along that green line. We can see that green line lies in both of the planes. It lies in the red plane, lies in the blue plane. If I hide the planes, I'm left with a line. Okay, a line sitting there in space. And every point along that line is a solution to my system. So I get an infinite number of solutions in this case. All right, that's it for this video. Okay, so in this next video on systems of linear equations, we're going to start looking at some systematic methods for solving a system of equations. Now, in the previous videos, we saw that there are certain things you can do to manipulate the equations to try and tease out a solution, right? Now, there are a few things we can do that we can all agree are not going to change the outcome as far as solving a system, right? So the first one says, well, obviously it does not matter. The order in which we write down the equations is not going to matter, right? So you can swap the positions of any equations in your list of equations. It's also true that if you multiply both sides of an equation by a constant, as long as whatever you do to one side, you do to the other side, right? Multiplying everything through by a constant. That doesn't change the equation either. And we saw that, one of the things you can do to try to eliminate one of the variables is you can add one equation to another, or maybe you need to first multiply one of the equations by a constant before you add it, right? So you can combine equations in that way, right? So if you have two equations and you add the left-hand sides from one equation, you add the right-hand sides, if the two equations were both balanced to begin with, then, adding two equal things is, going to give you the same result, right? So you can combine these two equations. It turns out that these are the only three things you need to do to solve any system of equations, okay? So here's an example, right? We could label these, let's label these 1, 2, 3, okay? So I could do a couple of things, right? I could do, I'm going to keep 1. I'm going to kind of transform this to a new system. So I can do the same. So the first equation is going to stay the same. X plus 3y minus 2z equals 4. Then I'm going to take the second equation, but I'm going to subtract off the first equation. So x minus x gives me 0. Minus y subtract 3y gives me minus 4y. There was no z here, but then I'm subtracting minus 2z, so that's adding 2z. So minus 4y plus 2z is equal to minus 2 subtract 4. I get minus 6. I'm going to take the third equation, and I'm going to subtract off 3 times the first equation. Okay. Right. Again, my goal is I'm trying to get rid of the x. So 3x minus 3x gives me that 0 I'm looking for. Right. So if I multiply by 3, just so we kind of keep track, 3x plus 9y minus 6z equals 12. So I'm subtracting those from the third equation. So 3x minus 3x, 0 minus 4y minus 9y minus 13y. Z minus 6z, that gives me plus 7. Right? 1 plus 6 gives me 7. And finally, I have a 0 here, and then I'm subtracting 12. So 0 minus 12 gives me minus 12. Right? So now what I can do is I can say, okay, you know what? Let's ignore the first equation for a minute, and let's focus on these guys. Okay, let's call these. So these are going to be some new equations. So let's label these guys maybe 4 and 5. Right. So maybe the first thing I'll do here is I'm going to do minus 1 over 4 times equation 4, and that's going to give me y minus 1/2 z is equal to 3 over 2 if I multiply everything by minus 1 over 4, right? And let's label that guy, so I guess that's going to be 6. And now I can take equation 5, and I'm going to add 13 times equation 6, right? Because 13 times equation 6, I'm going to get 13y minus 13 over 2z is equal to 39 over 2. Okay, and now if I combine that with 5, what do I get? Well, the z's go away, 13, or the y's go away, 13y minus 13y, they're gone. I've got to do this, right? 7z plus minus 13 over 2z. 7 is 14 over 2, so this gives me 1/2 z. So I simply get 1/2 z equals, what do I get when I add on the other side? I've got minus 12, and I'm adding to that, I'm adding 39 over 2.
So minus 12, that's minus 24 over 2. So that's going to give me 15 over 2. So I get 1/2 z is 15 over 2. And now I'm in business because that's one equation, one variable. I can solve that, right? So I get, what do I get? I get z equals 15. Let's plug that into 6. Okay. Y minus 1/2 of 15, so 15 over 2 is equal to 3 over 2. So this tells me that y is equal to 3 over 2 plus 15 over 2. That's 9. Okay. So now I plug that all the way back into the first equation. Not just the value for y, but also the value for z. X plus 3 times 9 minus 2 times 15 equals 4. That tells me, okay, so that's x plus 27 minus 30, so x minus 3 equals 4, x equals 7. Okay, so I've come up with values. X equals 7, y equals 9, z equals 15, and I could, if I wanted to make sure that I didn't mess anything up, one thing I could do is I could take those values, I could plug them into any one of the 3 equations I started with, and I'm going to leave this as an exercise for you. Exercise. Verify. Verify that this works, right? So take those 3 values, x is 7, y is 9, z is 15. Try them in any one of the 3 equations we started with and make sure that it works for all 3, okay? That's how you know that you've solved the system, right? Once you plug them back in, then you know for sure you did your job. Okay. Now it's a bit of a mess, right? One of the things that's really messy here is carrying along those variables, right? We notice as we go that what the thing that doesn't really matter, like the names x, y, z, don't really matter. They're almost kind of placeholders, right? The things that we really care about here are these numbers, the coefficients. Those are the things that we're working with. So what we do to kind of make our lives easier is we just drop the variables. We write everything down. We just keep the numbers, but we got to keep track of where those variables were, right? We got to remember where those numbers came from. So what we do is we write things down in what's called an augmented matrix, right? So we organize things into rows and columns, right? So we see that the first row corresponds to the first equation. The second row is the second equation. The third row is the third equation. The first column are the coefficients for x. The second columns are the coefficients for y. The third column, coefficients for z. And these guys, well, those are the constants on the right-hand side, okay? It's going to be much easier to work with this matrix than it is to work with the original system. And we're going to see that we're going to be able to write down an algorithm that allows us to always take an augmented matrix like this and reduce it down to a simple form where it's very easy to read off the solution to the system. So there are 3 skills that you need to learn as you work through systems of equations. The first is simply going back and forth between a system and an augmented matrix, right? If I give you a system, you want to make sure you can immediately jump to this augmented matrix. If I give you the augmented matrix, make sure you know how to write down the corresponding system. Okay, that's pretty straightforward. The next skill set is taking this augmented matrix, reducing it down to a simplified form. We have to say what that simplified form is. We'll give you an algorithm for that. You'll learn how to do it. The last thing is once you get down to that simplified version, how do you read off the answer? You want to make sure that you can read off the answer quickly. So we'll get to all of that in due course. Okay, so those elementary operations, those things that we could do to our equations, those correspond to things we can do to the augmented matrix, right? If I had chosen a different order in which to write down my equations, think about here, if I had maybe put the second equation before the first one, I would still have the same system, right? I'm just writing down the equations in a different order. But that would correspond, if I swapped these guys here, I would end up swapping the corresponding rows in the augmented matrix.
So one of the things that we want to allow ourselves to do is swap two rows, right? So we can interchange the positions of any rows in the matrix. Be careful when you do it, right? You don't just swap these guys. You got to remember the guy on the other side of this bar here, right? When you swap equations, you got to move the constants on the other side of the equal sign as well. You don't just move the variables, right? So when you swap rows, you swap the whole row. And we know that we can also multiply an equation, both sides of an equation, by a constant. And, in the augmented matrix, that corresponds to just multiplying all the way across a row by some constant, right? So we could, for example, take maybe the second row here, multiply everything by 3. We would get 3 minus 3, 0, minus 6. We multiply by 3 all the way across. And the main thing we do, the main way that we kind of simplify is we combine equations to cancel variables, and we do that by multiplying an equation by a constant and then adding that to one of the other equations, and that corresponds to multiplying one of the rows by a constant and then adding that to one of the other rows. So these three row operations, and these often are if we want to refer to them by type, this is often called a type 1. This is often called a type 2. This is often called a type 3 row operation. With these three types of row operations, we can reduce any augmented matrix to a simplified form where we can read off the answer to our system. Okay, so here are some basic examples. Okay, I'm gonna kind of jump ahead quickly so we don't make the video too long, but you can always pause here at this slide and peruse these examples. Okay, in the first one, we see what happens when we swap the two rows, right? So the original row 1 becomes the new row 2. The original row 2 becomes the new row 1. We're just interchanging the two rows, right? I could multiply across one of the rows by a constant, and in this case, I've multiplied by 1 over 3. Right, so dividing by 3 is like multiplying by 1 over 3. So I multiply everything by 1 over 3. That's something else I can do. And I could multiply one of the rows by a constant and add it to another row. So here what I've done, this row operation, I've multiplied row 1 by minus 1, and I've added that to row 2, and that gets me to here. So I'll leave you to pause and check that that's exactly what happens in that row operation. Okay. Now, and by the way, just for consistency, I guess, with the textbook, the notation you'll see in the textbook, they write things the other way. They'll write this as 1/3 row 3 becomes the new row 3, and they'll say that row 2 minus row 1 becomes the new row 2. They just kind of write things, the other way around with respect to this arrow. So I'll try to stick to the same notation as the book. All right, so we kind of, when we were solving this system, we kind of played around. I didn't solve it exactly the way we see it here, but we can reduce things down, get to sort of a simpler system, right? And so we got down to that z equals 15. We plugged it back in to solve for y. Then we took the y value to solve for x, and oops, that should be a y there. Right, so we can reduce all the way down to, this would be the simplest possible system, x equals 7, y equals 9, z equals 15, right? We can't reduce beyond that. We've got the answer staring us in the face. So how do we do that if we were working with the augmented matrix instead? So if we've got our augmented matrix, then what I would do here is I'm going to start out by, so the first thing I'm going to do is, well, it's nice to have these 1s, right? Because with a 1, you can easily use a 1 to get rid of the things sitting below it. We'll see that this is kind of the first step that we do. So we could take row 2 minus row 1 and make that the new row 2. While I'm at it, let's also take row 3 and subtract off 3 times row 1 and make that the new row 3. So I'm doing 2 steps at once, but each one involves a different row, so I don't have to worry about these conflicting with each other. So I haven't changed the first row. It stays as it is. So now I'm doing row 2 minus row 1. So I do 1 subtract 1 gives me 0. Minus 1 subtract 3 gives me minus 4. 0 subtract minus 2 gives me plus 2. And minus 2 subtract 4 gives me minus 6. Now, row 3 minus 3 times row 1. So 3 subtract 3 times 1. So 3 minus 3, 0. Minus 4, let me write that one out. Minus 4 subtract 3 times 3. That's minus 4 minus 9. That's minus 13. That minus 13 goes there. Okay. Next up, 1 subtract 3 times minus 2. That's 1 minus 6. So that's 1 plus 6 gives me 7. And then I get a minus 12. So I get down to there. Okay. So where do you go from here? Well, one of the options would be to kind of proceed as we did before. So if we want to follow the example we did before, there's kind of, there's no one right way to do this. So one way you could do this is you could do minus 1 over 4 row 2 and make that the new row 2. Okay. That's what we did when we solved it before. Some people might not like doing that because fractions are going to come into the picture. The other way you could do this, if you don't like the fractions, is I'm going to do this. I'm going to do row 3 minus 3 row 2 and make that my new row 3. Why do I want to do it that way? Well, let's see what we get. Okay, 1, 3, minus 2, 4, 0, minus 4, 2, minus 6. Okay, 0. So minus 13 minus minus 12 gives me a minus 1. Okay. 7 subtract, so 3 times 2, 7 minus 6 gives me a 1. And then minus 12, I'm going to get a 6 there. Okay. So I get down to there. You could do it the other way if you want, but here's another way to do it. So then one thing I could do, and let me just kind of, I'm going to sort of sneak in a row operation here. I'm going to do row 3 goes to, I'm going to change the sign on row 3. So that's going to become a plus, minus, minus. Okay. Then I'm going to do, the next thing I'm going to do is I'm going to exchange row 2 and row 3. 1, 3, minus 2, 4, 0, 1, minus 1, minus 6, 0, minus 4, 2, minus 6. And where do we go from here? Well, now I'm going to use this 1 to get rid of the 4. Okay. So I'm going to go row 3. I'm going to go row 3 plus 4 row 2 is my new row 3. 1, 3, minus 2, 4, 0, 1, minus 1, minus 6, 0. So minus 4 plus 4 gives me 0. 2 minus 4 gives me minus 2. And minus 6 plus 24 gives me, or sorry, that's not right. Minus 6 minus 24 gives me minus 30. Okay, so you get it down to there. And the last thing you might do is you might divide through. The last thing I might do, let's kind of sneak this in. I might do minus 1 over 2 row 3 becomes the new row 3. And then this minus 2 becomes a 1. That minus 30 becomes a 15. Okay. Now, how does this help you? Well, that last row, what does that last row say? If we kind of convert back to a system, that row says 0 times, remember this is the x column, this is the y column, this is z column. These are my constants. It says 0x plus 0y plus 1z equals 15. Right? So that bottom row says z equals 15. What does the next row say? The next row says y minus z equals minus 6. Or sorry, minus 6. Right? So y is equal to minus 6 plus z, which is minus 6 plus 15, which is 9. And And then I can go to the first row and I can say, okay, the same as before now, right? The first row says x plus 3y minus 2z equals 4. So I plug my y and my z values in and I can solve for x and I'll get x equals 7, the same as before. Now, I chose to go this route simply to avoid fractions. The fractions weren't even bad, right? I was going to deal with kind of halves. You probably should have gone this route because I think you would end up doing about 2 fewer steps at the expense of having some fractions around. If you really want to avoid the fractions, you can sometimes avoid them by adding extra steps. Sometimes you can't avoid them at all. But this is the idea. So the idea is that we can save ourselves a little bit of writing by working with the augmented matrix instead of the system itself. So we'll explore this a little bit further in some later videos, but this will be enough for this week. Okay, so welcome to the next in our series of videos on solving systems of linear equations for Math 1410 Linear Algebra. So this next video is going to introduce the main algorithm that we use for solving a system of equations. It's called Gaussian elimination, named after Carl Friedrich Gauss, who was a famous 19th century mathematician. The idea with Gaussian elimination is, well, what you're eliminating is you want to eliminate some of the variables, right? So basically you want to, by combining the equations in clever ways, you want to get rid of some of your variables, allowing you to solve for the ones that remain, right? So beginning with this system, we've got three equations with 4 variables here. What we might want to do is kind of reduce things down to maybe reduce it down to, say, 2 equations and only 3 variables, and from there maybe down to a single equation relating 2 of the original 4 variables to allow us to sort of set up and solve. So the way we do this is as usual, we want to set up our augmented matrix because it's easier to work with an augmented matrix than it is to keep all the variables in place. So we set up our augmented matrix like so. 2, 1, 0 for the x's, 0, 3, 2 for the y's, 6, 0, minus 1 for the z's, for the w's, 2, minus 2, 1, and over on the other side go our constants, 4, minus 1, 1. All right. So at this point, I want to create a leading one. Now I've got 2 options sitting here for creating a leading one, and I can use whichever one I want. What you want is you would like to create a 1 in the upper left-hand corner. We'll see why this is useful as we move forward through the example. There's 2 ways to do it. I could either swap row 1 and row 2 because I noticed that I have this 1 sitting here. I could swap rows to move that up. Or I could take the entire first row and I could divide everything by 2. I noticed that, hey, everything in row 2 is even. Why don't I divide by 2? Either one is valid. Why don't we divide by 2? Why not? So what we might do here is we might say, let's do 1/2 row 1 and make that our new row 1. Okay? So I get 1, 0, 3, 1, 2, and then 1, 3, 0, minus 2, minus 1, 0, 2, minus 1, 1, 1. Okay, so now I've got that 1 sitting there. So this guy is called a leading 1. And you want to use your leading 1 to create zeros. And where do you create zeros? Well, you create zeros in the column containing that leading 1. So you get rid of any non-zero entries that are below that leading 1. And well, there's only one non-zero entry below the leading 1. It's the 1 directly below it. How do I get rid of that 1? Well, if I subtract row 1 from row 2, I'm going to get rid of that 1. So I want to do row 2 minus row 1 and make that my new row 2. Okay, so that gets me 1, 0, 3, 1, 2. 0. 3 minus 0 is 3. 0 minus 3 gives me minus 3. Minus 2 minus 1 gives me minus 3. Minus 1 subtract 2 gives me minus 3. 0, 2, minus 1, 1, 1. Okay, and well, you can probably guess what I want to do next. You can tell this this problem was a bit of a setup. I made sure that all those 3's showed up. Most of the time, if life hands you a system of equations, it's not always going to work out so nicely, but you know, we'll stick with artificial examples because they take less time. So the next thing I'm going to do, I'm going to divide this second row by 3. I'm going to multiply 3 by 1 over 3. Get rid of all those 3's that are sitting there, right? That's going to give me my second leading one. So 1, 0, 3, 1. I haven't changed the first row. Now I divide everything by 3. So 1, minus 1, minus 1, minus 1, 0, 2, minus 1, 1, 1. Okay. Now I have 2 leading ones, okay? So I keep these guys there. The idea, what we do in this algorithm is we basically try to build up sort of a staircase of leading ones. We work our way down and to the right, starting from the upper right-hand corner. So the next thing I can do is I can say, well, look, I've got this leading 1. I'm going to use it to make 0. So I look what's sitting below the leading 1. There's a 2 sitting there. I want to get rid of the 2. How do I get rid of the 2? I take row 3 and I subtract off 2 times row 2. 2 minus 2 will give me a 0. That's going to become my new row 3. So I'm leaving row 1 alone. Let's recopy that. I'm leaving row 2 alone, so we recopy that. Okay, and now 2 minus 2 gives me my 0. Minus 1, so everything else multiplied by minus 2 is going to give me a plus 2. So minus 1 plus 2 gives me a 1. 1 plus 2 gives me a 3. 1 plus 2 gives me a 3. Okay, and oh, look, leading ones all the way down. Okay, that's the best we can do. I mean, as far as trying to create these leading ones, that's as far as we can go. There's nothing else I can do from this point to create further leading ones because I've run out of rows, right? So the idea with this leading one, we'll define these in a bit, but basically the leading one should be the first non-zero entry in your row. Well, I've got leading ones in all 3 rows, so that's pretty much the best I can do. So where do I go from here? Well, what I can do from here is I can say, well, what are these equations that are left here, right? So one of the reasons why these leading ones are nice is the equations that remain are, so the first one is x, okay, plus 3z plus w equals 2. That 1 in front of the x means it's very easy for me to solve for x. X is going to be 2 minus 2z minus w. Okay. In the next row, I've got y minus z minus w equals minus 1. Again, the fact that the coefficient of y is equal to 1 means I can quickly solve for y. Y is equal to minus 1 plus z plus w. And the last one says z plus 3w is equal to 3. Okay, and so I get, I get w, z is equal to 3 minus 3w. Now, one of the things I can do here, if I wanted to kind of continue with this, we're gonna leave it at this for now. But if I wanted to kind of continue, what I could do is I could take this value for z, right, and stick it in here. Right? Then y would be written in terms of w only. Then I could take this value for z and I could stick it in here, and then z would be written in terms of, or x would be written in terms of w only. In fact, let's do that. Okay. So x is going to be equal to 2 minus 2 times 3 minus 3w minus w. So x is equal to, that's 2 minus 6 minus 4, and then 6 minus 1, minus 4 plus 5w. Y is going to be minus 1 plus z, so 3 minus 3w, plus w. So y is equal to 2 minus 2w. Okay. All right. So that gives me, let's kind of rewrite the x and the y. Okay. So I get, here's x, here's y, okay, and down here is z. Okay. Notice that all x, y, z, they've all been written in terms of w, right? I don't have any equation that says w equals something. The w in this case, w is what's called a free variable. It's a free parameter. Okay, w can be whatever it wants, but once we choose a value for w, then I have to accept values for x, y, z, right? If I choose, say, w is equal to 1, then x will be minus 4 plus 5. X would have to be 1, y would have to be 0, z would have to be 0, right? So that's one possible solution would be x is 1, y is 0, z is 0, w is 1, and you could check that works in all three equations. But in fact, any other value for w would do. Okay, so we'll see that this comes up quite a bit, and because w is free, w could be any real number. We can see that you get an infinite number of solutions to this system. Okay, so this is basically the idea. So how do we kind of solve, right? So somebody hands us a system of equations, right? We want to simplify and, if possible, solve using these elementary row operations, right? So same as we did in this previous slide, right? The way I solve this system is I write down my augmented matrix and I use my row operations to try and get my augmented matrix down to a simpler form. And a simple form is going to be one that has a lot, as many ones and zeros in there as we can manage. Okay? And so basically what we want to do is we want to use our row operations to get this thing down to a simplified form, and from that simplified form, read off what the solution to our system is. The only thing is we have to agree, first of all, on what is the most desirable, simpler form, right? If we're going to program a computer to use this algorithm to solve a system, we have to tell the computer when the algorithm terminates. When do we stop? When do we know that we're done, right? So that's one thing we got to know, is when do we finish? The other thing is, okay, how do we program this algorithm as efficiently as possible? If we're dealing with thousands of equations and thousands of variables, we don't want to mess around, right? We want to, minimize the amount of computational power that's going to be needed to solve this system. Okay, so we'll answer the question about when to stop first. So the question of when to stop is this row echelon form. So the row echelon form, this is this sort of, this simpler form that we're looking for. Okay, so how do we know when our matrix is in row echelon form? Well, it might happen, it didn't happen in the previous example, but it could happen that one of the rows in your matrix cancels out completely and you're left with just a row of zeros. If you end up with a row of zeros, you throw it down to the very bottom of your matrix, right, where you can ignore it. We don't care about rows of zeros, they tell us nothing. The next condition is that for a non-zero row, so if a row has at least one non-zero entry, we want the first non-zero entry to be a 1. And by first, we always read things left to right. So first we mean, the first entry reading from the left, right, when we say first. So reading across the row from left to right, we want the first non-zero entry to be a 1. This is our so-called leading 1. And as we kind of work our way down, right, any sort of new leading 1 needs to be to the right of any leading ones that we already established. So let's jump back to what we had here, right? We can see that here, that the first leading 1 is furthest to the left, and then as I go down, each successive leading 1 shifts over to the right. Now, it could happen, it doesn't in this example, but it could happen that as I go down from one row to the next, I shift over several columns to get to the next leading 1. There might have been a 0 and a 0 and a 0 and a 1, something like that. But I need to move at least one column over to get to the next leading 1. The next leading 1 is always over to the right. Okay. So these are the conditions to be in row echelon form. Now, row echelon form is simpler, but it's not the simplest. Okay, the reduced row echelon form, right here, the reduced row echelon form, this is the simplest. Okay, the simplest that you can get. You can't go any further than reduced row echelon form, right? So this is our termination point. If we get down to reduced row echelon form, then we're done. Okay. Now, if we jump back to the example we've already done, okay, we gave a matrix which is in row echelon form. Let me show you that. Okay. So why is it in row echelon form? It's in row echelon form because, well, there are no non-zero rows. We don't have to worry about that. Each row, the first non-zero entry in each row is a 1, and the leading ones follow this staircase pattern, right, of going, as I go down, I go to the right. Okay. So that means I'm in row echelon form. What do I need to be in reduced row echelon form? I need this condition here. Every leading one has to be the only non-zero entry in its column. So, what's missing? Why is this not in reduced row echelon form? Well, we look at this column here, right? The first leading one, it's by itself in its column. Every other entry in the first column is 0. In the second column, we've got a leading 1 and everything else is 0. But in the third column, I've got a 3, I've got a -1, right? Those guys are non-zero, and because those guys are non-zero, that's why I had to do this, this extra work up here, right? That forced me to do this extra work, right, where x depended on z and w, y depended on z and w, and I want them to depend on w only, and I had to do this extra step of substituting things in and simplifying. So if I decided to go and do a couple more steps, and why don't we do that? Let's actually let's do these additional steps. So let me erase all this. Okay. I'm gonna do 2 more steps. What am I gonna do? I'm gonna do this. I'm gonna say, well, to be in reduced row echelon form, I gotta get rid of the 3. I gotta get rid of the -1. So I'm gonna do row 1 -3 row 3 into row 1, right? Because that's going to get rid of the 3 for me. If I do row 2 plus row 3 into row 2, that's going to get rid of that -1. I'm going to get, so, 0, 0. So the bottom row is unaffected. Okay. Now, here's the thing. Because I've already, because the leading ones follow this staircase pattern, I don't have to worry about what's going on in columns 1 and 2. Those are going to stay the same because in columns 1 and 2, I'm using row 3, right? I'm using row 3 to create my zeros. But row 3 has zeros in those first 2 columns. So I don't mess up the work I've already done, right? I don't want to put things back where I already have zeros. I want to keep those zeros. But now I know that I get zeros here and here. Okay? So if I do -3 times row 3, it gives me a -9. Added to that 1 gives me -8. Okay. And I do, there we go. And then -1 plus 3 gives me a 2. Okay, good. So I get down to there. And I got to deal with the other side as well. 2 times, so I'm doing -3, right? So 2 minus 9 gives me -7. And -1 plus 3 gives me 2. Okay. And then if I kind of want to read off my equations, and I'm suspecting that I made a mistake somewhere because I'm not getting back to where I had before. This one here still says that z plus 3w equals 3, so I can immediately solve for z, 3 minus 3w, the same as before. The second row says y plus 2w equals 2, so I can solve for y, it's 2 minus 2w. The top row, here's where I must have messed up. X minus 8w equals minus 7. So x should be minus 7 plus 8w. It's not what I got before. So where did I go wrong? Oh, I can see where I went wrong. This should have been a 3. That 2 should have been a 3. And so then, yeah, so then 2 minus 9 should have given me, let's fix it, should have given me minus 7. And then minus 3 times minus 3, that's plus 9 minus 1. I get my 8, which agrees with what I had down there. Okay, so reduce row echelon form saves you the trouble of having to do this additional back substitution step that we had to do when we first did this example. Okay. All right, so additional terminology, I mean, you'll see this used, don't worry too much about it, but you'll see it used at one time or another. These columns containing leading ones, these are sometimes called your pivot columns. The corresponding variables are sometimes called pivot variables, sometimes called basic variables, sometimes called dependent variables. Variables that correspond to columns without a leading one, that would be the W variable in the example we just looked at. These are called free variables. Sometimes we call these guys parameters, free parameters. Okay, their value, we can choose any value we want for these guys. Sometimes we call them independent variables. You'll see a number of different terms in use for these guys. Okay. Now, here's some examples just to make sure that we have this idea of row echelon form, reduced row echelon form in place. Let's see if we can identify whether these guys are in row echelon form, reduced row echelon form, or neither. So the first one, is it in row echelon form? Well, let's see. Any rows of all zeros? No. 2 non-zero rows, do they both start with a 1? Sure. Here. The leading one in the second row is to the right of the leading one in the first row. That's one of the requirements, right? The leading ones descend down and to the right. So this guy is in row echelon form. However, there's a 2 sitting above the second leading one, so that second leading one is not the only non-zero entry in its column, so it is not reduced row echelon form. Okay. What about the second one? Well, let's see. There's a row of zeros. It's at the bottom. Does every non-zero row begin with the leading 1? Yep, here. Okay. Notice the first column is all zeros. That could happen. You might think, how could that possibly happen? We'll run into situations later on where this does happen, right? There's nothing in the definition of reduced row echelon form or row echelon form that says you can't have a column of zeros, and certainly nothing saying that the first column can't be 0. So don't worry, it might happen. If it happens, well, what does that tell you? As far as solving the system, that just tells you that that first variable is completely free. Basically, you know, the only way this really happens is if the first variable just does not show up in your equations. Okay. So this guy is once again in row echelon form. Whether or not it's in reduced row echelon form depends on this guy. If that guy is 0, then we're in reduced row echelon form. But I don't know what value it is, so we can't conclude. All right. Next example. There's no rows of zeros. We detect leading ones here and here. That's all well and good. But then we see this guy here, this 2. Okay, so this 2, this is not even in row echelon form. Okay, it's not in row echelon form because the first non-zero entry in that third row is a 2. It's not a 1. If I wanted to get this thing into row echelon form, I'd need 2 row operations. Okay, first thing I'd have to do is I should take row 3. I have to multiply by a half. All right, that would give me a leading 1 in the third row. Okay, but that leading 1 would be to the left of the leading 1 immediately above it. We don't want that. leading ones that are lower down need to always show up to the right of the ones that are above it. So I would also have to take row 2 and row 3 and swap them to get this sort of staircase pattern. Okay, so I would need those 2 steps to get that guy into row echelon form. Okay, the next one is kind of an interesting one. It's a matrix of entirely zeros. Is it row echelon form? Is it reduced row echelon form? Well, let's check the conditions. Are any rows of zeros at the bottom? Yeah, I mean every row is all zeros. I guess they're all at the bottom, right? There's certainly not, I guess this is a bit ambiguous here, but there are no rows of zeros sitting above non-zero rows because there are no non-zero rows. Is the first entry in any non-zero row a 1? Technically, yes, because there are no non-zero rows. Well, the third condition is also vacuous, right? And the same with the condition for reduced row echelon form. This is in reduced row echelon form, right? Because it trivially satisfies all of the conditions. What about this next guy? This next guy is also in reduced row echelon form. A lot of people will be thrown off by these guys here, okay? Don't worry about the fact that there is not a leading one in that column, right? It's row echelon form, reduced row echelon form. We pay attention to the rows, right? There are no rows of zeros. Okay, the first entry in each non-zero row is a 1, a 1, a 1, and those ones go down and to the right. So they follow what they should follow, and it's reduced row echelon form because each leading one is the only non-zero entry in its column. Okay. Similarly, this last guy is also reduced row echelon form. Okay. You got your row of zeros is at the bottom. The first entry in the 2 non-zero rows is a 1. The first non-zero entry is a 1. And those ones are the only non-zero entries in their respective columns. So it's in reduced row echelon form. Okay, so far so good. Where do we go from here? Well, once you've got your matrix in reduced row echelon form, you need to be able to tell me what the solution to the system is. So you want to be able to do this quickly. You want to be able to just glance at that matrix and tell me what is the answer. Okay? So look at this first one, right? What does this first row, so let's label these columns, X, Y, Z for all 3 of them, okay? The X column, the Y column, the Z column. What does that first row represent? That first row says 1 times X plus 0 times Y plus 0 times Z equals 1. Remember these guys over here, those are the constants on the other side. Okay, well, that's a very complicated way of just saying X equals 1. Right? The next row, similarly, 0x plus 1y plus 0z is minus 5. Y is minus 5. That last row, 0x plus 0y plus 1z, z equals 2. Okay, we've got our answer. What about the next one? So in the next example, the first row says x minus 2z equals 4. The next row says y plus z equals 5. The third row just says 0 equals 0. It tells me nothing, right? Really, this just says this is 0, this is 0, 0 equals 0. Yes, that's true. Right? So the third row contributes nothing. And so I haven't said anything about what z is. And so what we do here is we just say z is free. And one of the things that we often like to do in this case is we might do this. We might say, let's let z equal to t. Okay? And we think of this t is called a parameter. It's a free variable. So this is called a parameter. And in terms of that parameter, we get this solution. We get x equals 4 plus 2z, but z is t, so x is 4 plus 2t. Y is equal to 5 minus z, so 5 minus t. Z equals t. And you can understand why we might call this thing a parameter, because what you have here, these are parametric equations for a line, right? Remember, what is it? It's a line that passes through the point 4, 5, 0 with a direction vector of 2, -1, 1. Right? So that's a line in 3 dimensions. Hence parameter, right? Because it looks like parametric equations for a line. And one of the things that tells us is we can interpret the solution to this system geometrically, right? So geometrically, the solution to this system is a line in 3 dimensions. It's a line passing through a given point in a given direction, and every point on that line represents a solution to our system. Okay, now, the last one, this is one of the things you want to be on the lookout for when you're solving a system. If this shows up, we don't bother writing down anything, because that last row says 0x plus 0y plus 0z equals 1. And you ask yourself, all right, are there any values of x, y, and z that can make 0x plus 0y plus 0z equal to 1? And I hope your answer is no, because we certainly know that 0 is not equal to 1. Okay, and so what does it mean in this case? If you see a row like that with zeros to the left of the bar and something non-zero to the right, that means that there is no solution. Okay, you just write that down straight away. No solution. Don't bother. Yes, the first row tells me that x equals -4. The second one says z equals 3. Who cares? There's no solution. Those values tell me nothing about how to solve the system, because to solve the system I have to solve all equations, and I can't satisfy that last equation. So there's no solution. There's no way to solve this system. Okay. So here is the Gaussian algorithm, okay, for solving a system, the so-called forward steps. We'll talk about, there's kind of two sets of steps that we do, but we start with the forward steps. So you start in the upper left-hand corner, and you work down and to the right. So you go from left to right, top to bottom, right? And so if you're programming a computer, well, one of the things you'd have to say is okay, is it the zero matrix? If it is, you do nothing. You can't simplify the zero matrix, right? But it's probably not the zero matrix. So if it's not the zero matrix, then you find the first column. There's got to be a column that has something non-zero in it, right? And you find the first column containing a non-zero entry, all right? And you make sure that at the top of that column, the first entry in that first non-zero column is a 1. So you use elementary row operations of your choice to get that leading 1 at the top of the first non-zero column. Once you've got that leading 1, you get rid of anything below it in that column. So that first column should be a 1, right? So your first non-zero column ends up looking like 1 and then 0 and then 0, zeros all the way down, right? And then you move on. Once you're done with it, by the way, you stop working with that column. You leave it alone. You move on to the next one, and you keep repeating until you're done. Okay, so here's what it looks like. All right, we've got an augmented matrix. We want to reduce it down to row echelon form. We won't worry about reduced row echelon form yet. Okay, so the first thing I could divide row 1 by 2, but the smart thing to do here is probably swap row 1 and row 2. Okay, 1, 3, -1, 4, 2, -1, 3, 1, -1, 1, 0, 2. Okay, and so now I've got my leading 1, and I'm going to use my leading 1 to create zeros. So what zeros do I have to create? I've got to create zeros here and here. So to get rid of that 2, I'm going to have to do row 2 minus 2 row 1 and make that my new row 2. To get rid of that 1, I'm going to have to do row 3 plus row 1 and make that my new row 3. Okay. Notice I'm doing 2 row operations at a time, but they affect different rows, so I can get away with this, and it saves me a little bit of writing. So we don't change the first row. Let's leave that guy alone. Okay. So now I'm going to get rid of that 2. 2 minus 2 gives me 0. -1 subtracts 6. I get a -7. 3 subtract minus 2, 3 plus 2, I get a 5. 1 minus 8, I get minus 7. Okay. Now I add row 1 to row 3, minus 1 plus 1, 0, 1 plus 3, 4. Okay. 0 plus minus 1, minus 1, 2 plus 4, 6. Okay. So now you're done. You've got that first column, right? 1, 0, 0. So here's the thing. Once you've got that first column, you've created that leading one and the zeros below it. Stop working with that column, and that means you got to stop working with row 1. Okay, so we leave this stuff alone. We leave it alone. Okay, it's part of our matrix, but we ignore it, and we kind of boil things down to this smaller matrix, right? This matrix now is so basically we started with 3 equations, 3 unknowns. Now we're down to 2 equations, 2 unknowns, right? So we ignore that first row, first column, and we deal with this smaller system. This is the idea with the algorithm. At every step, you're cutting things down to a system of a smaller size. All right. So now we repeat the algorithm for this 2 by 2 system that we have left over. How are we going to do that? Well, one option would be to divide row 2 by minus 7, create my leading one that way, but then I'm going to get a minus 5 over 7 there. Maybe we're not so keen on those fractions. So one of the things I might notice if I'm paying attention is, well, 2 times, I've got a 4 sitting here, 2 times 4 is 8, adding 8 to minus 7, that gives me a leading one, right? So this is not necessarily, from a computer's point of view, this row operation, doing row 2 plus 2, row 3, oops, and making that my new row 2. This is technically a deviation from the algorithm that you would give a computer. The computer would divide by minus 7 because that is the most efficient way of doing things. But as humans, we tend to prefer to avoid fractions if we can. So minus 7 plus 8 gives me a 1. 5 minus 2 gives me a 3. Okay. Minus 7 plus 12 gives me 5, 0, 4, minus 1, 6. Okay. All right. Now I've got 2 leading ones. What's my next step? My next step is I've got to get rid of any non-zero entries below my second leading one. That means I got to get rid of the 4. How do I get rid of the 4? I should do row 3 minus 4 times row 2 and make that my new row 3. And again, because I've got zeros to the left of that leading one, I don't have to worry about what happens in this first column, this highlighted column, right? These guys here are still, they're still out of bounds. We're not dealing with those, right? They don't come into the picture. 1, 3, minus 1, 4. I'm not changing the second row, 0, 1, 3, 5, 0. So I get my 0. 3 times minus 4 gives me minus 12. I'm adding that to minus 1. I get minus 13. Minus 4 times 5 gives me minus 20. Added to 6 gives me minus 14. Okay. All right. So now I kind of hive things off like this, and I'm just left with a 1 by 1 system. There's only one thing left to do at this point. There's only one thing really that I can do. I got to divide by minus 13. Create my last leading one. I've got no other choice here. So I do minus 1 over 13, row 3. That's my new row 3. 1, 3, minus 1, 4, 0, 1, 3, 5, 0, 0, 1, 14 over 13. And we're done. That's in row echelon form. We could, if we wanted to, we could continue on to reduced row echelon form from here, but that's a topic for the next video. Okay, so in this next video, we're going to move on from the algorithm we introduced in the previous video, the Gaussian algorithm. And we're going to talk about what happens once you get to row echelon form. We mentioned that there's a simpler version of row echelon form, the reduced row echelon form, right? So once you get down to a row echelon form, you might want to continue on. And one of the reasons you might want to continue is that there are many different row echelon forms, but there's only one reduced row echelon form. The reduced row echelon form is unique, and everyone can agree on the reduced row echelon form. So finding the reduced row echelon form amounts to kind of continuing on. So the Gaussian algorithm, we mentioned this last time, gives us these forward steps, right? We move from left to right and top to bottom, and we create our leading ones, right? So this was what we did in the previous. We saw one example. We ended with an example last time, right? So moving from left to right in each column, we create a leading one, and we make sure there's zeros below that leading one. We move on to the next column. We keep repeating, right? This is the idea. Now, that gets you to row echelon form, but you want to keep going from row echelon form to the reduced row echelon form. You'd like to simplify further. So where do we go from here? Well, there are two ways that we can proceed to the solution from a row echelon form. One is using what's called back substitution. So we kind of look at that bottom row first. That bottom row says, again, let's label these columns X, Y, Z, right? So the bottom row says that 1 times Z equals 5, right? So Z equals 5. So now we know what Z should be. So we look at the next row. The next row says 1Y minus 3Z equals minus 2. Okay. Well, that means that Y is minus 2 plus 3 times Z, which is 5. So Y has to be 13. The top row says 1X plus 2Y minus Z equals 4. Okay, and so X is 4 minus 2Y plus Z. So that's 4 minus 2 times 13 plus 5. Okay, which is going to give me minus 17, I believe. There we go. Okay, and so now I know what X, Y, Z are. So X is minus 17, Y is 13, Z is equal to 5. Notice one of the reasons why the leading ones are quite useful is that in each one of these equations, right, we can immediately solve for the first variable, that leading variable in each equation, the one corresponding to the leading one, right? All we do is throw the other stuff to the other side and we're done. Now, Gauss-Jordan elimination is a continuation of this algorithm using row operations, but now in the Gaussian algorithm we work from the top down. We get this staircase of leading ones. In Gauss-Jordan elimination, now we work backwards, and we go from the bottom right. We start at the bottom right, and we kind of go back up, right? So from the bottom right, we go back to the top left. Right? We go in the opposite direction. But this time, instead of creating zeros below our leading ones, we create zeros above our leading ones. Okay. So we start now not on the leftmost column, but the rightmost column. And we say, okay, in that right, not the constants, but the rightmost variables column, right? The sort of the leading one that's the furthest to the right. We say, okay, how can I use that leading one to get rid of any non-zero things above it? Well, in this case, we see that we should do, if we do row 1 plus row 3, and make that my new row 1, I'll get rid of the minus 1. Then I can do row 2 plus 3 row 3. Make that my new row 2. And that gets me to 1, 2. So minus 1 plus 1 gives me the 0 I'm looking for. 4 plus 5 gives me a 9. Then 0, 1. So minus 3 plus 3 gives me a 0. Minus 2 plus 3 times 5, minus 2 plus 15 gives me 13. 0, 0, 1, 5. Okay. And so now, that leading one is the only non-zero entry in its column. The first leading one is always the only non-zero entry in its column. We've got one left to deal with. What do we have left? We've got this 2 here. We got to get rid of that 2, but we know how to get rid of the 2. We take row 1 and we subtract 2 row 2 and make that my new row 1, right? 2 subtract 2 is going to give me my 0 that I'm looking for. So I get 1, 0, 0. And so now I got to do 9 minus 2 times 13. So 9 minus 26 gives me minus 17. 0, 0, 1, 5. And now we're in reducer echelon form. Okay. And you can also see that from reducer echelon form, you can immediately read off the answer, and it's the same as before, right? The first row says x is minus 17. Second row says y equals 13. Third row says z equals 5. And you're done. Okay. All right. Here's another example. We'll apply the Gauss-Jordan algorithm here. Now, one of the, back substitution is fine. You can do back substitution. One of the places where we're continuing all the way to reducer echelon form is useful is when there are free variables. If there are parameters around, it's nice to continue all the way. We know that in this system, if there is a solution, we're going to have at least one free variable because we have more variables than equations. It's not going to be possible to completely determine all 4 variables. We're not going to be able to get a unique value here. So, start with the augmented matrix. 1, 2, 1 for the x1 variables, minus 2, minus 4, minus 2 for the x2 variables, minus 1, 1, 2, 3, 0, minus 3 for x4, 1, 5, 4 for my constants. Okay, so I've already got a leading 1 in the upper left-hand corner, so we leave that alone. We don't want to lose our leading 1. We've got it right where we want it. So we keep it there, and we use it to create zeros below. So we do row 2 minus 2 row 1. That's going to be my new row 2. Row 3 minus row 1. If I make that my new row 3, that's going to get rid of the 1. Okay. 1 minus 2 minus 1, 3. Oops. Got ahead of myself there. 3 bar 1. So 2 minus 2, 0. Minus 4 plus 2, 0. 1 plus 2 gives me 3. 0 minus 6 gives me minus 6. 5 minus 2 gives me 3. Okay, now row 3 minus row 1. 1 minus 1, 0, minus 2 minus 2, 0. 2 subtract minus 1, 2 plus 1 gives me 3. Minus 3 subtract 3 more, minus 6. And 4 minus 1, 3. Okay. So, now you notice, hey, look at this, guys. This row and this row, those are the same. So here's what I would do, right? I'm going to be a little bit lazy because I know what's going to happen. I know that that second row is going to cancel the third row. I know that that's going to be gone, right? So I'm gonna kind of say, well, one of the things I'm going to do, there's going to be a step, but I'm going to skip it. I'm going to do row 2 minus row 3 and make that my new row 3. But I'm not going to bother to write down that step because I know what that step's going to be. It's just going to create that row of zeros on the bottom. Sorry, row 3 minus row 2. Mixed up my subscripts. Row 3 minus row 2. The other thing I need is, well, I need in the row 2, I need that this 3, the first non-zero entry in that row. I need that to be a 1. I need a leading 1. How can I get a leading 1? I can divide by 3. So I'm going to 1/3 row 2, make that my new row 2. Okay, so I'm not touching row 1. And remember, I don't want to, right? Once I've got this column here with zeros below my leading 1, I forget about that first row and that first column, and I work with the smaller system that's left. And then you might say, hey, the first row or the first column in that smaller system, here's one of those places where that first column might end up being all zeros. It's a column of zeros, so I don't really worry about that. Really, I should be working just on this smaller system here, right? So I'm not going to do anything that affects, I'm not going to do anything using row 1, because anything using row 1 might get rid of these zeros I just worked hard to create. So I'm going to divide by 3 in row 2, 0, 0, 1, minus 2, 1, 0, 0, 0, 0, right? So those rows, that row of zeros at the bottom was created in this step that I didn't bother to write down. Okay, at this point I'm in row echelon form, right? I've got my leading ones. My row of zeros is at the bottom. My non-zero rows begin with a 1, right? Below my leading ones, I've got zeros. This guy is in row echelon form. It's not yet in reduced row echelon form because of that guy, right? So at this point, I've done the Gaussian algorithm. I've done the forward steps. I'm down to row echelon form. Now I kind of do this backward steps, and there's only 1. I got to get rid of that minus 1 to get down to reduced row echelon form. So I do my Gauss-Jordan steps. So I go, how do I get rid of that 1? Row 1 plus row 2 is going to be my new row 1. 1 minus 2, 0. 3 minus 2 gives me 1. 1 plus 1 gives me 2. 0, 0, 1, minus 2, 1, 0, 0, 0, 0, 0. Okay. So what I get here is I'm in reducer echelon form now. It's reducer echelon form. Let me jump up to the top. So the first equation says this. It says x1 minus 2x2 plus, notice there's no x3 in there, but there's an x4 equals 2. The next one says x3 minus 2x4 equals 1. Okay? So notice that first equation I can quickly solve for x1 in terms of x2 and x4. The second equation I can quickly solve for x3 in terms of x4. I don't say anything about x2 and x4. Those guys are actually my free variables here. So x2, x4 are free. Okay? You can leave them as x2 and x4 if you want, or you might, if you like. I prefer to do this. I prefer to say, let's assign them to parameters. So x2 will be s, x4 will be t, and so then then this is my solution, right? So I get the following solution. I get x1 is going to be equal to 2 plus 2s minus t. x2 is simply s. x3 is 1 plus 2t. x4 is equal to t. And s and t here can be any real values that they want, right? So I've solved my system, right? This is the best I can do for solving this system. I give values for x1, 2, 3, and 4. They depend on 2 parameters, but I can't do anything about that, right? I have infinitely many. This is a case where I have an infinite number of solutions, okay? Because, I started with more variables than equations, and that row of zeros tells me that actually my third equation was redundant anyway. So really I only had 2 equations with 4 variables. And with 2 equations, I can only really eliminate 2 of those variables. So I'm left with 2 that are free to take on whatever values they want. And so that's my system, my solution in this case. Okay, one more example. What do we get here? So we follow the same procedure. Step 1. Augmented matrix. 1, 0, 10, 5 for the first equation, 3, 1, minus 4, minus 1 for the second equation, 4, 1, 6, 1 for the third equation. Okay, again, things were handed to us in a convenient fashion. There's already a leading 1 where we want it, so we got to use that leading 1 to create zeros. So we're going to do row 2 minus 3 row 1 and make that my new row 2. I'm going to do row 3 minus 4 row 1 and make that my new row 3. Row 1 stays the same. 0, 1. Nice thing about that 0 in that second column means I don't have to worry about what goes on there. Minus 4 subtract, minus 4 minus 30. So minus 34. Okay, we can handle that. Minus 1 subtract 15. Minus 16. All right, then 0, 1. 6 subtract 40. Uh-oh, that's another minus 34. And 4 times 5, that's 20. So 1 minus 20. I get minus 19. Okay. Let's double check. Did I make any mistakes? I don't think I made any mistakes. Minus 1. Yep, I think we're good. So what does this mean? Well, let me do one more row operation. Row 3 minus row 2 is going to become my new row 3. 1, 0, 10, 5, 0, 1, minus 34, minus 16, 0, 0, 0, and minus 3. Okay, so I stop at this point and I say, is there, this is not I mean, I guess it's technically not in row echelon form because this guy is the first non-zero entry in the third row, right? But do I care? Do I continue reducing from here? No, I don't do anything more because what does that third row tell me? This third row says that 0 equals minus 3. Well, that's not true. So what can we conclude in this case? That third row is a contradiction, and that means that there is no solution to this system. By the way, this is one that you might find interesting to go ahead and maybe ask a computer to plot it for you, see what happens. Right? Each of these equations gives you the equation of a plane. Right? The fact that there's no solution, there's a number of ways in which three planes can intersect in ways that don't give you a solution. Right? So there's no point that's common to all three planes. Probably what you're looking at here is something where one of the planes kind of goes like this, and another plane goes like that, and another one goes like that. So you kind of have some sort of, intersection like this going on. It's kind of hard to sketch this thing out, right? But you have this sort of picture here. So, those planes intersect along, so there are points that these two planes have in common. There are points that these two have in common. But that you get this kind of they form this sort of triangle, this triangular tunnel between the planes, right? And so there are points that are common to any two of the three planes, but there's nothing that's common to all three, and so there's no way to solve the system in this case. Okay, one last example, and then we'll call it a day. How do we solve this? Let's fix that. This should be an equal sign, of course. That's an equal sign, not a plus sign. Missed the shift key there. Let's proceed to solve. 3, 2, 4, 4, 3, 3, 1, 0, minus 1, 1, 0, 2. Okay. What do we want to do here? So this time you might notice there is no 1 in the first column, right? There's lots of non-zero entries in the first column, but none of them are equal to 1. So now I choose. Do I want to divide, let's say divide by 3 and create fractions? If I'm a computer, I probably do. As a human, I think what I'm going to do here is I'm going to do this. I'm going to do row 1 minus row 2 and make that my new row 1, right? Because 3 minus 2 gives me a 1. 4 minus 3, 1. 1 minus 0, 1, 1. Okay. That's a little better. All right. Now I've got my leading 1, and I can use it to make some zeros. So I'm going to do row 2 minus 2 row 1. That's going to be my new row 2. Row 3 minus 4 row 1.
That's going to be my new row 3. 1, 1, 1, 1, 0, 1. So 3 minus 2. 2 minus 2 gives me 0. 3 minus 2 gives me 1. 0 minus 2 gives me minus 2. 0 minus 2 gives me minus 2. 0. 3 minus 4, minus 1. Minus 1 minus 4, minus 5. 2 minus 4, minus 2. All right. You guys that are playing along at home, make sure my arithmetic is correct. I'm trying not to take up too much time on these videos. So there's always a chance that I mess up. Okay. Now I've got 1, 2 leading ones. Again, be careful at this stage. Don't do anything with this. You know, this guy's out of the picture. We're just working. We're working here on this smaller system. And we see what do I want to do. I want to use that leading 1 to get rid of the minus 1 that's below it. So I should do row 3, oops, plus row 2. Make that my new row 3. 1, 1, 1, 1, 0, 1, minus 2, minus 2, 0, 0. So minus 5, minus 2, minus 7, minus 2, minus 2, minus 4. Okay, at this stage, you got no choice. You got to bring in the fractions, right? They show up sometimes, and there's not much you can do about it. The next thing I got to do is minus 1 over 7, row 3. That's going to be my new row 3. So we recopy the first 2 rows. 0, 0, 1. And 4 over 7. Okay, this is in row echelon form, right? I've got my leading ones, leading 1, leading 1, leading 1. I can choose from here. I'm gonna give you guys the exercise. Of finishing. And you've got 2 choices for finishing this guy off. You can finish off using back substitution, right? We know that z is 4 over 7 now. Work your way back. Do you want to do back substitution, or do you want to continue the row operations all the way down to reduce row echelon form? It's up to you. You might want to try both ways, see which one you like better, and that might inform your process going forward as to which method you want to use. Okay, so we've now looked at a number of examples of systems of equations. We've seen that as far as the solutions go, there's sort of 3 scenarios that we run into. Sometimes there's one unique solution where we have exact values for every variable. Sometimes there's no solution at all, and occasionally we get an infinite number of solutions. We end up with free variables, right? Some of the variables can be assigned to parameters that take on any value, and then we can generate an infinite number of solutions. Now, a homogeneous system is one where all the constants on the right-hand side are 0, and so because the constants on the right-hand side are 0, it's impossible to run into an inconsistent system, right? One where there is no solution. So why is that the case? Well, think about this guy in matrix form. We discussed in class that we can if we let x equal to a vector containing the variables x1 down to xn, right? Then we can write down this matrix A consisting of all the coefficients, and the matrix form of this equation is simply A times x equals 0. And so what is one solution that works? Well, we know one solution that works. One solution we can take is simply x equals 0, right? So the 0 solution, where all the variables are 0, is always an option for a homogeneous system, right? And so with a homogeneous system, the question is not whether or not a solution exists. The question of interest is whether that solution is unique, right? And to some extent, we don't really want a unique solution here. With non-homogeneous systems where we have numbers on the other side, often we want that unique solution. We want to know there's one right answer. But here, you know, a unique answer is that everything is 0. That's kind of boring. If we get a non-zero solution, we'll see that what ends up happening is, you know, if we have a non-zero solution, that means that we can solve for some of our variables in terms of the others, and
that gives us some relationships among those variables that might be useful for some sort of problem that we're studying. Okay. So here's an example of a homogeneous system, right? We see that we've got zeros over here on the right, and actually we can say right away that this system is going to have an infinite number of solutions. We know that that there's not going to be a unique solution simply because we have more variables than equations, right? As we reduce this thing down, right, there's no way, think about it this way. A unique solution corresponds to a leading one in each one of the variable columns, right? We'd have to have a leading one in the x column, in the y column, z column, w column. We've seen that that's how it works with a unique solution. Every column gets a leading one. Well, there are more columns than rows, and every leading one lands in a row, so we can't possibly have a leading one in every column. Okay. So here's one where we expect something interesting in the solution. Let's see what it looks like. So we write down our augmented matrix. I'm going to put this column of zeros on the right. You don't really have to bother with the column of zeros, right? Because this column of zeros is going to remain a column of zeros all the way through. So if you just want to work with the matrix of coefficients and forget about the zeros, go right ahead. It's not really going to affect things. But let's put it there just to remind ourselves that we are really solving a system here. And let's proceed. So we've got our first leading one, right? We've got our one up here where we want it in the upper left-hand corner. So let's use it to get rid of that 2 below. So we got to do row 2 minus 2 row 1. That's going to be my new row 2. 1, 3, minus 1, 4, 0. 0. Minus 1 minus 3 gives me minus 7. 5 minus minus 2, that's 5 plus 2, gives me 7. 6 minus 8, that gives me minus 2. I get a 0. Okay. And then 0, 4, minus 2. You know what, actually, let's save ourselves a little bit of work in the next step. Notice that everything's even in that third row. So while I'm at it, I'm going to do this. I'm going to do 1/2 row 3 and make that my new row 3. Why not? 2 minus 1, 1, 0. There we go. Okay, what's the next step? The next step is to get a leading one in the second column. How are we going to do it? We got some choices here. Here we've got, we've got a few options to consider. Okay, how do we want to do it? We could, here's one option. I could divide the third row by 2 and move it up into the second row. That gives me a couple of halves to deal with, but as fractions go, a half is pretty innocent. I could divide the second row by minus 7, but then I'm going to have a 2 over 7 to deal with in the fourth column. I could probably handle that. Another option might be I could take 4 times this third row here and I could add it to the second row because 4 times 2 gives me 8. 8 added to 7 gives me 1. That seems promising. How do we want to do it? You guys are probably in the no fractions camp, so let's do it. Let's do it that way. So let's do row 2 plus 4 row 3 and make that my new row 2. Doing this, by the way, this actually generally adds steps. It makes things take a little bit longer, but we get out of fractions. Okay, so, not 0, 1, right? So minus 7 plus 8 gives me 1. 7 minus 4 gives me a 3. Minus 2 plus 4 gives me 2. 0's over there. 0, 2, minus 1, 1. Okay. All right. Now I got my leading 1. I can use it to get rid of that 2 below it. So I'm going to do row 3 minus 2 row 2. Make that my new row 3. 1, 3, minus 1, 4, 0, 0, 1, 3, 2, 0.
0, 0. Minus 1 subtract 6 minus 7. 1 minus 4 minus 3, 0. And, well, we knew we couldn't avoid fractions forever. So let's see, what do we got to do now? We got to do minus 1 over 7, row 3. Make that my new row 3. 1, 3, minus 1, 4, 0, 0, 1, 3, 2, 0, 0, 0, 1, 3 over 7, and 0. I'm in row echelon form now, okay? But we can see that we're going to end up with a parameter here. W is going to be a parameter because there's no leading one in the W's column. Whenever you got parameters, it's usually desirable to continue on all the way to reduced row echelon form if you've got the patience. So how do we get to reduced row echelon form? Well, remember now we do the backward steps. We go from the bottom right back up to the top left. I got to use this last leading one to make zeros above it. So I've got to do row 1 plus row 3. That's going to be my new row 1. Row 2 minus 2 row 3. That's going to be my new row 2. So 0, 0, 1, 3 over 7, 0, 0, 1, 0. Uh-oh. 2 subtract, so I got to do this. I got to do 2 minus 2 times 3 over 7. So that's 2 minus 6 over 7. That's 8 over 7, right? 2 is 14 over 7. 8 over 7, 0. Okay, and now I add row 3 to row 1. 1, 3, 0. I'm adding 4 over 7 to 4. 4 is 28 over 7. 28 plus 3 gives me 31 over 7, 0. Okay. Again, remember that one of the things that's making this work here, these two zeros here, mean I don't have to worry about these columns when I do these backward steps here, using the third row to modify row 1 and row 2. I don't destroy the work that I've already done. All right, what's the last step? The last step is use this 1 to get rid of the 3. So there's one more step. One more step is going to be row 1 minus 3 row 2. Make that my new row 1. And I'm short on space, so let me just write down what that first row is going to look like. 1, 0, 0. And then I got to do another one of these guys. 31 over 7 subtract 3 times 8 over 7. 31 minus 24. Oh, interesting. That's 7 over 7. I just get a 1. Okay. Did I do that right? I feel like that's a little too easy. I think my arithmetic is okay. 31 minus 24. Yep. Okay. All right. So that would be, that would be my new row 1 eventually. Okay. So what all does this tell me in the end? What kind of relationship do I get among my variables? Let me get rid of these fractions. We don't need those so much. What's my solution? My solution is, well, I've got x plus w equals 0, so x equals minus w. Y plus 8 over 7 times w equals 0, so y is minus 8 over 7w. Z plus 3 over 7w equals 0, so z is minus 3 over 7w. And, well, w equals w. W is free. Free to be whatever its heart tells it to be. There we go. Okay, so that's our solution in this case. All right, now
let's think of some things we can do, some situations that lead to homogeneous systems of equations. There's a few that we've run into. One is this problem of linear independence, right? So we saw that this test for independence is, well, one way to test if a collection of vectors is independent is I set up a linear combination like this, set it equal to the 0 vector, and if my vectors are independent, then the only linear combination that's going to work here is the trivial one where I set all of my x's equal to 0, right? And we know that this gives us independence because if one of the x's is not 0, then I can solve for that vector in terms of the other vectors, and then I would know that my vectors are dependent, right? So this leads to a system of equations, right? Because if I have my vectors in there, you know, if v1 looks like a11, a21 down to an1, right? And so that's v1, this guy here. And if v2 looks like a12, a22 down to an2. Oops, I'm missing my x2, and so on down to xk. Right, here's v2, and if vk is a 1k, a 2k down to a nk, there's vn, and that's equal to the 0 vector. Well, you can see that homogeneous system staring you in the face, right? a11 times x1 plus a12 times x2 down to a1k times xk equals 0, a21 times x1, and so on, right? So we've got that homogeneous system sitting there. So determining independence, it basically amounts to solving a homogeneous system. Let's give it a try, okay? So we want to determine if these vectors are independent. Now notice that if we wanted to kind of set up the corresponding augmented matrix, right? How do we solve? We solve by reducing an augmented matrix, and what is that augmented matrix? It's going to be, you know, v1 in the first column, v2 in the second column, down to vk in that last column, and you know, if you want, you can add the zeros in. The zeros are not really important. So what we do is we let a equal minus 1, minus 2, minus 1, 0, 3, minus 2, 3, 0, minus 7. Okay? So we create a matrix whose columns are these vectors, and now we reduce. We figure out what the reducer echelon form is. And if we end up with a leading 1 in every column, right? If we end up with a leading 1 in each one of the columns, that gives us the unique solution. It tells us that x1 is 0, x2 is 0, and so on. If there's going to be a column with no leading 1, that means the corresponding variable is free. We get a parameter, and that means we can come up with a non-zero solution. So let's reduce. We've got a leading 1, so what are our first two row operations? Row 2 plus 2, row 1 becomes my new row 2. Row 3 plus row 1 becomes my new row 3. 1, 0, 3, 0, 3, 6, and 0, minus 2, minus 4. And you can maybe see what's going to happen here. What do we do next? So the next thing I might do is do 1/3 row 2. Make that my new row 2. 1, 0, 0, 1, 2, 0, minus 2, minus 4. I've got my second leading 1, and now I can use it to get rid of the 2 below there. So if I do row 3 plus 2 row 2 and make that my new row 3, what do I get? 1, 0, 3, 0, 1, 2, 0, 0, 0. Okay, so we we get down to a reduced row echelon form where there's a row of zeros, right? So now, if we were solving this equation, right, a times x1, x2, x3 equals 0, 0, 0, right? That's essentially the system, right? So then we would go to the augmented matrix, A with a 0, and we reduce down, we get that down to the reduced row echelon form, and it looks like 1, 0, 3, 0, 1, 2, 0, 0, and, right, so put that column of zeros back in that we didn't bother to write, and what does it tell me? It tells me that x1 could be minus 3x3, x2 could be minus 2x3, and x3 is free to be anything. So since x3 is free to be whatever it wants, it doesn't have to be 0. If I put x3 equal to, let's say I put it equal to 1, right? That's going to give me x1 is minus 3, x2 equals minus 2. That suggests that minus 3 v1 minus 2 v2 plus v3 equals 0, right? So that's not 0. That's not 0. That's 1 times v3. That's not 0. So this tells me that the vectors are dependent. Because I found a linear combination of these vectors other than the trivial linear combination that adds up to give me the 0 vector, right? The way I would have known if these ones were not independent, the way I would have known they were independent is if I ended up with a 1 in this spot rather than a 0, then I would know that the only solution is everybody equals 0, and I'd be done. Now, notice that, this system, if I wrote this system in matrix form, right, this system of equations that we get when we solve for independence, we mentioned this in class, right? Questions about independence are closely related to questions about null space because, if I take A, if this is my A, right, then this equation here is simply A times the vector x equals the vector 0, where x is the vector containing these guys as components, right? We see that here. Right. So the other way to think about what I'm doing here, the other thing you could think about what I'm doing is I'm trying to solve for the null space of my matrix, right? And so in that language, in this language of null space, I guess what we could say is that these vectors are linearly independent if and only if the only vector in the null space of this matrix A is the 0 vector. Since we found examples of non-zero vectors in the null space, we know that they have to be dependent. Okay. So here's one more example. Let's say I want to determine the null space of this matrix here. So remember, the null space is all of the vectors x, so that A times x equals 0, right? So that equation, think about, so A times x equals 0. In this case, x is going to look like x1, x2, x3, x4, okay? So the system of equations would be 2x1, 0x2 minus 3x3 plus x4 equals 0, minus x1 plus 4x2, 2x3, 3x4 equals 0, and so on. So we know how to solve this. We set up our augmented matrix, we reduce. In fact, we'd have zeros on the right-hand side, so it's enough to reduce A. Okay, so we want to reduce A. So probably the first thing I'm going to do here is I'm going to swap row 1 with row 2. Minus 1, 4, 2, 3, 2, 0, minus 3, 1, 0, 8, 1, 7. Okay, and then I'm going to do, well, again, maybe I won't bother to write this one, so I'm going to switch the signs on row 1. So that's going to become plus 1, minus 4, minus 2, minus 3.
Okay, then I'm going to do row 2 minus 2 row 1 to use my leading 1 to get rid of the 2. 1 minus 4 minus 2 minus 3, 0, 8, 1, 7, oh, 0, 8, 1, 7. How about that? Okay, so what's next? Row 3 minus row 2 is going to be my new row 3. 1 minus 4 minus 2 minus 3. Well, let me skip writing down that step. We know that's going to give me my row of zeros. Let me also do 1 over 8 row 2. I'm going to make that my new row 2. 0, 1, 1 over 8, 7 over 8, 0, 0, 0, 0. And then let's go all the way down to reducer echelon form. So I got to do my backwards step. I got to go row 1 plus 4 row 2. Make that my new row 1. 1, 0. 4 times 1 over 8 is a half, so minus 2 plus a half leaves me with minus 3 over 2. Minus 3 plus a, okay, here I'm going to do 4 times 7 over 8, so 7 over 2. Minus 6 over 2 plus 7 over 2 leaves me with 1 half. 0, 1, 1 over 8, 7 over 8. Okay, there's my reducer echelon form. So what does this tell me? Right, I'm trying to figure out which vectors satisfy a times x equals 0, right? And so remember that this represents x1, x2, x3, x4. Leading ones in the x1, x2 columns, right? So remember I kind of, setting everything there. There's the column of zeros I don't bother to write. So the first row tells me that x1 is equal to 3 over 2x3 minus 1 half x2. The second row says x2 is minus 1 over 8x3 minus 7 over 8x4. Sorry, this is a 4 here. Okay. And that means that if I plug those in, x looks like 3 over 2x3 minus 1 half x4, and then minus 1 over 8x3 minus 7 over 8x4, x3, x4. So if I split that up, x is going to look like x3 times 3 over 2 minus 1 over 8, 1, 0, plus x4 times minus a half minus 7 over 8, 0, and 1. Right? So these two vectors, this guy here, those are going to be the basis vectors for the null space, right? So any element of the null space is going to be written as a linear combination of those two vectors by choosing values for x3 and x4. Okay, that's it for this one. All right, so here's the next in our series of videos on systems of equations. There's a couple more to follow this with a little bit of theory in them, I suppose, but this is an example of some of the applications, things that we've mentioned in the past that that lead to systems of equations. We mentioned that questions about span, questions about column space, that these are really problems that need to be solved by solving systems of equations. And at the time we didn't have methods for solving, so we left this alone, right? Now, remember the definition of span. So the span of a set of vectors is all of the linear combinations that you can form with those vectors. So if I tell you that a vector w belongs to the span of these vectors v1 up to vk,
what I'm telling you is that I can write W as a linear combination, right? So W is a linear combination of those vectors. What I don't know is what values, x1, x2, I don't know what these values are, right? So my job, if I want to know, well, one, whether or not W does belong to the span, and if it does, what are the coefficients? Well, this amounts to solving a system, right? Because if V1, again, if V1 looks like A11 down to maybe AN1, right? X2 times V2 looks like A12 down to AN2, right? And so on up to XK, and VK looks like A1K down to ANK. And if W looks like, let's say, B1 down to Bn, right, well, we can see what our system is going to be. A11 times x1, A12 times x2, up to A1k times xk, right? And so we could also write this, right? We could write this as A times x is equal to B. Well, not B, it's W, so let's leave it as W, right? W, right, where x is this guy, x1 to xk, and A is the matrix formed by putting in these vectors. Okay, so you can guess what you do. We got to solve our system, so how do we solve? Well, we're going to reduce the augmented matrix A W to, well, row echelon form at the very least, possibly reduce row echelon form, depending on how we want to go. Okay, so let's try this out. Here's a vector W, here are some vectors, V1, V2, V3. We want to figure out if W belongs to the span of these vectors, so we set up our augmented matrix, -1, 2, 0, 0, 2, -3, 1, 0, 4, okay, and then 2, -4, 3, right? So here's your V1, here's your V2, here's your V3, here's your W. And we proceed. So, all right, we've got a, well, it's a leading -1. Let's do this first. I'm going to do row 2 plus 2 row 1 and make that my new row 2. So what happens when I do that? 2 minus 2 gives me a 0. 2 plus 0 is 2. 0 plus 2 is 2. And -4 plus 2 gives me a -2. While I'm at it, let's switch the signs on row 1, because I do want a leading 1 there. 1, 0, -1, -2. All right, so you want to be careful if you try to do these two steps at once. It's very easy to get a sign error, right? So let's be careful on that. 0. Didn't do anything down here, so let's just recopy that. 0, 3, 4, 3. Okay. Easiest way to get my next leading 1 is to divide that second row by 2. So 1/2 row 2 becomes my new row 2. 1, 0, -1, -2, 0, 1, 1, -1, 0, -3, 4, 3. Okay. So next up, what do I got to do? I got to use my second leading 1. I got to use this leading 1 here to get rid of that -3. So we got to do row 3 plus 3 row 2. Make that my new row 3. 1, 0, -1, -2, 0, 1, 1, -1, 0, 0, 7, 3, -3, 0. Okay. Gets me down to there. Excellent. And notice that we can answer yes. We can already answer yes, right? Because I got a leading 1 in every column. You might say, wait, there's no leading 1 in that last column. Well, that's true, but I can, let's just squeeze in one more step, and I won't bother to write it down. 1 over 7 row 3 becomes my new row 3, and then this 7 becomes a 1. There's my leading 1. Okay, maybe I want to figure out from here what values of x1, x2, x3 are going to do the job. But I can already see that this one here tells me that that x3 should be 0. 1 times x3 should be 0. And if I were to back substitute, well, then I'm going to get, I'm going to get zeros in here and in here. And so this says, if this is going to work, this says that x1 should be minus 2, x2 should be minus 1, x3 should be 0. All right, why don't we make sure that we didn't mess that up? If I do minus 2 times v1, minus 1, 2, 0. Okay, there's my x1, v1. Minus 1 times 0, 2, minus 3. There's my x2, v2. And, well, 0, I'm not going to write the other one. It's 0, right? So what do we get? 2 times 1 is minus 2 times minus 1 is plus 2. Subtract 0 gives me a 2. Minus 2 times 2 is minus 4. Subtract 2 more gives me a, oh, I've messed something up, haven't I? Minus 6. 0 minus minus 3, 3. Something has gone wrong in the middle. All right. Can you guys find my mistake? Should we go back and look, or should we brush this off and move on? I think we should check to, why don't we find our mistake? This is the nice thing about most of these problems in linear algebra. If we make a mistake, we can go and find it. So let's look for our mistake. Did I copy everything down correctly? I did. All right. Did I do my first row operation correctly? Minus 2 gives me a 0. 2 plus 0 gives me a 2. 0 plus 2 gives me 2. Minus 4 plus 2 gives me minus 2. And I changed my signs. That last row is still fine. Okay. Divide through. So far, so good. So then I'm multiplying through by 3. 3 minus 3. 0, 7, 0. Okay. Seems all right. X1 is minus 2. X2 is minus 1. All right. Where is my mistake? Can't find it. Can you guys find it? All right. We'll have to come back to this one later because I don't see my mistake. Okay. All right. Let's move on. Here's another example. Okay, I want to figure out for what values of A, B, and C this vector W, ABC, belongs to the span of these vectors. So we set this one up the same kind of way as before. We set up our augmented matrix. Minus 3, 1, 0, 0, 1, 6. Well, this time we don't know what A, B, and C are. We just leave them hanging out there on the other side. But we can still reduce. So how do we reduce? We've got our first leading 1. We got to use it to create zeros. So row 3 plus 2, row 1. That's going to be my new row 3. 1 minus 3, 0, A, 0, 1, 1, B, 0, minus 6, and then 6, and oh, sorry, I'm missing a minus sign. That might cause me some trouble later on, wouldn't it? And then C plus 2A, right? I'm adding 2 times row 1 to row 3, so 2 times A gets added to C. All right. Well, now I've got leading 1, leading 1. I might as well get rid of that minus 6. So next up, I'm going to do row 3
plus 6 row 2. That's going to be my new row 3. 1 minus 3, 0. A, 0, 1, 1. B, 0, 0, 0. And then C plus 2A plus 6B. All right. So now we can answer the question, right? Because we got zeros on the left. If this system is going to be consistent, right? So a consistent system corresponds to answering yes to the question of whether or not W belongs to the span. So what do we get in this case? Well, it's going to be all values of A, B, and C, such that 2A plus 6B plus C equals 0. Right? So that lets us describe the span. In fact, we could say the following. We could say that the span, if I write C equals minus 2A plus 6B, right? We could use that to describe the span. We could say, well, in fact, A, B, C looks like A, B, and then minus 2A minus 6B minus there, right? And you could plug that in, and you could say, well, you know what this is then? This is A times 1, 0, minus 2, plus B times 0, 1, and minus 6. And what's interesting is that that tells you that, really the span of V1, V2, V3, it's just the span of V1 and V3. V2, unnecessary. I can throw it away. I can get rid of it. By the way, that's really because I solved for C here in terms of A and B. If I had solved for A in terms of B and C, or B in terms of A and C, I would see different vectors showing up. Okay. So far, so good. Another reminder from class. If we have a matrix, right, we can look at the columns of that matrix as vectors, and we mentioned in class that we can define the span of those columns to be the column space of our matrix A. And we mentioned, right, we connected this back, if we think in terms of the previous example with span, right, the span of these columns, we said, well, this is equal to the set of all y such that A times x equals y for some x, right? So it's the another way to say it is it's the range of the function, this matrix transformation, t of x equals A times x. Okay, so range is something we might want to compute for a function. How do we compute the range of this particular function? Well, using Gaussian elimination. So what we do is we take our matrix, we reduce it down to reducer echelon form. In fact, it's enough to really, by the time you get to row echelon form, you know where the leading ones are. So what you do is you find the columns where the leading ones happen. Okay, you figure out which columns get leading ones. Then you go back to the original matrix. So these are the original columns. And the corresponding columns in the original matrix, those are the ones that generate your column space. So basically, this gives you an algorithm. So we know that the problem here is that, well, we write the column space as the span of these vectors, but some of those vectors might be redundant. Like in the previous example, right, it was enough to just have V1 and V3. V2 was redundant. We didn't need to keep V2. So Gaussian elimination essentially gives us a means of determining which vectors are redundant. So we figure out which vectors end up with leading ones. We keep those ones. We throw away all the rest. So here's an example. How are we going to solve this? So the way we solve this is we reduce. So first thing I'm going to do here
is I'm going to swap row 1 and row 2 because I want to get my leading 1 up top. 1, 1, 2, 0. 2 minus 1, 4. Minus 3, 3, 1, 2. Okay. You know what? Actually, let me make this a little more interesting. Let's make that a minus 3. Okay. All right. So now I'm gonna do row 2 minus minus 2 row 1. I'm gonna do row 3 plus 3 row 1. 1, 1, 2, 0, 0, 0. Minus 5, 4, 0, 0, 5. Sorry, not 5. 3 times 2 is 6, plus 1 gives me 7. And then 2. Okay, and then I can do, what can I do from here? From here, I guess I'm going to do minus 1 over 5 row 2 becomes my new row 2. So 1, 0, 0. 1, 0, 0. 2, 0. I'm going to go 1. Minus 4 over 5. And then 7 and then a 2. And so then I can do row 3 minus 7 row 2 and make that my new row 3. 1, 2, 0, 0, 0, 1. Minus 4 over 5, 0, 0, 0. 2 minus 7 times minus 4 over 5 is 10 over 5 plus 28 over 5. 38 over 5, right? Well, the last thing I would do is I would do 5 over 38 row 3, make that my new row 3, and then this becomes a 1. Okay, so where are my leading 1s? They're here, and they're here. Okay, this one is not a leading 1 because it's not the first non-zero entry in its row. There's a 1 in front of it. Okay. So there are leading 1s in columns 1, 3, and 4, and that means that the column space of A is the span of 2, 1, minus 3, row 1. I skip row 2, I go straight to row 3, and then 4, 0, 2. And actually, one of the things you could do here is one of the things that this theorem tells you. I mean, it tells you it's a basis, right? And we didn't really talk a lot about this idea of a basis, but a basis is a set of vectors that not only spans, it's also independent, right? So what we've done is we've thrown out the dependent vectors. We've kept the essential ones. And so you've actually got 3 independent vectors in R3, and with a little bit more theory, more than we cover, we could argue that in fact those 3 vectors are guaranteed to span all of R3. Any 3 independent vectors in R3, it turns out they form a basis, right? They don't all lie in the same plane, so they actually generate the whole space. Okay. So that is it for now. Okay, so I want to do one last example with eigenvalues and eigenvectors, and then I'm going to get these notes up online in case you want to look at them. So here's another matrix. This one is not symmetric, right? It's not equal to its own transpose. So we're going to work through and see what happens when we try to find eigenvalues and eigenvectors in this case. So get the characteristic polynomial first. So x minus 1, minus 2, 0. Remember, we're putting x's down the diagonal, and then we subtract the entries of a. So minus minus 3 becomes plus 3. X minus 2. 0 minus 3. 0 minus minus 1. Minus 2. X minus 2. Okay. So the next thing we want to do is we want to expand, right? Trying to use row operations to simplify usually doesn't get you very far because you've got those variables that you have to deal with, and it's a bit of a pain. So what we'll do is we'll just expand along that first row because at least there's a 0. So x minus 1 times this 2 by 2 determinant, right? We get x minus 2 minus 3 minus 2 x minus 2 minus 2, right? Remember that in the middle we always put that minus sign in there, right? Across that first row our signs go plus, minus, plus always. Okay, so plus sign in front of the x minus 1, minus sign in front of the minus 2, and then we're going to do these two pieces here. That gives us the second 2 by 2 determinant, so 3, 1, minus 3, and x minus 2. Okay, so x minus 1 times, we have x minus 2 squared minus 6, and then we have plus 2 times 3 times x minus 2 plus 3. Okay, so we start expanding. I'm going to leave that x minus 1 factored out, so x squared minus 4x plus 4 minus 6. I can factor a 3 out, right? 3 is common in this second term. So we'll factor that 3 out. 2 times 3 gives me a 6 out front, and then I have x minus 2 plus 1. Okay, and now the whole point is that, well, not the whole point, but one of the things that we might notice that makes our life a little bit easier is that's x minus 1. And there's another x minus 1 there. So we can group factor, right? Remember, I'm trying to choose examples where you can do group factoring or something that makes it a little bit easier to work these things out. So x minus 1, and then we have x squared minus 4x minus 2, and then plus 6, right? So that plus 6 is coming from there. Okay, so we're actually back to x minus 1, x squared minus 4x plus 4, so x minus 1 times x minus 2 squared. So once again, we have that repeated eigenvalue, right? We have two eigenvalues, right? So we have lambda is equal to 1, and we have lambda is equal to 2, and this one has a multiplicity of 2. Okay, so we want to find the corresponding eigenvectors. So we'll do lambda equals 1 first. And so for lambda equals 1, we're going to do a minus 1 times the identity. And that gives us 1 minus 1, 2, 0, minus 3, 2 minus 1, 3, minus 1, 2, 2 minus 1. So 0, 2, 0, minus 3, 1, 3, and then minus 1, 2, 1. Okay. All right. So what we're going to do is we want to get that down to reducer echelon form. And one of the things I'm going to notice here as well, we're going to divide that top row by 2 to get a leading 1 in that middle column. And then I'm going to use that leading 1, to eliminate those two terms below it. I'm just going to do that kind of cancellation step right away because it simplifies things for me. So I have 0, 1, 0, minus 3, 0, 3, minus 1, 0, 1. Okay, I guess I shouldn't say equals is not quite right anymore. We're doing row operations. There's a couple of row operations in there. I'm not labeling them all just to save some time. And so after a couple more steps, we'll get down to there. Okay, and so in this case, if I have a minus I times x is equal to 0, and x is, let's say, x1, x2, x3. Well, I need x1 equal to x3 and x2 is equal to 0, right? So that x1 equals x3, that comes from this first row, right? That says x1 plus 0 minus x3, that would be equal to 0 in the homogeneous system. So x1 equals x3. That middle row just says 0 plus x2 plus 0 equals 0. So x2 has to be 0. Okay. So what we'll do is we'll take x to be this vector, 1, 0, 1. Okay. And we leave it at that, right? We could get a unit vector if we wanted to, but we'll leave it as 1, 0, 1, right? We keep our numbers simple. So we chose x3 to be 1, set x1 equal to x3, x2 is 0. Okay, so there's our eigenvector corresponding to that first eigenvalue. Now we'll do the second. Lambda equals 2. So I do a minus 2 times the identity. So this time I have 1 minus 2, 2, 0, minus 3, 2 minus 2, 3, minus 1, 2, 2 minus 2, subtracting 2 down the diagonal. So I get minus 1, 2, 0, minus 3, 0, 3, minus 1, 2, 0. Okay, well, we can see that two of those rows are the same. What I'm going to do is I'm going to move that second row up to the top. I'm going to divide by minus 3 to get to there. Okay, and then I'm going to put that there, and we might as well cancel a row while we're at it. And now I'm going to add the first row to the second. 0, 2, minus 1, 0, 0, 0. Okay. So that's not quite at reducer echelon form. We should divide row 2 by 2 to get to reducer echelon form. But it's probably close enough as far as deciding what our vector should be, right? Because if we say that a minus 2I times y is equal to 0, and y is, let's say, y1, y2, y3, well then we get that y1 has to equal y3, okay, and 2y2 has to equal y3. Okay, so what I might do is if I put y2 equal to 1, that says that y3 is equal to 2, and that means that y1 has to equal 2. And so that gives me a vector 2, 1, 2. Okay, for that second eigenvector. And if we wanted to, we could always go back to the original matrix. Where is it? Way up here. And we could check that if we multiply by 2, 1, 2, make sure that we actually get what we're supposed to, which is twice the original eigenvector. If you want to make sure you didn't do any mistakes. Let's give it a try. If I do a times y, so that's 1, 2, 0, minus 3, 2, 3, minus 1, 2, 2. I multiply by 2, 1, 2. Okay, so I get 2 plus 2, I get 4. I get minus 6, plus 6 plus 2, I get 2. I get minus 2, and then I get plus 2 plus 4. So I get 4, which is indeed 2 times 2, 1, 2. Okay, so I know that it worked. We could check the other one as well. But here's the thing. Notice that we only get one eigenvector, right? Up to scalar multiple. We don't get two independent eigenvectors here. We only get one, right? All other eigenvectors corresponding to lambda equals 2 have to be scalar multiples of the one that we have. So that's the best we can do. There's just the one. So this would be a case where this matrix A cannot be diagonalized, okay? Because there's only one eigenvector corresponding to that eigenvalue of 2. And for Math 1410, that's sort of where the story ends. Let me give you, we'll just briefly say, well, what would happen next? Where do you go from here? Well, if you don't get enough eigenvectors, then what you do is you look for something called generalized eigenvectors. And so it turns out that what you should do, if you don't get enough eigenvectors from solving this equation, right? So we try to solve this equation and we only get one eigenvector, and that's not good enough. Well, what you do is you square the matrix. It turns out that there's some general theory that says if you have a non-invertible matrix, so you have some non-zero solution in your null space. Sometimes if you start taking powers of that matrix, you will get more solutions. So you get the null space gets larger as you take higher and higher powers of that matrix. Eventually it stabilizes. And so in this case, it'll turn out that if you square the matrix, you can actually find a second solution. And so you can solve that, and then there are some details that we're not going to get into here because it's not appropriate for our first course in linear algebra. But what we would get is we would get the vectors that we have, the x and the y that we already found, and we would get z. And this z would be this so-called generalized eigenvector. And I'm not going to go over how you find it because it's not important for this course. And then, you can set that matrix P, right, to be, this matrix where we put these vectors in as the columns, x, y, and z, okay? And then you do the same kind of thing where you do P inverse times A times P, right? And if your matrix can actually be diagonalized, then what we expect is we expect to get the eigenvalues down the diagonal. And remember, I did mention that you can always triangularize a matrix, right? You can always get a matrix into upper triangular form. And so it turns out that what happens when you do this right, when you use the sort of a certain standardized process for finding that generalized eigenvector, you can set things up so that you are very close to diagonal. And the only thing that's missing, or the only thing that you're off by, is just above where those 2's are on the diagonal, just above the repeated eigenvalue, there's a 1. Just off the diagonal, there's a 1. This particular form here, this has got a name. It's called the Jordan canonical form. Okay? And that's something that you would see if you go on. If you take a second course in linear algebra, like Math 3410 here at U of L, you would get into how do you figure out the Jordan canonical form of a matrix. So that's beyond Math 1410, but just in case you're wondering what happens, that's what happens. Okay, so this is our last batch of videos for Math 1410 linear algebra. And in this first video, we're going to look at some of the properties of the eigenvalues and eigenvectors of a matrix. And then from there, we're going to move on to talking about diagonalization and some of the applications of diagonalization. So to begin with, we start with a definition and a theorem. Now, these are results that you're familiar with if you completed assignment 5. We defined what it means for two matrices to be similar there. We said, well, we would say that B is similar to A if you can find an invertible matrix P, so that I can write B as P inverse times A times P. So that's what it means for these two matrices to be similar. And if I take this equation, if I multiply on the left, if I multiply both sides on the left by P, right, then I get to P times B is equal to A times P. And from there, I could go one step further, and I could say, I could write A as P, B, P inverse. Or if you like, I could think of this as Q inverse B and then Q, where Q is the inverse of P. I could do it that way, right? Because the inverse of the inverse gives you back the original matrix. And so saying that B is similar to A is the same thing as saying that A is similar to B, right? So this is a symmetric relation here between these two matrices. In fact, this is an example of what's called an equivalence relation. So not only is it sort of symmetric between the two matrices in the sense that saying A is similar to B is the same thing as saying B is similar to A, every matrix is also similar to itself, because I can take P to be the identity matrix. And similarity is also what's called transitive. If I know that A is similar to B, and I know that B is similar to some other matrix C, then I can conclude that A is similar to C. And what happens, and you study these a little bit, if you take Math 2000, you'll learn a little bit more in detail about equivalence relations, is that any equivalence relation takes your set, in this case the set of all matrices of a given size, and chops it up into what are called equivalence classes, so different subsets where everything within one of those subsets is similar to each other, right? So all the matrices that are similar to a given matrix, they all go in one group, and then if I find some other matrix that isn't similar to the ones I already have, then that starts a new group, and so on until you've exhausted all possible matrices. And the theorem here says that within any one of those groups, within one of these equivalence classes, within the group of all matrices that happen to be similar to each other, every matrix in that set is going to have the same trace and the same determinant, and also the same eigenvalues. Now, the first two, trace and determinant, that was done. You guys did it for me on assignment 5, right? Trace and determinant. These were the third problem on assignment number 5, right? And if you didn't do assignment number 5, well, you can also find these results and the proofs in the textbook. So maybe you should have done assignment 5. All you really had to do is go find the appropriate page in the textbook and copy and hand it in, and you could have got at least part marks. But in any case, perhaps you didn't get around to that portion of the textbook, and if you want to, you can go take a look. You'll find that it is indeed there. Now, what we didn't prove yet, what I didn't assign, because we hadn't talked about eigenvalues yet, is we want to argue that similar matrices also have the same eigenvalues. So how do we prove that two similar matrices have the same eigenvalues? So what we want to do is we want to suppose two things. One, lambda is an eigenvalue of A. And remember what that means. That means that A times X is equal to lambda times X for some non-zero vector X. And the other thing we're going to assume is that B is similar to A, right? So B is equal to P inverse times A times P for some invertible matrix P. Okay, and what do we want to conclude? We want to conclude that this same number lambda is also an eigenvalue of B. Okay, so how do we do this? Well, what we do is we say, you know what, if B is P inverse times A times P, as we noted above, I can write A as P, B, P inverse. And that means that A times X is P, B, P inverse times X. And on the other hand, that's equal to lambda times X. Because we're assuming that A times X equals lambda times X. All right. So let's take this equation here. Okay, and let's multiply both sides by P inverse, and what do we get? We get, if I multiply on the left by P inverse, then I cancel it from the left-hand side of this equation, and I get B times P inverse X is equal to P inverse times lambda X. But lambda is a scalar. I can pull it out of this matrix product and write this as lambda times P inverse times X. Right? And so now I can see that lambda is an eigenvalue of b, and I even know what the eigenvector should be for this eigenvalue lambda. My eigenvector should be p inverse times x. Well, there's one thing to be concerned about. How do I know that this is non-zero? Well, I know that it's not zero because P inverse is an invertible matrix, right? And we know that there are no non-trivial solutions to a homogeneous system with an invertible coefficient matrix. So if I take a non-zero vector and I multiply by an invertible matrix, the result has to be non-zero. Okay? And so that tells me that similar matrices have the same eigenvalues. So why is that useful or interesting? Well, there are a number of situations in which it's easy to determine the eigenvalues, right? One such situation is that of a triangular matrix. Okay, so for either an upper triangular or lower triangular matrix, and in particular for a diagonal matrix, you can immediately determine the eigenvalues by just looking at the numbers on the diagonal. So the diagonal entries on a triangular matrix are the eigenvalues, right? So if you have a matrix which is similar to a triangular matrix, well, you know the eigenvalues for the triangular matrix. Similar matrices have the same eigenvalues. So as soon as I know that my matrix is similar to a triangular matrix, I know the eigenvalues for my original matrix. Okay? So we can see how similarity could be useful here in the context of determining eigenvalues and eigenvectors. Now, by the way, this is not quite as convenient as you might think, because it turns out that in order to kind of determine this triangular matrix, which is similar to the one you started with, the standard procedure for figuring out what that triangular matrix is begins with finding the eigenvalues. So it's sort of a vicious circle. If you had the triangular matrix, you would know the eigenvalues, but in order to get the triangular matrix, you have to figure out the eigenvalues first. So that's, maybe a downside here. But the way to see that this does indeed work, right? If my matrix looks like so, if it's upper triangular, well, let's be suggestive and put lambdas down the diagonal, right? So let's say it's upper triangular, so zeros, 0, right? So everything below the diagonal is a 0. I've got possible non-zero entries above the diagonal. I don't care what they are. I've got some entries. And so when I do x times the identity minus a, right, when I try to set up my characteristic polynomial, and take the determinant of this guy, well, you can see what you get. You're going to get x minus lambda 1, x minus lambda 2, and so on down the diagonal. All these other guys are still zeros, and we know that for an upper triangular matrix, right, so this is a difference of two upper triangular matrices, so it's still going to be upper triangular. And we know that you determine the eigenvalues, or you determine, the determinant of an upper triangular matrix by simply multiplying down the diagonal, right? So the characteristic polynomial, it must be x minus lambda 1 times x minus lambda 2, and so on down to x minus lambda n, right? And so we know that the eigenvalues are simply the zeros of this polynomial, and there you have that polynomial sitting there in front of you already factored, and you can see that the zeros are exactly the diagonal entries. Good. Now, in this note here, I've mentioned that for a diagonal matrix, not only can you immediately read off the eigenvalues, but the standard basis vectors, the ones that have a 1 in one of the positions and zeros everywhere else, those are automatically eigenvectors, right? Well, what about for a triangular matrix? Is that still the case? Not necessarily. Here are 3 matrices with the same eigenvalues, okay? All 3 of these matrices have 1 eigenvalue. So for all 3 of them, we simply have lambda equals 2 is the only eigenvalue, okay? Now, it's repeated 3 times, right? But lambda equals 2 is the only eigenvalue, right? The characteristic polynomial here would look like x minus 2 all cubed, right? So it's a repeated root, if you like. It shows up 3 times. So if I were going to try to find eigenvalues and eigenvectors, well, this is sort of interesting, because if I did, for the first one, if I do a minus 2 times the identity, well, a is 2 times the identity, so I just get the 0 matrix, right? And so when I'm looking for an eigenvector, right, what am I trying to do? I'm trying to find a non-zero vector x that solves this homogeneous system. Well, 0 times x equals 0. That's going to work for any vector x, right? And so any x will do. So every non-zero vector is an eigenvector. And so then I have to think, well, okay, I don't want to write down any. I want to sort of, come up with the basic eigenvectors, right? Think about writing down the basic solutions to the homogeneous system. Well, the basic solutions are just going to be that I could take x equals I could take j, I could take k, right? Because every vector can be written in terms of those 3. So I have sort of 3 basic eigenvectors in that case. Now, when I do b minus 2 times the identity, right, you can see that something survives. That 1 up there sticks around, right? And so if I were to solve, if I were going to do b minus 2 times the identity times x, set that equal to 0. Well, that matrix there is already in reducer echelon form. Notice that this is one of these rare scenarios where there is no leading one in the first column. The first column is entirely 0, right? So for the corresponding homogeneous system, that first row would say 0x plus 1y plus 0z equals 0. So y has to equal 0. That means that a general eigenvector is going to look like this, x, 0, z, right? So x times I plus z times k, right? So the sort of basic solutions are going to be either x equals I or x equals k. But this time there's only 2. We had 3 options for the matrix A. There's only 2 options for the matrix B. And you might guess that for the matrix C, if I do C minus 2 times the identity, right, now I get this guy, right? And this time, if you were to kind of play around and solve the homogeneous system, well, you can see that the first component can be anything because there's no leading one in the x column. But y and z both have to be equal to 0, right? So in this case, every eigenvector is a scalar multiple of a single basic eigenvector, simply I, right? So the basic solution here is only I. So for the matrix C, there was only one eigenvector, one basic eigenvector corresponding to our eigenvalue, right? The matrix B had 2. The matrix the matrix A had 3, right? And so we'll see that. So you can see that not all matrices with the same eigenvalues are created alike. You do have to pay a little bit of attention to what's going on off the diagonal. Okay, so that's sort of the basics for the properties. In the next video, we're going to look at this process of diagonalizing a matrix. All right, so this is going to be the first of 2 videos on this problem of diagonalizing a matrix. In the previous video, we saw that similar matrices have the same eigenvalues, and so it's interesting to look for cases where your matrix is similar to a triangular or even better diagonal matrix, because for a triangular or diagonal matrix, you just have to look at the numbers down the diagonal, and those will tell you what the eigenvalues of your matrix are going to be. But we also saw in those last few examples that we looked at in the previous video that when you have a repeated eigenvalue, you might get more than one eigenvector coming with that eigenvalue, and you might not. And that kind of question of how many eigenvectors come along with a repeated eigenvalue is very closely related to this question of whether or not you can diagonalize a matrix. Okay, so what does it mean to diagonalize a matrix? Well, we say that we can diagonalize a matrix A if A is similar to a diagonal matrix. So if you can find an invertible matrix P, so that when you do P inverse times A times P, you get a diagonal matrix, right? And so we know that similar matrices have the same eigenvalues, so if A is similar to this diagonal matrix D, then we know that the diagonal entries of D have to be the eigenvalues of A. And one of the things that you can show, and it takes a bit of work, and essentially this the proof of this theorem down here, we'll see that to some extent the proof of this theorem falls out from just kind of looking at the procedure of how do you go about diagonalizing a matrix. It turns out that the way you diagonalize a matrix is you find the eigenvalues, then you find the eigenvectors, and if you have enough eigenvectors, to form a basis for all of Rn, then you can diagonalize. And this matrix P, okay, the columns, we'll see that the columns of P are going to be the eigenvectors, right? Now, remember that for a matrix to be invertible, the columns have to be linearly independent. So you have to be able to find enough linearly independent eigenvectors, right? It's an n by n matrix, so you need n linearly independent eigenvectors, and a basic theorem of linear algebra, one that we don't prove this in 1410, but in 3410 you would prove that anytime you have n linearly independent vectors in an n-dimensional space, you're guaranteed that they form a basis. So enough independent vectors automatically span. Okay. So if you have a diagonalizable matrix, then we can compute the trace and the determinant of our matrix, because we also saw in the previous video that similar matrices have the same trace and determinant, and since we know what the trace and determinant of our diagonal matrix is, right, if this is our matrix D, right, we know that the trace is given by just summing down the diagonal, right, so the sum of the eigenvalues must give the trace, and the determinant is the product of all the diagonal entries, so the product of the eigenvalues gives the determinant. If you can diagonalize your matrix, then we can compute trace and determinant, right? If you can't diagonalize, whether or not these remain true, actually it will be true in general that the determinant is the product of the eigenvalues, but you do have to allow for the possibility that some of those might be distinct, or sorry, might be complex. So there are some kind of issues to deal with there. But in general, this is sometimes a useful bit of information, that trace and determinant can be computed in terms of eigenvalues. Okay. Now, one of the important facts about eigenvectors corresponding to given eigenvalues is that if you take a collection of different eigenvalues, so if none of these eigenvalues from lambda 1 up to lambda n, if no two of them are the same, then you're guaranteed that this collection of eigenvectors corresponding to those eigenvalues will be linearly independent. Okay, the proof of this it's not going to fit on one slide. There's a fair amount of work to proving this result. Some of the details are given in the textbook if you want to see it. But a consequence of this fact is that if we have n distinct eigenvalues, so if all of the eigenvalues are different, and this is the case of an n by n matrix, right? So the two n's here, they match up. Okay, n eigenvalues for an n by n matrix, and each eigenvalue is different, so there are no repetitions. If you have n distinct eigenvalues for an n by n matrix A, then you're guaranteed that you can diagonalize. Why? Well, because if you have n distinct eigenvalues, each one comes with an eigenvector. Those eigenvectors are guaranteed to be independent, and so you've got enough to form a basis. Right, so this is a standard result. If you don't have any repeated eigenvalues, you're guaranteed that you can diagonalize. Okay. So as a quick example, let's say we want to determine whether or not this matrix can be diagonalized. So if I wanted to decide, well, the chances are we're going to apply this previous result, but in order to apply it, the first thing I've got to do is I've got to find the eigenvalues. So let's see. What does the characteristic polynomial look like? Okay. So determinant of x times the identity minus a. Again, I like to do x times the identity minus a because I like the way the polynomial comes out. If you're worried about making sign errors, there's nothing wrong with doing a minus x times the identity. You can do that instead if you want. But I'm going to do it this way. Okay. So what do I get? I get x minus 2, 0, minus 2, 0, x minus 2, 1, minus 1, 1, x minus 4. All right. 3 by 3 determinant, so we've got to expand, right? With the x's in there, it's kind of hard to simplify using row operations. So let's just try to expand along. Let's go along the first column. So we've got x minus 2 times x minus 2, 1, 1, x minus 4, minus 1. That's this minus 1 right here. This guy. Okay. Minus 1 times, if I delete row 3, column 1, I'm left with 0, minus 2, x minus 2, and 1. Okay. So I've got x minus 2 times, so I've got x minus 2 times x minus 4, that's x squared minus 6x plus 8 minus 1 from the off diagonal. And here I've got, so I'm going to have minus 2. Okay, so overall minus sign, right? Because I've got a minus 1 up front, a minus 1 there, and this is the off diagonal, so another minus 1. That's 3 minus signs, 2 times x minus 2. And you might be tempted to expand everything, collect terms, and then see if you can factor, but notice you've got a common factor, x minus 2 in both, okay? If you can do this sort of group factoring, you're much better off. So we pull out the common factor, x minus 2, leaves me with x squared minus 6x. Here I've got plus 7, but I'm subtracting 2. So that leaves me with 5, okay? So now I've just got to factor that quadratic, and that's something I can handle. I get x minus 1 times x minus 5, and so I get lambda equals 1, 2, and 5 are my eigenvalues. And notice that I've got 3 eigenvalues, and they're all distinct. And so that means, and we aren't doing the diagonalization yet, and I, it takes a while to do a diagonalization problem, so fitting one into a video is sort of time prohibitive. But we can, at the very least, we can conclude that A can be diagonalized. Okay. If we wanted to go through the remainder of the diagonalization procedure, we would have to find eigenvectors for each one of these eigenvalues, form this matrix P whose columns are given by those eigenvectors, then find the inverse of P, then multiply everything together to see that we do indeed get a diagonal matrix with the eigenvalues down the diagonal. But that's a lot of work. That's a good, that's another 10 minutes of work that we're not going to try to squeeze into a video that's already long enough. So this will be our second of two videos on diagonalization for Math 1410 linear algebra. In the previous video, we saw that whenever you have distinct eigenvalues, so for an n by n matrix, if you can find n different eigenvalues, then you're guaranteed that you can diagonalize, because each eigenvalue will come with its own eigenvector, and those eigenvectors are guaranteed to be independent, and you can use those independent eigenvectors, collect them together to form an invertible matrix. Now, if the eigenvalues are repeated, you've got a little bit more work cut out for you, right? So in general, you're going to have several different eigenvalues, right? Say lambda 1 up to lambda m, but each one comes with certain multiplicities, right? So the multiplicity of an eigenvalue is just how many times it's repeated in the characteristic polynomial. So these are the numbers k1, k2, up to km. Okay? These numbers. And so one of the things we do know is that if I choose one eigenvalue for, say, lambda 1, and I choose an eigenvalue for lambda 2, I'm guaranteed that those will be independent, right? So if I choose one eigenvector for each eigenvalue, I'm guaranteed that those eigenvectors will be independent, right? But what I don't know is, let's say k1 is equal to 3, right? What I don't know is, can I find 3 different independent eigenvectors for that one eigenvalue? This is the question that's going to determine whether or not we can diagonalize in the case where we have more than one eigenvalue, where we have a repeated eigenvalue. Okay, so the language that we'll use here, and it's fancy sounding language, but it's a fairly basic thing. So we talk about the eigenspace of an eigenvalue. Okay, so the eigenspace is basically the set of all possible eigenvectors, right? We want this to be a subspace, so we throw 0 in. 0 is not an eigenvector, but we need it to be in the subspace. So it's, what is it? It's just, it's the null space of this matrix. It's the set of all solutions to this homogeneous system, right? So in other words, it's the span of the basic solutions to that equation, and the basic solutions to this equation are called the basic eigenvectors, and we'll say the basic eigenvectors for this particular eigenvalue lambda. So we'll call that a lambda eigenvector. Okay, and so what we're interested in is what's often called the geometric multiplicity of the eigenvalue, as opposed to up here, these multiplicities k1 up to km, they're sometimes called the algebraic multiplicity because they show up in a polynomial. So the dimension is the number of basic eigenvectors, right? So this this number here, dimension of the eigenspace, this is the number of basic lambda j eigenvectors. Okay. And a basic fact is that for every eigenvalue, there's always at least one eigenvector. So the dimension of this space is always at least 1 if lambda is an eigenvalue. And the maximum possible dimension is the multiplicity of the eigenvalues. So, so if you have distinct eigenvalues, if each eigenvalue only shows up once, then each one of these spaces has to be one-dimensional. But if you have a repeated eigenvalue, if say k1 is equal to 3, then the lambda 1 eigenspace, it might be one-dimensional, it might be two-dimensional, it might be three-dimensional. We don't know which one it is. And if we want to diagonalize, we want to max out these dimensions. We want the biggest possible dimension in each case. Okay. So I don't know if we put that. Yeah. So that's the result here. Okay. So in order to diagonalize, right? So the question of when can you diagonalize in the setting of repeated eigenvalues? Well, you can diagonalize as long as the dimension of each null space matches the multiplicity if they're equal, right? It might be less. If the dimension ends up less, then you can't diagonalize. If it's equal, you can. Okay. One thing that I should, if we're being, let's be kind of honest and open about things here. We've completely factored this characteristic polynomial. If we want to guarantee that we can completely factor, we're allowing for the possibility of complex eigenvalues here. Okay, so we are working over the complex numbers when we make this statement. The other way you can fail to diagonalize is if you're trying to work over the real numbers. You might just be unable to factor your polynomial. That's one of the problems that might come up. Okay, so here's a matrix. I want to figure out if I can diagonalize. So how do I proceed? Well, I find the characteristic polynomial. So let me find, well, I guess this will be the negative of the characteristic polynomial. Last time we did xi minus a. For those of you who like to see it done the other way around, let me do it that way for you guys, okay? A minus x times the identity. So we take our matrix, we subtract x's off the diagonal. Okay, 0, minus 3, 2 minus x, 3, minus 1, 2, 2 minus x. So let's expand along the first row. 1 minus x, 2 minus x, 3, 2, 2 minus x, minus 2, so deleting column 2, row 1, minus 3, 3, minus 1, 2 minus x. Right. So you can see the advantage of doing it this way versus doing, we could have done x times the identity minus a. The advantage of doing it this way is you don't have to worry about flipping signs on the entries of a. The disadvantage is that you're dealing with all these minus x's everywhere, and so the algebra at this stage is a little bit, well, I mean, it's not that much worse, but you have to think a little bit harder. Let me pull that minus sign out. So I have an x minus 1. So here I have x squared minus 4x plus 4, and I'm subtracting 6 minus 2 times, so what do I have here? 3 times x. So minus 3 times a minus x is 3x. 3x minus 6, and then plus 3. Okay, so let's do a little bit of work here. X squared minus 4x minus 2. So this is 3x minus 3. I can pull out an additional 3 here and write it like that. And then again, I can do some group factoring, right? I've got a common factor, x minus 1. So that leaves me with x squared minus 4x minus 2 minus 6 more, so minus 8. Okay. And now, and I'll hope that I have not messed things up here anywhere along the way. X squared minus 4x minus 8. Can I factor that? I'm not so sure that I can. Does it factor nicely? Doesn't seem to factor nicely. Okay, let me pause for a second. Okay, let's resume. Realize where I went wrong. Where did I go wrong? I went wrong because, and this is where I don't like kind of doing it this way versus doing it this way. That minus sign out front caused me a whole world of trouble. When I bring that minus 6 inside, I got to account for that minus sign. That minus 6 becomes a plus 6. So that minus 8, is a plus 4. And there we go. Now I can factor. I get x minus 2 squared. Okay, so we can see that the x minus 2 is repeated, and that means that the lambda equals 2 has multiplicity 2. Okay, now I want to know if I can diagonalize. So in order to figure out whether or not I can diagonalize, I've got to see how many eigenvectors come along with lambda equals 2. So let's add a page in here. Okay. We'll add one more. Oops, I don't need that. There we go. And let's see if we can figure this out. So when lambda equals 2, okay, I've got to do a minus 2 times the identity. So a was 1, 2, 0, minus 3, 2, 3, minus 1, 2, 2. Make sure I remember that right. Yeah. And I'm subtracting off 2, 0, 0, 0, 2, 0, 0, 2. Okay. So I get minus 1, 2, 0, minus 3, 0, 3, minus 1, 2, 0. Okay. And I try to get this thing down to reducer echelon form. So let's see. So I want reducer echelon form. So I'm going to go 1, 2, 0, minus 2. We can see that row 1 and row 3 are identical, so I get that row of zeros at the bottom. I'm going to get, if I take, I'm going to get 0, minus 6, 3. So I'm going to get 1, minus 2, 0, 0, 1, minus a half, 0, 0, 0. Okay, and so I don't really actually need to write down this. I could write down the solution if I wanted to, but at this point I just do a little bit of analysis and I say, look, there are two leading ones. That means one parameter. And that means one basic solution, which means one eigenvalue. One independent not eigenvalue, eigenvector. Okay. And so what that means is that the sort of lambda equals 2 eigenspace, the dimension of the lambda equals 2 eigenspace is 1, which is not equal to 2, and that means that we cannot diagonalize. Okay. One more example. We'll press on. We're probably getting a little bit long in the time, but let's do one more. Okay, so I'm going to do my determinant x times I minus a, x minus 2, 0, 0, 2, x plus 2 minus 2, 5, 10, x minus 7. So expanding along the first row, I get x plus 2 minus 2, 10, x minus 7. So x minus 2, I get x squared minus 5x. I get minus 14 plus 20, x squared minus 5x plus 6, which is x minus 2 squared times x minus 3. So in this case, when I do a minus 2 times the identity, okay, I'm going to get 0, 0, 0, right? Minus 2, minus 4, 2, minus 5, minus 10, 5. And this time, if I take that guy to reducer echelon form, I get 1, 2, 1, 0, 0, 0, 0, 0. Okay, so there is, in this case, one leading one. That means two parameters. So the dimension of the lambda equals 2 eigenspace in this case, E, is 2, which does equal the multiplicity. Okay, And so in this case, I get two eigenvectors coming along with that lambda equals 2 eigenvalue. We haven't bothered to find what they are yet. We'll do some examples like that in class. And so the answer in this case is a yes. We're going to get two eigenvectors from lambda equals 2. We're going to get one more from the lambda equals 3. That's going to be our basis of eigenvectors that we need to construct this matrix P that we use to diagonalize.